There is this running joke that diffusion math is this crazy complicated thing. You've seen the memes, simplest diffusion paper, hardest LM paper, LM maths, diffusion maths. There is this general consensus that diffusion math is this magical, crazy, complicated field, but I sincerely don't think that's the case. I think that just like any other subject, diffusion math comes out of very fundamental first principles, and once you understand these basic ideas, then everything just comes together and makes sense. So instead of writing on Twitter like diffusion math is very easy actually, I've decided to explain it. So that's what this video is about. So here's the plan. There's just one rule, and that's that I gotta explain everything. So no hiding behind slides or blogs. Now I love blogs, I think they're amazing, but I think that it's very easy to hide behind an equation. So instead what we're trying to do here is to talk through each one of these steps that leads us to understanding these fundamental principles. So okay, what are the resources? Well, first of all, you get these video notations. So everything that you see on screen, every note that I scribbled down, you'll get access to. I actually created this entire platform myself. So if you come here and then you paste this URL into your browser, you'll get access to absolutely everything you're seeing. Second, every single paper has been implemented into code. So you get access to the Google Colabs, kind of like an MIT style type of class. Finally, everything that we learn will be related to the actual Stable Diffusion code. So we have something that I've called local Stable Diffusion, which is this thing right here. And what this is this essentially an implementation using the original weights of Stable Diffusion all the way into image generation. Now, this is not actually my code. I originally implemented my own code, but then I came upon this video um, by Omar Jamil, in which he codes a Stable Diffusion from scratch, and I thought that it was really, really good. So it's a nice resource to have because you also get his video as well. Okay, so now let's talk about the game plan. This is gonna be a multi-part series. Here on the left, you'll see the papers that we're gonna go through, and here on the right, most importantly, you get the concepts that we're trying to learn. Now the papers, we'll take a look at the original diffusion paper, we'll take a look at the unit, we'll take a look at DDPMs, we'll take a look at improved DDPMs, and then finally diffusion model speed cans on image synthesis. As I said, most importantly, what are the concepts that we're trying to learn? Well, first of all, what is diffusion? So what is the general idea behind diffusion? Second, we'll take a quick introduction into statistical mechanics and how and why machine learning is related to statistical mechanics. Now you can actually skip this section. You can skip this section of the video because this is not strictly necessary in order to understand diffusion. I have added it because I think that it is very, very important for us to think in terms of statistical mechanics and in terms of energy, especially in the long run. So I think it's very important. Also, we're not going to go super deep into it. We're just going to take a look at the basic equation of statistical mechanics. Okay, then we'll take a look at stochastic processes. So like Markov chains, we'll take a look at probability distributions, the unit, negative log likelihood, the above. And as I said before, every single paper has been implemented into code, so you get access to the code as well. We also take a look at some diffusion improvements, and then finally, a working history. So this last paper essentially led the way for this diffusion world that we live in, essentially. Okay, now as an interlude, you get access to this stochastic processes video, which is a story time. This is a video that I've been meaning to do for a long time, and this is learning the mathematics at the same time as you learn about the history behind the math, which I think is a very fun and useful way to learn. And then on part two, just as a sneak peek, we'll go through variational autoencoders, attention is all you need, classifier free guidance, estimated gradients of the distribution, and score-based models. The concepts are like autoencoders, attention, guidance, differential equations, gradients, vector fields, score functions, and so on. And then at the end, we'll take a look at the implementation of stable diffusion and the actual paper. So this is going to be quite a long road, but by the end of it, you'll see that diffusion math isn't magic. Diffusion math is just a sequence of beautiful and simple ideas. And we'll go through each one of these ideas together. Okay, what is diffusion? You might have already seen this very satisfying, like, blob of noise that slowly turns into a beautiful image. But what is really happening here? Well, diffusion in machine learning at its core is essentially learning to undo chaos or to reverse time. Now, let's just go to like a very simple scenario. Let's say that you go to your favorite cafe and then you order a latte. And then let's say that your barista adds like a heart on top. Now, you're charmed, but you're very busy, so you just let it stay there. And then after some time, this is not a heart anymore. So this is just like a blob. And then let's just say that an hour later, this is definitely not a heart anymore, and this is just like some brownish liquid because like it just diffused. Now let's imagine that we had a magical black box. and then you gave this brownish liquid to the black box, and then it would go do, 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 and it would go back in time essentially, and it would give out your coffee with the heart on top made out of cream. This is a bit of an exaggeration, but in spirit, this is what diffusion is doing. Now let's look at like maybe like a more serious example. Let's say you have a painting, and there's like a gorgeous painting, just work for it. And then let's also say that we have a hammer, and then we slowly start hitting this painting. So we slowly start hitting this painting. One hit, two hits, and so on, until at the end, we're left with just like a bunch of splatters. So we just hit this painting over and over again. Now, this is essentially our so-called forward process. And what you're doing is you're destroying structure. You're adding noise, right? So we had this structure and you're just slowly destroying it. The cool thing about diffusion modes is that they're learning this, but in reverse. So how do you slowly, step by step, go back to something that resembles your original data? Now, there are very different strategies on how you could achieve this. For example, I don't know, we could say that we could recreate the painting slowly. So we start here, and then you would slowly recreate the painting until at the end you get something that resembles your original data, your original painting. We could also, for example, we could also say that we could try to predict exactly which hammer hit happened. So I don't know, let's say that, okay, at this time step, this hammer hit happened. So we remove it. And then we could say like, okay, at this time step, this hammer hit happened. So we remove it. And then this hammer hit, and then we remove it, and so on, until you get back your original painting. There are different ways of doing this, but fundamentally, and the most important thing is that step by step, you are getting back to something that resembles your original data. Now, in these videos, we'll actually take a look into the intricacies of the mathematics and the models themselves and how do you actually train something that does this. But the most important part and what you should like get out of this video right now is that diffusion at its core is just learning how to reverse time on your data. Okay, so now we'll take a look at the original paper that introduced the idea of diffusion. This is called deep unsupervised learning using non-equilibrium thermodynamics. If this is the first time that you heard it, this might sound like very intimidating, but I'm sorry, it's not that bad once you go into each one of the concepts. So what does it mean for something to be deep? It just means that this is using large neural networks. What does it mean for it to be unsupervised? This just means that this is learning from raw data. There are no labels, there are no like right answers in this case. So just raw data. Of course, the deep learning. And finally, the hardest part is like this non-equilibrium thermodynamics thing. Like, what is this? Well, non-equilibrium thermodynamics is this slice out of statistical physics, which treats, of course, with systems that are not in equilibrium. Now, the thing is, you don't necessarily need to be an expert in non-equilibrium thermodynamics or know the field at all in order to understand diffusion. This is just an idea that was borrowed from non-equilibrium thermodynamics from this field, and then it was used in machine learning, and this is how we got to diffusion models. But you don't need to like be able to solve like college level questions on non-equilibrium thermodynamics in order to understand what's happening here. Now, having said that, I think an introduction into statistical physics is actually extremely important if you want to get into machine learning. There are two main reasons for this. The first one is that I think it's very useful to think in terms of statistical physics, especially in the long run. So we're going to get eventually to something that is more energy based, and having these intuitions of how it works, like things work in statistical physics, helps a lot in my opinion. And then second is that a lot of machine learning is actually inspired from statistical physics. So the first equation that we're going to derive, and the only one that we're going to derive in this introduction, is going to be the Boltzmann equation, and we're going to get to the Boltzmann distribution. And then it turns out that this Boltzmann distribution has the mathematical equivalence of softmax. So they're essentially the same thing. So once you get the intuitions for the Boltzmann distribution, you will also get some intuition about softmax and how it behaves. So once again, I think it's very, very important because a lot of concepts follow these same ideas of like being inspired by statistical physics. Now, having said that as well, you can always, as I said at the beginning, you can always skip this section of the video. If this is like too abstract or too complex, you can just skip it, and this won't change much in order for you to understand diffusion at this level. Why are we talking about statistical physics? Well, turns out the world is very big, right? You just look around, there's like a lot of stuff. And then you probably already know that like everything is made up of even smaller particles. So like everything around you is made of atoms, and then it's made of molecules and stuff like that. So the world is just very big and very complicated and very granular. So as a physicist, if you're trying to understand the world, right? Let's say you had, for example, a pool table. Let's say you had a pool table. Um, and then if you're a physicist, if you know with how much force you hit this ball, for example, and if you know the angle, right, of where of the angle where you hit the ball, you know the speed of these things, you know the positions of all these balls. Uh, if you basically know all the data about this specific ball, right? Like you know the position, okay, it's like I don't know 20 centimeters of this thing, or if you know all the details, you will be able to basically reconstruct the entire game. You will be able to know exactly if you hit this ball, where are the rest of the balls going to go, right? As a physicist, you can do that. Now the problem, as I said before, is that the world is just very, very big. It's around 10 to the 23 orders big. Now, what is this number? This is just a random number that's pulled out. You maybe seen this before. This is called Avogadro's number. Um, Avogadro is like this very, very, very beautiful man. Avogadro. Yeah, sorry. Sorry, dude. He's not very good looking guy. Um, and now this number is basically what we use in physics and chemistry and all this stuff to say this is related to a mole. So this is the unit. This is like the basic unit. Now, what is a mole, right? Like this is so useless to like to you right now. Well, a mole is basically the amount of particles that are in like a tablespoon of water. So if you had a tablespoon of water, the amount of molecules that are going to be inside of this thing, they're around 10 to the 22. That is a mole. Um, so yeah, this is kind of like just a unit that we use to describe things that are around us in the world. So like if you try to do the same analogy as we did before with this, if you try to do the same analogy of like, well, if I knew every single position, every single angle, every single velocity, every single like force that I'm applying, I could basically recreate the entire game. Well, if you try to recreate the entire game, so to say, inside of like this tablespoon of water, that would be around 10 to 23 particles. Um, no, that's a lot. You can do, of course, simulations and stuff like that, but as a physicist, right, if you're trying to understand and make statements out of this, well, that's kind of really, really hard and not very useful. Another way of looking at a mole, it's, sorry, this close, okay. Another way of looking at a mole is basically the amount of air molecules that are inside of a balloon. So you had a balloon, right? Let's just draw a balloon. The amount of air molecules are going to be inside of this thing. They're also going to be around 10 to the 23. So that's basically where we're looking at the world, right? If you look at everything around you, everything is made of atoms, everything is made of particles. And we kind of use this 10 to the 23 number. Avogadro's number is actually 6 point something to the 10 to the 23, right? Yeah. So what do we do, right? What do we do if we cannot look at the world that microscopically? Well, what we do is we look at things macroscopically, right? Instead of microscopically, like, oh, itself, every single little particle, as I said before, with the pool table. What we do is we take a look at things um, on the on the bigger properties that we can actually look at. So if we go back to this very funny like balloon example, let's say that we have this tiny little balloon, right? And this tiny little balloon just has two air particles inside. So this thing has like just two particles. Um, Now we could, the internals of this thing, kind of like what we said about the pool table, right? Like every single position and every single, for this we only have two, so we can use the same analogy. So we can tell where each particle is, we can tell how fast it is going, and then we can, based on these properties, we can get like a more interesting thing. In this case, we can take, for example, the energy. Now, what is the energy, right? That's a really good question. I said before, I'm going to try to explain everything. It's like, what is the energy? Well, we know that energy is 1/2 mass velocity squared, right? So if we had two particles, that would be like, well, the mass of particle one times the velocity of particle one squared, and then the same, and then that half, and then the same for the other particle, right? Um, well, now if you don't know where this thing comes from, as I said before, I'm really, really trying to get everything from first principle. So if you don't really understand where energy comes from, well, we define energy as the capacity to do work, right? Capacity to work. That kind of makes sense. You're like, dude, I need to work. Let me just get like a Red Bull or something. Like I need energy. It kind of makes sense, right? Um, so energy is defined as the capacity to work. Now, what is work? Well, work is just like the force to move something a certain distance. So this is literally just like work equals like the force time at distance, right? Which is also gonna make sense, right? It's like, oh, like I don't know, like if you move something, you can just like put work into it. Um, And then like we can even go further. Like, what is a force itself, right? Well, we know by Newton's second law that force equals ma. We can even go further. Like, why is this the case? And this is actually like Newton's very critical insight. Um, so like basically Newton, if you remember Newton's laws, right? This is from like very basic physics. First law is that like an object will just keep moving, unless a force acts into it. And then the second law is just defining this force. Now, the interesting thing about Newton, is that you think about these things and you're like, well, of course, right? Like this is very basic. But at the time, um, we didn't really understand how things moved, if that makes sense. We didn't really have like a clear mathematical kind of like foundation of how things um, just like behave in the world. Anyways, that's where energy comes from. I said before, like I kind of just want to be very fundamental on the things I'm explaining. So this is where this equation of energy comes from. As I said before, basically you get an energy for this specific system. So this system, you have these funny particles, and they can be in different positions, and they can have different velocities, and this is the energy for that. Um, then let's say we have a balloon, right? But this balloon also has just two particles. But then one of those particles is not really moving, but the other one is moving really, really fast. Like the other one is moving really fast, but the other one is not really moving. So this one would have the same energy as the other one, even though their internals are very different. So at the end, the energies are the exact same, right? And then we have another balloon. And this, in this case, we also have like two particles for this balloon. And then once again, the other particle now it's moving really, really fast. Um, and the other one is just not moving. So once again, microscopically, if you look inside this balloon, if you look at where each particle is positioned and how fast it is moving, it would be very different. But the energy at the end, they're all the same. Once again, what is energy? Well, it's just the mass of this one um, times the velocity of this one squared, and then half of that, and then plus this one. So that's like the total energy. That's what we're looking at right here. So you can kind of already guess what we're looking at right now. And this is what physicists have generally named microstates. Microstates and macrostates. Macrostates. Once again, like it's really at the heart, right? You can say like microstates just like where things are inside microscopically. Macrostates is just how do those micro states relate to an actual bigger thing, in this case energy. Now you can already kind of like make the connection probably that a lot of macrostates we can actually measure, right? You can think, for example, in terms of like temperature. We can actually measure temperature, even though internally it might have different configurations. So okay, I think the kind of like the idea is already selling in, right? Um, the idea of like, yeah, we have microstates and we have um, macrostates. Now, something very important, we call these microstates this sig letter. It's a psi. Now don't be scared. Like a lot of people get really scared when they see like these crazy kind of like um, mathematical formulas where they use like psis and like a lot of Greek letters and stuff. I'm like, they're just letters. They're the same thing as like calling these like A or B or C, right? They're just like letters. So yeah, it's just even cooler, right? Like if you could write a mathematical equation, you would probably use the coolest letters. So they're just really cool. Anyways, that is not the reason, but like my point is like just don't be scared. A microstate is called this psi. Now we're gonna get into like some actual mathematics, but it's very easy once again. Um, what we do is we basically get every single microstate that has a certain energy. Um, Now what is this? Once again, I'm trying to make everything very fundamental. This is called set notation. Set notation. This is kind of just like a list, right? What this is doing is remember what we called microstates. So like each one of these will be a different microstate. So this would be one, this would be two, and this would be three. Now, if I call you like, oh, what is psi one? Well, it's where there's two particles and they have like this velocity. And what is psi two? Oh, one is stopped and the other one is going really fast. And what is psi three? Oh, it's the same thing, but like the particles that switch around. Um, well, this set notation basically is just like a mathematical way of describing every single one of these. So this is just saying this is kind of like a list. You can think about it as a list, um, kind of like having all these things. This is kind of like a more programming relationship. And if there's a mathematician watching this, they're probably gonna hate me. But I don't know. I feel like this is kind of like an interesting way to look at it. It's just like very easy. It's called set notation. And then once again, it's kind of like a list that hosts all the possible configurations.
And these are the possible configurations that have this exact same energy. So where energy 1 is equal to energy 2, which is equal to energy 3, right? So basically, um, this would represent like the things we have on top. Now, if we had an extra balloon, right, with now let's say two particles, and then both of them are going really, really fast, then this energy would be energy would be huge, right? This would be huge, huge energy. So this psi 4, for example, it wouldn't be in our list. So it wouldn't be on our list because it doesn't have the same energy. Okay, I think that's really easy still, right? Like this is very, very easy still, nothing crazy just yet. Some math, but then again, just don't be scared. Like it's not that hard. Um, it's just some funny notation and some funny cool letters and stuff like that. Now this, if you want to know, this is called a microcanonical. Microcanonical. But honestly, like, you don't have to remember the name. Like that's not that useful. Just remember what this represents, right? And we looked at the balloon. We look at each particle that kind of like is the same thing as a pool table, and then we look at like different balloons that have like the same configurations, um, the same micro configuration, and just different internal kind of like microscopic positions and velocities. And then at the end, we kind of just put them all in a list, um, and we call that the microcanonical ensemble. Okay, so now we say something right here, and we say that like every single one of these um, examples of these microstates, they're all the same probability. Now, what does that mean, right? This is actually extremely important. So like very, very important. You don't really have to like understand why it is important right now, because it will make sense when we advance further. But this is basically saying that if you only knew like the energy, it could kind of be in like any one of these positions, right? Like if you kind of knew the energy, you could be like, well, these ones have all the exact same energy, so it could be any one of these microstates. So that's something that we're doing. Like they're indistinguishable, basically. So now we come up with this very funny function that it's also gonna look crazy if you're not used to this, but it's gonna be a function. It's gonna use the op thing, and then you're gonna pass the energy, and this is gonna give out the number of microstates, right? With E, with energy E. Now, once again, like you don't have to scare. Like this is very, very easy. Once again, like what would happen if we use this with our energy, with this energy, right? What would happen? Well, it would just give us three. Why? Because there's three balloons that have these microstates. So this is just a function that is giving you basically the number of microstates that have this very specific energy. Now, the actual form of this function is irrelevant right now. Like that's not the point. We're kind of just coming up um, with this function that gives out, kind of like spits out. You can think about like a function in programming. Like it just returns the number of microstates. Now there's something here about like energy being not precise, and like you cannot really get precise energy due to quantum mechanics and stuff like that. So you are not really getting like a specific energy, but like a little tiny like spot. But that's honestly like that's not that big. That's not very important. Um, so okay, we are okay so far. I think this all makes sense. Now we will go into our first equation and our first like big topic, and this is called the Boltzmann distribution. That's just a little one. Distribution. Wow, this is huge already, right? You probably heard of this. You probably already heard of like what is the Boltzmann distribution. It's this very, very useful thing. Okay, before we go into the how we get the Boltzmann distribution, there is something extremely important we have to say right here, and this is related to the paper actually, and this all is under equilibrium. Equilibrium. Wow. Now, why is that important? This is basically, non-equilibrium thermodynamics. That's crazy. Well, this is the first one that says that it's under equilibrium. What does that mean? Well, if you go back to the balloon example, let's say you have a balloon, and let's say that the air particles inside this balloon, they're very chill, right? The balloon is it's pretty cold, right? It's kind of cold, right? Like they're pretty chill, they're chilling, they're moving that fast, and then all of a sudden decide to put in a lot of hot air, like really, really hot air. Really hot air. This is going super fast. Boom, right? Extremely fast. You're putting hot air into this thing. Um, Now, as you probably know from like just experience, um, at the beginning, a part of the volume is going to be hot, and then the other part is just going to have the exact same temperature as temperatures to have. Um, but with time, these temperatures will basically equalize. Then again, you have this example even in your car when you turn on the AC. It's just like it's cold air, and then eventually, you turn it off, and it's kind of cold at the beginning, and then it just merges with the rest of the air in the room, and it kind of just like um, achieves like it reaches a stable temperature. That stable temperature, when like basically all of them kind of like combine, and you just get a unified temperature. This is what we call equilibrium. Equilibrium. Now that is very important because this is basically what the paper is saying. Non-equilibrium thermodynamics. Why is it non-equilibrium? Well, we'll see that in a second. But like we kind of know, at least we know equilibrium now. Okay, that's amazing. We that's really good. We can already know equilibrium. Again, as I said before, this is the same thing. And if you put like your AC on your car, this is the same thing. Even as the original example of the coffee cup, right? This is the same thing. It basically reaches a point where this is equilibrium, and like after this, there's really not much else. Like it doesn't really matter if you leave this all night; it will still look the same. If you leave this night, it won't really merge anymore. Like that's it. It's equilibrium. Um, it's kind of the same thing, and this is a really useful and useful. It's kind of like the same thing if you put like melted ice cream on the fridge. You put it melted ice cream on the fridge. So this is water, and you put it on the fridge, and then if you check like an hour, well, that's still pretty much cold melted water. Cold water. It's not really frozen. But then if you check the next day, well, now it's gonna be actually frozen. It's gonna be just frozen. And then if you take a look like 3 years, right? It's still gonna be frozen. It's not gonna be like a difference really. But this is basically it reached equilibrium. At the beginning, it's water, and then once it freezes, it just reaches equilibrium because like it doesn't really matter. If you check in like 3 years or whatever, it's gonna be the exact same thing. So that's equilibrium, and maybe that's already giving you an idea of why care about non-equilibrium thermodynamics. Maybe, but if it's not, then don't worry about it. Like we'll take a look at it a little bit later. So okay, we already said Boltzmann distribution. This is what we're trying to get, and we already said that this is thermal equilibrium. In terms of mathematics, this is saying that in the system, right? In this case, our balloon, the system is in equilibrium. It means the probability of the system becomes independent. So the system is time independent. Now, once again, this is just mathematical for saying like it just doesn't move anymore with time, right? Like this thing, if you look at the beginning at the melted ice cream, well, this is time dependent because if you look at it 1 hour, it's gonna be just cold water. If you look at it maybe 3 hours, it's gonna be almost melted, but not really. If you look at it like one day, then it's gonna be frozen, right? So this is cold water. This is like kind of melted a little bit. I mean, not melted, but like frozen a little bit. And this is like truly frozen. And then if you look at it here on, it doesn't really matter when you look at it. Could be 1 year, could be 3 years, could be years. No, it doesn't really matter. This is time independent. So, mathematics, we just say, wow, our system is time independent. Okay, so I think this all makes sense. I think. Um, uh, so now comes the good part. How do we get the Boltzmann distribution that basically tells us what is the probability of getting this exact same balloon given our energy? Um, and we'll basically create a DOM, not really a DOM, but like we'll basically make up our own scenario so that we can extract stuff from it. So let's go to our balloon, right? Let's go to our balloon. And let's say that this balloon has an energy, and let's call this the environment, whatever. Now this means once again, like this doesn't have to be a random number. We know exactly what is energy from before. What does it mean that this balloon has an energy? It just means that it has particles that are moving at certain speeds that are in certain position. Um, and once you calculate the energy for each one and then you add them all, this is basically the total energy that this thing has. So this is, it's a number. You just have to like relate it to the actual physical thing. You have this balloon, right? And this is like a huge energy. So like this has huge energy. Once again, what does it mean for it to have a huge energy? It means that it has like a lot of particles going really fast. Now we have this little tiny thing in the balloon. This is kind of like a mini balloon inside of the balloon, right? It's gonna be like really tiny. And then we will say that inside of this balloon, we also have some energy, but this energy is just like tiny, 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 tiny. So like, what is like for this energy to be tiny? That just gonna have like some particles that are going really, really, you know, like not that many particles first of all. So like the one on the one outside might have like a lot of particles going really fast, like just a ton of them. And then tiny, tiny, tiny little balloon, it's gonna have just like a couple particles, right? So let's say just put some numbers into it. Like this has like I don't know if it's like 100 particles or something, or 3,000, and then this one has like 5, or even more. Like doesn't matter. The point is like this energy on the outside is huge. This energy on the inside is just like tiny, 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 tiny. And we call this state psi I. Now, once again, what does it mean for this thing to have this energy? Well, I said it before. It just means that the sorry, that the particles inside there are not that many particles and they're not moving that fast. And then what does this thing mean? This is just, as I said before, the balloon configuration, so the microstate of how the balloon is looking. This is how we of course we don't know this. So we're just gonna put a letter to it. So okay, this is our system. This is our system. There's something different here, and this is that this wall basically allows heat, but it doesn't allow the particles to move, right? So it allows heat to move around, but no particles can escape. Um, well, that makes sense, right? Because if a particle would escape, this would be like a different picture, because now the particles would kind of share. Now, why do we make up this seemingly random example? We're like, why did we come up with this? I know the thing is like in physics, there is this tendency to write examples that are really, really easy that will help us understand the general problem much better. So you have like this general problem that is really, really hard, and just make like just dumbest example, just make it the easiest thing possible. The same with your programming, right? When you want to like this crazy feature, you can just make it work, make it. You can like, oh, like I want this crazy thing to do and to work, and then just like make the simplest possible implementation of the feature, and then you add and then you complexity on top of it. It is basically the same thing. So we're basically creating this seemingly random ensemble, this seemingly random system, just understand something way more complex and way more general. Okay. So now we say that this thing has E of the environment plus the E tiny thing. This is the total E. Right? This is totally. As you remember before, this is actually pretty big. This is also pretty big, and this is just a little tiny guy. Just a little tiny image. Put that function. And this is like the energy if you sum them up. And this is the energy of the entire balloon. So this is basically both of these added. So it's just the entire balloon. So I think first of all we're just gonna rename these things so that it's clear. So I've renamed basically this as environment, as we had before, and I've renamed this as sub. So this would be just like a subsystem, right? I think this makes things way clearer in the future. So once again, when we say the energy of sub, that's just the energy of this tiny little thing. And then when we say the size of sub, that's just one microstate inside of this funny little um, subsystem. I think this makes things a lot simpler, hopefully. Okay, so what we're looking for is we're looking for the probability of this size sub, right? Once again, don't get confused by this like funny symbols and stuff. This is just the probability, like what is the likelihood of getting um, any one of these subsystem configurations. So if we look at our previous example, right? Remember, we had 3 balloons. They had the same particles, um, and with different movements, velocities in each one of those particles, we got the same energy. So they all had the same energy. They just had like different configurations. So if you wanted to ask, like, what is the probability of any one of these configurations? Well, that would just be, 1/3, because we have 3 balloons. That would just be 1/3. It's basically you're saying like 1 over the total number, for this energy. So if you had this energy and this energy only has 3 different configurations, well, the probability is just 1/3, right? It's that simple. Now, in this case, we cannot just do like, 1 over the total number. Why? Well, because now we have a subsystem, right? We're looking for the probability of any configuration inside this subsystem. That's inside this that's that itself is inside this bigger environment, right? So we have this case where like we're looking for this thing of, that corresponds with to this tiny thing. Um, so we cannot do the exact same thing as before. If that makes it clear. Um, so what how they usually teach this is they just go like, okay, the probability of this of like any um, microstate is just proportional. They just go this is proportional to the number of microstates in the environment, right? That's what they usually say. Now, if you don't know what proportional means, that just means that like there's like a constant, right? Like if this side increases, if this side increases, this side also increases with like a constant, right? With like a factor. That's basically what this thing is saying. Um, Now, why does this make sense, right? Why are we saying that the probability of finding any particle configuration is proportional to just the total number of um, microstates, like the total number of possible configurations of these things, right? Well, this has to do with something called combinatorics. And this is extremely useful. This will be especially useful when we get like this core function. Um, so let's look at a very simple example, right? Let's say we have like two normal dices. We have two normal dices, each one with six faces, right? Six faces, six faces. Now, if you wanted to look at like all the possible options or like all the possibilities of running these two dices randomly, you would get like 1, 2, 3, 4, 5, 6, right? So the first one you could get like 1, 2. Now for the second one, you could also get like 1 and 2 all the way to 6. So for example, you could get 1 on the first one, so this one, and then you can get a 1 and 1, right? And you can 1 on the first one and then 6 on the second one. So basically, this is kind of like our all of our possibilities. And at the end you have like 36 total possibilities. So if we go one step further, we can define a function that if given a dice, it just gives you just give me 1 second. Okay, anyways, just do it by hand. If given a dice, it just gives you the total number of possibilities, right? So this would be 6 times 6, right? And this would bring us our final number. Okay, so far so good, I think. Now what happens if we change these dice? Like what happens if we change this one and we instead make it a bigger one of those like odd kind of like 20 phase things. Now we plug it right here. This would be now 20, right? Be 120 now. Now, what I'm trying to say with this, what I'm trying to get at with this example is that like, if you had two sets of possibilities, right, and then you want to look at the combination between those possibilities, at the total number of combinations between these two possibilities, this is basically the equivalent of just getting the combination and the other combination, and then just make the product of those, right? So for this example, the total number, right, the total combination number, or total, this would be equal to um, the number of combinations in the environment times the number of combinations in this subsystem. This would be a total, so this would be like every single one. Now, we said at the beginning that this one is way bigger, right? This one had like a lot more particles than this tiny little one. So basically, like this one is just tiny. This is tiny. And this is very, very big. This is like huge. So the total number of particles really basically depends on this one. Now, okay, I think so far everything makes sense, right? So now we go back to our dice example. If we say, for example, now that we have a constrained number of possibilities, let's say we can only have 100 possibilities and we have two dices to make it work. There's different ways of making this work, right? We can just say, okay, one of our dice is gonna have 10 possible configurations. It's gonna have 10, and the other one will also have 10. It'll be 1 and 10. But we could also say like, oh, what if we make this instead 2, and what if we made this 50? That would be also 100 total possibilities, right? Now, what if we check this second dice, what if we check what is the possibility of getting any one of these faces, right? Any single one of these faces. Well, for this case, it's just 1 over 10. But what happens when we make this other one, instead of 10, we just make it 50. And this, instead of 10, we just make it 2, right? Now this on top would be 50, so there's like a lot more options. And here there are a lot less options, just 2 options, just 2. Well, before it used to be 1 over 10, and now it's just 1 over 2. So we just have 2 options. So you can see that if we increase this dice, if we increase the amount of probability, the possibilities of these dice, it also increases the possibilities. I mean, not the possibilities, it also increases the probability of getting any single option on the other dice. So if we kind of like relate this to what we know, right? Getting any single phase, any single possibility is the same one as getting any single microstate. This is the same thing, right? Like any single this is the probability of getting any single microstate. It's the same thing as the probability of getting any single phase, just like a single phase, right? And this is just a number of possibilities. So if you change the number of possibilities in the environment, which is the huge one, it basically makes the probability of getting any phase inside the small one very big. What does this mean mathematically? I think that's clear enough, right? What does this mean mathematically? Well, mathematically, this just means that if you increase the number of possibilities in the environment, that would also increase the probability the exact same way as we did before, right? So this is how they come up with this relationship. So now we finally have just like a thing that says, well, for any one of these sub ones, right, this is proportional to this thing on the environment. Now we just say that like this proportional. What is the environment? Well, the environment is just the total energy minus the energy. We'll just make this smaller because the total energy is really really big and the other one is really small. So it's kind of like a way of representing that. Um, they're both energies. It's just a graphical way of representing that. Okay, so I think I did a very poor job explaining this before, so I'm just gonna do it again. So yeah, once again, as we did before, it's just some mathematical parkour. Basically, we're just doing the exponent of the log, which cancel each other. So we're basically doing basically right now. And then we do something that is very, very common in mathematics and in physics called a Taylor expansion. So this is a Taylor expansion. Now, as I said before, like just to be very clear on the fundamentals, like, okay, what is a Taylor expansion? I'm not. This is the first rule. I should explain everything. So a Taylor expansion is basically like if you just have a function, right? And then you have a point, let's call it this x. And then you want to know, like, oh, what would be, like, where would be a point that's very close by, right? Like, let's say this is close by. Where would that be? So this is just like x plus a, right? This is distance, is a. Well, Taylor expand the Taylor series, Taylor expansion basically tells is that like this next point will basically be dependent on the derivative of your function. So once again, like just to be super clear, just remember what a derivative is, right? So like a derivative is just it's just the rise I think that's how the Americans call it, right? So like um as this equals 0. So like basically if you have a point, that's x, and you have another point, that's x plus a little bit. What you're basically doing is determining this height, which would be the part over here, right? So like f of x, which was this minus, I mean, this height minus this height would be this, and then over we stepped on, right? So the derivative is basically just this height over here over how much we stepped on, we stepped for. And then we just make this be extremely small, very close to 0, and that's a 0 derivative. So basically, that's how you get a tangent line. Because this is literally just telling you like if you step 1 to the right, you will be here. And that's exactly what you do for Taylor. Like once you get this derivative, you just get this tangent line and you just go and then, oh well, what if I step like this little bit? So you will be here. So this is an approximation, of course. Then you do like this for more and more and more and more derivatives, and eventually you actually converge to the point that's here. So this would be like once again, this would be kind of like just taking the tangent line and being like, oh, like a little bit here. It's just, and then you just do that for other derivatives. Um, and that's basically a Taylor expansion. Uh, there's a way to prove it, and it's not that hard, but I just won't do it here. So okay, what is the Taylor expansion of this thing? So like if put this entire thing back, um, the Taylor expansion of this thing would be just first one minus the derivative of the logarithm of this this function, and then multiply by this thing. And then it's like the Taylor expansion, as I said before, is basically like it has a bunch of derivatives. So like it just goes, oh, it just goes, it just keeps and keeps and keeps and keeps going. But basically, there's a way to show mathematically that like this is n that the derivative of like this thing, it's basically close to zero for like anything that's like n more than two. This is also very easy to prove, but I don't think it's necessary. So yeah, just trust me. Just that like all these other values are useless. So we basically only take these values. Okay, sick. So you basically get as I said before, you just get these values. So like this is proportional to like the exponent of the logarithm of this thing. Do this quickly minus this thing. Um, okay, perfect. Now first thing is just a constant, right? This first thing is just a constant, so we don't really care about it. As I said before, what is our definition of like something proportional? It's just like just a proportionality factor, right? So like this proportionality factor can be anything basically. So we don't really care. So we can make this smaller. Right? We don't really care. That's what we're using the proportion notation. So basically, it just makes this thing smaller. So we don't really care about constants. So we just okay. This first part is a constant. So let's just get it out of here. And then we get to the actual Boltzmann. This is not the Boltzmann equation. This is called the Boltzmann factor. But we finally get to the Boltzmann factor. So the Boltzmann factor is just this thing proportional to the exponent of this thing. Uh, uh. And the thing is like, this looks like a lot. So we just say that all this stuff is just beta. We just make it even easier. We just say like they say the proportional to minus beta. Okay, so far so good. What? No, you might already see me like, oh, this kind of looks like something I already know, right? This kind of looks like something. If not, I think it will be clear in a moment. But for now, let's just see what this actually means. What this is saying is basically the probability for this microstate to be in this to be in, like the probability for any single microstate um is proportional to the negative, like the exponent to the negative energy, right? How does that look like? So remember, for like a normal exponential function, it kind of looks like this. But now this is a negative right here. So it kind of just goes the way back. Maybe this would, so this is like that, and this one looks like this. And we only covered this one right now. As you can see, like, oops, let's go. As you can see, this is how it looks like. But this is not an actual probability. This is not an actual probability distribution, right? It's just a factor. That's why it's called the Boltzmann factor. So what you do is basically you want to make this right. Let's just see what this is like. If you just plug in a certain energy, it would basically give you, the height of this exponential would basically give you the. It is proportional to the height of that thing. So the probability will be proportional to this height, right? So what do we need to make this an actual probability distribution? Well, we need to make it, be one. Any probability distribution can just be one. You cannot have like 110%, right, of probability. It can just be one. So basically, what you do is you say like, okay, this is for um, a single microstate for a single energy. So basically, what you do now is you say like, okay, the general equation for this thing is just like equal to what we said before. Now over this thing. Now, if you remember from earlier, this just means the sum. This is just the sum. So like this could be 1, 2, 3, 4, 5, 6, 7, whatever. This is just the sum of that. Now, if you're into machine learning, you might be like, oh well, that's that looks familiar. And well, yeah, this is literally or like this is the same form, the same form as the softmax equation. So if you look at the softmax equation, right? Softmax function. Let's just take a quick look at this thing. Softmax, what is it? It has functionally the same form. This is just not negative. Now, why is that the case, right? Why? Why do they look? Well, it's because they both represent kind of like a probability, and I think this makes a lot more sense if you look at it from like the literal like graph, right? So if once again we just go like this, and then this is basically saying like, okay, if you have like different energy levels, well, like if you want um the probability of like a microstate being one of these energy levels, you basically just like select one of them, and then you just you divide it over all the other ones, add it up, right? So this would be basically like, this is a height, by the way. So I'm representing this as a height. This is the height, this is the height, this is the height. So this would be, um, let's say, we want this height right here. So, and then this is the first height plus this height right here. It's kind of like a smaller plus this tiny one. And if you look at it, right, that's kind of like, what if we just add all of this up, you just get like a really big height. And then that is composed of like this big one and this small one, right? Um, and then you say, well, if I want to check this middle height, how much of the total height is this a percentage of? So this is, I don't know, kind of like 40%. So this would just be like, okay, that's a 40% probability. And that is the exact same thing that happens in softmax. The only thing with softmax that is, with softmax, it's not a negative exponential, but it's a positive exponential. You're gonna go like this. And then once again for softmax, you just give it like a bunch of values, right? Just give it like 3, 5, -2 or something. And then this will give out a probability distribution. Why? Well, if you just plug like 3, 5, -2, and then you just check the heights, right? Check the height, check the height, check the heights. And then you just add all of these heights together, right? So you just get like a big height. And let's say like this is for 5, and let's say like this is for 3, maybe a bit smaller. And then let's say this is for -2. Well, this is kind of like 50%. This is, I don't know, like 30%. And this is 20%, right? It's basically the same thing. It's basically the same thing. And one of the, like, the really important reason why we're watching this and like why I want to make all these relationships is because like once you understand all of these like physical intuitions and once you get really comfortable with just analyzing models and analyzing systems, like a lot of the concepts in machine learning and in other things will start to resemble like things that you already know, right? And this helps a lot to actually develop intuitions and to actually develop a lot of these techniques. So we will see, going back to the actual paper, that this guy, Sasha Sludikstein, used like one of these intuitions from non-equilibrium thermodynamics to develop what we now know as diffusion models. So basically, I mean, we're now at the Boltzmann equation. Now this has like a lot of branches. With this Boltzmann equation, you can define basically like entropy. You can define like temperature. You can define a lot of stuff. And then I really wanted to go into the Gibbs entropy, but I don't think that's that useful. So I think I'll leave it up here. But basically, what we did right now is we just went to the entire model. We just analyzed it, and then we arrived at a very interesting solution that kind of looks like a softmax. Um, we learned about combinatorics. We learned about a lot of like their expansion, a lot of mathematical parkour, um, and we also learned about what is actually equilibrium in regards to thermodynamics. So okay, hopefully this was clear. And once again, there's like a lot. Like this is very very basic. This is like the introduction. Um, for example, you can see right here if someone is interested that what are these energy levels, right? Like how do you define these energy levels? Like what is this thing? That is a really good question. And the thing is like if you know something about quantum mechanics, like these energy levels are actually discrete, kind of like this. Then if you have gases, that's kind of like continuous. energy levels. But okay, I don't think that's that useful for the current discussion. So for machine learning, we're just gonna leave it at that. But yeah, hopefully this was clear. Um, and yeah, we have like a really really cool and like a super important uh, physics equation. So now we'll just keep going now to the actual machine learning. Okay, yeah, I just wanted to do one last very very quick thing about like why this was different. Um, so yeah, we basically derived all these things, and we ended up at this equation, and then we said like, oh, this equation can look softmax, right? But just super quickly, the Boltzmann distribution is not the like softmax and Boltzmann is not the other one, the only ones that use kind of this distribution. So I just want to show you that an example of something else that uses this distribution. So for example, you probably already know that if you go up from the Earth, you're still getting like different kind of like um, layers of the atmosphere, and as you keep going up, the density starts going down. Why? Well, there's gravity, right? So here there's going to be like a lot of air particles, and then there's going to be less here, and then here's going to be like almost and then like no particles at the top. Now, fun enough, if you look at the actual equation for this in terms of height, well, let's just look at the Boltzmann factor, right? So the or like let's just look at the factor itself. So it's the exponential minus b e. If your energy is like gravity, you now have something that kind of looks like this. What is this saying? It's just saying that let's just draw the thing again. This is just saying that let's just define this as n of h. This is just that as you keep decreasing, I mean as you keep increasing the height. So like this is the height, right? So you go from here to here to here. As you keep increasing the height, the amount of air particles will just go down exponentially until you can reach zero. So okay, that's it. Super quick. This has actual like other relationships which are like super interesting. Okay, now next, let's keep going. Okay, so very shortly on the relationship between statistical physics and machine learning. As I said before, it is no surprise that our Boltzmann distribution ended up looking so much as a softmax. As far as I understand it, it literally comes from there. It is not like an instant step. I believe that the Boltzmann distribution eventually started getting into like different fields, and it eventually turned up in machine learning. But essentially, it literally comes from there. In a second, we will see like an intuition that will make this a lot clearer, and will hopefully also strengthen the relationship between what we just learned and machine learning. But once again, if you know a little bit of the history and the origins of like machine learning, you might have also heard of something that's called like Boltzmann machines. And well, Boltzmann is right in the name, right? So we just learned the basics and the fundamentals of like the Boltzmann distribution, which, as I said before, is very very intertwined and inspired a lot of things in machine learning. So thinking about statistical physics, for example, thinking in terms of combinatorics, thinking in terms of energy, thinking in terms of the number of microstates, for example, like this has all this, well, thinking in terms of probability distributions, this has a lot of intuitions in machine learning in the future that are going to be incredibly useful. So once again, this does matter. So we'll now look into an example that will hopefully make this a lot clearer. So before we said that, okay, this entire thing is just going to be beta because that made things easier for us. But now we won't ignore it, and then we'll take a look at what beta is. So we say that we said that beta was the derivative with respect to the energy of the logarithm of the number of microstates for a given energy. And then what we do in physics normally is like, okay, you call this S, and this S is entropy. I will explain what like the intuitions behind this in just a second. This actually has a K in here, but it's not that important for our purposes. And then we say that 1 over the temperature is equal to the derivative with respect to the energy. Okay, this is of course temperature. What does this mean intuitively? This is just saying that, okay, we just call entropy essentially the logarithm of the number of microstates. So we have like a lot of microstates, that is really high entropy. If we have very low number of microstates, that is very small entropy. And then we say the difference in entropy, so essentially the difference in the number of microstates
in the log number of microstates, of course, but essentially the number of microstates will be equivalent, inversely proportional to our temperature. So what is this saying? This is saying like if you add a little bit of energy, so like a little bit of energy into our system, and then the change in entropy, so the change in the number of microstates is really high, that just means that we're in a very low temperature. What does this mean? Well, if you're like very, very cold and then you add a little bit of energy, so a little heat, that heat will go like a long way, right? You're very, very cold and yeah, a little bit of heat will go a very long way. But let's say that you're in like hell, like you're already super, super, super hot. Um, then a little bit of energy won't change things that much, right? So if the change is small, this just means that the energy is very big. Why? Because you're already super hot, so a little bit of change doesn't not gonna change much. But if you're very cold, a change will be very high. Once again, because a little bit of energy will go a long way. That is essentially what these things say. Now, there are a lot of very interesting things that you can derive from this. For example, we can take a look at, well, what would be a negative temperature, right? Because like this doesn't prohibit a negative temperature. And it turns out that in physics, you do have negative temperatures for some like funky quantum states, but that's not that important for us. What I want to go into right now is just that what we defined before as our Boltzmann factor was something like this. And then we have this extra temperature thing. And let's just see how this looks like, right? So let's see how this looks like. I just decided to add a couple of points just to see how, so you can move this around. And then this is our temperature factor. And then what happens if we increase the temperature? Well, our plot moves like that. So once again, we're not moving the points, we're just leaving them there. And then what happens if you make this close to zero? Well, you see that this will have like a starker difference between these, right? It's like these are very low, while this is very high. And then we said that this is equivalent mathematically to softmax, right? So this equivalent mathematical softmax is a different sign. And then if we take a look at that, so this is softmax, and this is just like some points that I decided to put in there. And then what happens if you increase the temperature? Well, this starts, they start having essentially the same heights. And then what happens if you decrease it? Well, the difference are very, very stark. So one might be like super, super tall, while another one would be like tiny. Once again, what does this mean? Let's just explain this intuition. So if we quickly plot our softmax. So we plot our softmax. So this is our exponential. And let's just say that we have these 3 points. And then we take a look at the heights for this exponential right here. And then we say in softmax that what we do essentially is we just add up each one of these heights. So the first one plus the second one plus the third one. And then we divide over the total height, and this would essentially tell you like, okay, what percentage is this height compared to like the total. So for example, this would be like, I don't know, like 40%, and this would be like 30%. And then, well, I think let's just say this is 40 as well. And then this is like 20. Something like that, right? But well, what happens now if we change our temperature? So once again, let's just say that we were at 1 at that point. And then what happens if we make our temperature larger? Well, our plot starts looking like that. So now our points that haven't moved, that you see where they will end up. So once again, if you do this, this will just make the distribution kind of like this. Yeah, this is just an approximation. And then if we take a look at the heights, once again, we haven't moved our points. We just take a look at our new heights. This would be here, this would be here, and then this would be here. And then once again, if we take a look at, we add the first one, we add the second one, we add the third one. And then what percentage of this compared to the entire thing is? Well, this is basically just 30%, 33%, 33%. And then let's just look at the last example. So now what happens if we make the temperature very, very small, so close to zero? Well, we'll see that the difference are very stark now. So once again, if we do this, this will be kind of like doing something like this. And then if we take a look at where those heights are, well, this is going to be very, very small. And this is going to be like relatively large, and then this is going to be huge, right? Huge. So once again, if we do softmax, the first one plus the second one plus the third one. And now let's just say that this is something like, I don't know, like 80%. And this is like 19%. And this is like 1%. So once again, for a machine learning model, right? This is your output, and then you're trying to predict, okay, which one is the most likely like response? Well, at the beginning, this might be like relatively likely. So they just see these are words, so this might be like a very close synonym, right? But then if you increase the temperature, then Once again, let's just look at the thing. If you increase the temperature, then the heights start becoming very similar. So if you increase the temperature, now the words have the same probability, right? So this might use like a different synonym, or this might use like this might take the sentence into a different direction. So this would be more creative. On the other hand, if you decrease the temperature, so if you make this very, very close to zero, now this is deterministic. So it's like, okay, this is the next word that has to go after this, right? Like 80% probability. That's it. So this is essentially what's happening with these models and how you can in an LLM, for example, make the temperature smaller or make it bigger, and this would turn out into something that is more creative or more deterministic. And it all comes down for what we just learned into statistical physics and machine learning. Okay, I hope that was fun. I hope that was useful. Once again, there are like a lot of different things that you can take a look at. For example, just some hints if you want to research this by yourself. It turns out that if we look at our distribution, and then if we just take a look at like one of these, so like this would be one, it turns out that this looks like a sigmoid. And then if you can follow those sigmoids, you can see how it changes. And this makes sense when you're training a model because you want, for example, one label to be like more likely than the others. And then it turns out that if you make one more likely, the other ones will decrease like a sigmoid, but this will increase like a sigmoid. So that's something that you might research yourself. But once again, I just wanted to like drill the point that the statistical mechanics and the statistical physics and machine learning are like very, very related. And it does matter that we learn this. Okay, so if we want to understand this paper, deep learning using non-equilibrium thermodynamics, right? If we just go and take a look at the paper, we can see it right here, right, in the abstract. Inspired by non-equilibrium and statistical physics to systematically and slowly destroy structure in data distribution through a diffusion process. We then learn a reverse diffusion process that restores structure in data. Okay, cool. If you look a little bit further, it goes, our method uses a markup chain to gradually convert one distribution into another. The idea from non-equilibrium physics and sequential multicolor, whatever. We build a generative markup chain, which converts a simple known distribution, example a Gaussian, into a target data distribution using a diffusion process. Now, this sentence right here is probably like the entire paper. Like, that's it. This is like the entire concept of the paper. And well, you cannot really understand this paper if you don't really know if you don't understand what a markup chain is. That's pretty much fundamental. So right now, I will do exactly that, right? I will explain from very basic principles, so like all the way from the start, what a markup chain is. This is something called the stochastic processes. If you've never heard of the stochastic processes, then this might sound very abstract. This might sound crazy, right? You'll be like, well, there has to be some like insane mathematical models or something. The truth is that it's really not. It's actually quite intuitive, and it's really really fun. So we will learn it now. Okay, so what is a stochastic process? Like, just what is this thing, right? It's actually very simple. A stochastic process is just this thing. If you don't know what that is, I'll explain in a second. This thing is called a random variable. This is just mean that it's indexed by time. And this is just, as we said before, this is just set notation. So this kind of makes it, I mean, if you think about it in programming terms, it kind of makes it like a list. It's not really that, but it's kind of like a good way of saying it. Now let's go with parts, right? Let's just start at the beginning. What is a random variable? Well, first of all, what is a variable, right? Well, a variable is just a substitute for something else, of course. It was, I think, first used by like the Descartes or something, um, and it basically just covers something that you just don't know. For example, if you have like this equation, well, this variable has the value of 2, right? Then if you have like something different, for example, like y equals 2x. Now, this variable might have any value, right? Any value. So like this could have like 1, 2, 3, 4, whatever. This could have like negative numbers, right? Minus 1, minus 2. This value could be 0. This value could be pi. This value could be anything. So that's it. Basically, it stands for all these different numbers, right? That's a variable. Um, this is actually called real numbers. Anyways, now what is a random variable? Well, the same way this basically is just a substitute for something else. A random variable is also a substitute for something else, but this something else is random. It's inherently random. So if you have this random variable, for example,
and we say that this variable corresponds to the toss of a coin. Oops. Now this variable inside would have heads or tails, but um, as opposed to like these other variables, this is a random one. So this doesn't like this is not heads or tails. This is both of them, right? It's just a random variable. This is the values that it can take, but this is just well, random. So this is basically like a random variable, just heads or tails. It could also be I don't know something different, right? You can just say like this is, for example, I don't know the amount of cars on the highway. I live next to a highway. You can probably hear it. And I don't know. This is kind of random, right? You can be like, oh, there was 200 for the first day, and there's like 100 for the other one, and then one day they just stopped it, so like they just closed it to this zero, and then there's like a 1,000. There was like a parade. So this value kind of represents that randomness, right? This is just like, oh, this is just the amount of cars going to the highway, and we use this instead. So that's a random variable. Okay, so we know the first thing. What does it mean indexed by time? Well, indexed by time is just saying, well, it's just we start at one, like we start at zero, I guess, and then we start at one, and then two, and then three, and then four. So we basically start, at zero, and then we keep going. And then, as I said before, set notation, this kind of makes it a list. So you can just say like, okay, just putting everything together. Let's say we have the toss of a coin, and then it's indexed by time. So at time zero, we toss a coin and we get heads. So we just get heads here. And then we do it again, and then we also get heads. And then we do it again, and we get tails. And then we do it again, and it keeps going. This is basically a stochastic process. Well, this is not basically, this is exactly an stochastic process. That's it. A stochastic process is literally a random variable indexed by time. Once again, a random variable is just a representation of a random event. And then indexed by time is just like, well, you put it chronologically, basically. Like, that's it. You just start at the first one and like end up at the last one. Um, so that's all a stochastic variable, a stochastic process is. That's literally it. Now, as it happens in mathematics, a lot of things they're very general and they're very basic, and you can construct very complex structures and you can make very complex arguments and solve really cool problems with this. So we will now go into a little bit more depth. So let's just define a new stochastic process, and we will say now that like we will call this y, right? You usually put a stochastic variable in capital letters. So now we would say that y is basically just similar to like heads or tails, but we would say that this is like if it so like with 50% probability, this will be 1. With 50% probability, this will be -1. This is basically like saying if it is heads, this will be -1. If this is tails, this will be 1, right? So now if we look at this stochastic process, that might look something like this, right? We might say like, oh, at first it was heads, so that's -1, and then it was heads again, so it was -1 as well, and then it was tails, and then it keeps going, right? So this is basically what this thing is saying. Now we can go even further, right? I think this is still like you can still see how this is a stochastic process, right? This is just random variable index by time. Now we can create a new stochastic process, and this is called this C. And now we will create this new stochastic process, and we will make it basically be the sum over y. Now what is that, right? You might be like, why? Wait a second, right? Like, what did you just make? Well, this is very easy. Once again, we can just go by what we had before. So this will be the sum of y's, right? Y is just a random variable indexed by time. So if we start at the beginning, if we just start at zero, at at the very beginning, well, at first it's just one -1, right? So we just say -1, and then at this part, the sum is not going to be -1. It's going to be -1 -1. That's going to be -2, and then the next one is -1 -1 plus 1. That's going to be a -1 again, right? And then it just keeps going. Now we call this z, right? This is once again just another stochastic process. Now we can graph this stochastic process. We can graph this thing, and it would basically look like this. We can call this time. This will be 0. It would be like 1 and 2 and 3 and 4, right? So we start at 0, and we say at 0 that this is -1, right? So you just kind of starts like right here, -1, and then, well, this is a bad example because I should put this. Give me 1 second. Uh, there we go. Okay, so we start at -1 at 0, and then we go to -2 at 1, and then we go to -1 at 2, and then it just keeps going, right? Well, since this is random, right? This is literally like tossing a coin and getting these values. So you could get like heads, heads, tails, tails, heads, like whatever. So if you would imagine this, if this keeps going for a really long time, you would get basically something like this, right? Let's just do this very quickly. Let's just say, okay, tails is 1, and then heads is -1, right? So just get like tails, 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 and then heads, and then tails, and then heads, 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 tails, heads, tails, head, tails. And then if you keep doing that, right? Like if you make it more and more and more granular, um, you cannot get these things. You know, there we go. And that is basically a stochastic process. Now you might already be like, okay, this kind of looks like something, right? Um, this kind of looks like a stock, and that is exactly the case. Stochastic processes are extremely useful for stock analysis and a lot of financial things. We basically use the same mathematics for a lot of financial math. You will see in a second how we can do analysis on these things that seem random, and we can get rid of that randomness, and then we can add some randomness, and that's the whole point of stochastic processes, because it kind of looks like random, and it is random, but in a moment we will see how we can extract some information of this randomness. This, what I just described right here, this is called a simple random walk. Simple random walk. Now, I don't think this was particularly hard mathematically, mathematical wise, right? Like, this was pretty chill. We kind of just like said like, okay, this is just the sum of the over this value, um, and then if you keep going like tails, 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 so like heads, 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 you could just add one or subtract one, and then we get kind of like these funny little graphs. So that's what we call a simple random walk. Is like the simplest stochastic process that you can get. Um, okay, so that's really cool. Now mathematically, you can ask a lot of stuff about this thing. So for example, like you can say like, okay, what is the expected value of like our what is the expected value of our random walk? And you will see that this is 0. Now, if you don't know what expected value is, that's okay. I will explain in a second. What is an expected value? An expected value is something very similar, very easy. Is this kind of just like an average? This is kind of like an average. It's not really an average, but it's kind of like just like an average. And this is basically saying the sum of the probability times the actual occurrence. So, for example, let's just say you have a dice. Once again, you just have a dice, and this is like 6 faces, and then each one has like a 1/6 possibility of appearing. So you would basically just go. Remember what we said before, that this is just a sum, right? This funny little symbol is just a sum. This is a really good example. So we would just go like 1/6 probability, and then the first value is just 1. Then plus 1/6. The second value is just 2. Then plus 1/6. The third value is just 3. And then just keep going, right? Plus 1/6. And then at the end, you will find that this is like 3.5. So the average, I mean, not the average, but the expected value of like this thing right here, like let's just put a dice here, is just gonna be 3.5. Then once again, it's kind of like an average. It's not really an average, but it's you can kind of see like an average. Um, so if we look at this thing, like why is the average? Sure, well, because like if you think about it, right, we're just doing randomly up and down, up and down, up and down, up and down. So like we're not really going anywhere, right? Like this thing is not really going on anywhere because there's a 50% chance of going up and then a 50% chance of going down. Like you can imagine a scenario where like, okay, there is an 80% chance of going +1. So you can go +1 at the beginning, and then well, there's a lesser chance, um, a smaller chance, I guess, to go down. So like you can keep going up, 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 and then down, and then up, 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 and then this would be an expected value that's different than 0. But for a simple random walk, since it's a 50% chance to go up or down, this would be the expected value of 0. Now, this thing about the expected values, you will see them everywhere. So you kind of like this is the simplest example, and it's really good because you kind of like get used to it. But these expected values are like literally everywhere, and you will find them in the latest the latest diffusion papers. Um, you will find them everywhere. So yeah, you just kind of get used to them. Now, there's a lot of other mathematical things you can start saying about this random walk, right? There's this thing called like independent increments. But basically, with independent increments, this is basically saying, um, like what happened before, it doesn't really matter for what happened next, right? Um, so like if you know what happened in the past, this doesn't really matter because like at this point you can just keep going up or down. So you have two choices. So like that's called independent increment because what happened here doesn't really matter because you're already here. And there's like this other stuff. For example, this is also like the stationary that stationary distribution. And so like, but like I think this is good enough for our purposes. So like we'll just keep going. So once again, in just a simple random walk, you can do like a lot of analysis, right? You can start asking yourself like, okay, how how quickly could I get to like 30, right? Like if you tell me like let's just toss a coin, and if you win, I'll give you $10, and if you lose, you give me $10, right? And if we plot this stochastic process, we're tossing a coin. So at the beginning, let's just say this is from my perspective. So I just gain $10, and then I gain 10 more bucks, and then I just lose $10, and then I win again, and then I lose again, and so on, right? Once again, if we define a new stochastic process, the sum, well, what would be my total in my wallet? At the beginning it will be 10, then it will be 20, then it will be 10 again, then it will be 0, then I would owe money. It keeps going, right? Now let's just say this is 300. Now I just said like at the beginning I have 10, and then I have 20. It's not in scale obviously, and then I lose, and then I lose again, and then I lose again. You cannot. You might want to ask like, okay, is there a way I can tell if this could go to like 300? Is there a way I could like just lose so that I can stop playing the game? Um, so you can do a lot of analysis, and this is actually extremely interesting. But then again, this is something I'm just telling you so that you can like so you can get the inspiration. But like I just won't prove this right now. But yeah, you can do a lot of things with just a simple random walk. Now, I think everything so far is relatively clear. So we can right now just go directly into seeing what a Markov chain is. It's literally that easy, right? We haven't even learned that much about stochastic processes, and we can already define a Markov chain. That's how basic this thing is. So okay, what is a Markov chain? A Markov chain is just a stochastic process. What is stochastic process, right? We already know that a stochastic process is just a random variable that's indexed by time, right? So like this is a stochastic process, a random variable indexed by time that the effect of all the past has no effect on the future. So I will actually write down the definition of this thing. It's gonna be the definition, right? And if you don't understand the definition, that's perfectly fine. Okay, I had some problems with my internet, but let's keep going. We're defining what a Markov chain is. So we just keep writing this x of t. This is equal to the probability of xt plus 1 given x of t. Now, if you don't understand what this means, I'll explain in 1 second, right? So let's just go slowly. What is this thing? This is just a probability, right? If you have a dice, what is the probability of just getting a 3? That would be, well, 1/6, right? Because you have 6 like sides. Now, what is this thing right here? Well, this funny little bar is called the conditional probability, right? And this just means that what is the probability of something given that you already know something else. So, for example, let's just say we have two of these, each one with which 6 faces, and let's just say what is the probability, for example, of getting the first one to be 6? So I mean to be 3, given that we already know that the first one is 3, right? What is the probability of that? Well, we already know this one is a 1, so we only really care about the first one. So that would be 1/6. Now, this is not the case, for example, if we just said like, oh, what is the probability of like getting a 3 on either one of those, right? So let's just say we don't know the answer. Like we don't know which one the second dice is gonna get. Like what we got here because we haven't done it. So let's just say like, what is the probability of just getting a 3, right? In both of them. So like for both of them, what is the probability of just getting a 3? Well, that would be 11 over 36. Um, well, why? Because you're gonna have like 6 here, right? And then you're gonna have like 5 here because like um, you're gonna have like 3, 1, 3, 2, 3, 3, and then the same thing but the other way around. 3, 2, and then these ones are gonna be the same. So you only count them as one, so it's gonna be like 11. Um, okay. So that's basically what conditional probability means. It's just like given that we already know something, what is the probability in this case of something else? Conditional probability. So once we understood this, what is this equation saying? This is just saying that the probability of this thing, given that we already know all those other things, is the same. Is literally the same thing as saying what is the probability of our next state given our current state. Let me explain this further. Let's just say you're at this point. This is t, and then this is t plus one, right? This is our next state, and this is t equals one, and this is t equals 0. So let's just say we started here, and this is how where we're going. Now, what this is saying is that at this time step, if you're here and you're like, where am I going now? Right? Where am I going now? Well, what this is saying is if you already know what happened before, right? You already know what happened before. The probability for this next point is only dependent, it's the same thing as where you are right now. Now, let me give you an example. If, believe it or not, we've already constructed a Markov chain when we created this funny coin toss where you win 10 bucks or lose 10 bucks. That is already a Markov chain. Why? Well, let's say we start at 0, right? And then you win, and then you win again, and then you win again, and then you lose, and then you lose, and then you lose, and you keep losing. So let's say you're at this point, right? And then you're like, okay, what is this is t, this is t plus 1. Where am I going next? Right? I already know all these previous points. I already know what happened before. Where am I going next? So if you can just like zoom into this thing, boom. Where am I going next? Well, at this point, you're still tossing a coin, right? So like at this point, you only have two options: you either go up or you go down. That's it. So basically, what this is saying is like it doesn't matter what happened before. Like it literally doesn't matter because at this point, you can only go up or down, right? So if you're here, you can only go here or here. What happened before, how you got here is absolutely relevant. So you could have just like lost a lot and then won. You could just like gone up and down, up and down, up and down, and then here, you know, like it doesn't really matter how you got here. Oh, well, that's impossible. Um, yeah, it doesn't really matter how you got here. The point is that like once you are at this point, the next point is only dependent on where you are right now. How does it look mathematically? Like this. The probability for your next point, given that you already know everything, is the exact same thing as the probability for your next point, given that you only know your current point. So this is exactly this. That's it. That's it. That's a Markov chain. It's quite easy, honestly, and we've already constructed a Markov chain before, as I said. Now there is this very fun way of looking at Markov chains. That is a little bit different. Sorry, that's a little bit different. And this is when you have limited states. So this is when your random variable has what is called a finite set. So here, my random variable can only be like powers of 10, right? Like not powers of 10, but like multiples of 10. So this could be like 10, this could be like 20, and this could be like 30. It could also be like minus 10, minus 20, minus 30. But you could have a run where you like go to 1,000 and then you lose 1,000 and just go to 1,000. Um, so this is not quite finite. Now, when we do have a finite set of values, this basically looks like this. And I will first make up the scenario and then I'll show you why this is a Markov chain. So let's just say we have two states. This I will call GF and this I will call GG, right? And let's just say that this is just you having a girlfriend and this one is you being single, right? Just by yourself. Now, let's just say that you going from having a girlfriend to keeping her, there's a 50% chance that you keep your girlfriend. And then there's a 50% chance that you lose her. And then if you're single, there's a 50% chance that you stay single. And then there's a 50% chance that you actually get into a relationship. Now, right, if you think about it, this is just a Markov chain. Let's say you start by being single right here, and then you kind of just like toss a coin. It's 50-50. And then, whoa, you got a girlfriend. Nice. Right? Now you're here. Now you also toss a coin. And nice. You just kept her. Um, and the thing is, right, if we look at the history of this, right, let's just say that for time one, let's just say this is year one, you have a girlfriend, and then year two, you keep her, and then year three, you just toss the coin again and you keep her. Now, what would happen at point four? Well, it doesn't matter what happened before, right? This literally doesn't matter. You still have to toss a coin right now. So you're at this stage. You have to toss a coin. So this could be either you keep being on a relationship or you don't, with a 50% chance each. This is also a Markov chain, and this is a Markov chain that's really really useful, and you'll see why in an example in the future. So let's now just construct this to show something very beautiful about this type of Markov chains. Um, so let's just keep our previous example, right? Girlfriend, being single, and let's just put some like more realistic values. Let's just say that like keeping your girlfriend, that's relatively easy. That's pretty easy. But let's say the 80%. But there's always a chance, right? There's always a chance you might do something wrong. So let's say like a 20% chance of losing her. Now you're single. You're a good looking guy. So finding a girlfriend is gonna be like easy money. 60% chance. And then obviously like being single is like a 40% chance. So this is basically our states. Now, let's say once again you start by being single, and then you run the numbers, and then you say like, okay, I got a girlfriend, and then you just keep her, and then you keep her again, and you keep her again, and then just probability, you just lose her, and then you're single, and then you keep being single, and you keep being single, and you keep being single, and then you get a girlfriend again. My point is that there's something really really cool about this behavior. So we can represent this actually as a matrix, right? We can get here girlfriend, and then from GG to GG, right? We know this is 0.4. From GG to GF, that's 0.6. From GF to GG, that's 0.2, and this is 0.8. Now, if you apply this matrix to a vector, let's say this is GG and this is GF, and let's just say you start by being single. If you apply this a lot of times, right? You do this like a bunch of times as we did before, right? You just start here and then you just run it, and then you see what happens. There's a really really cool thing called the Perron-Frobenius theorem. Perron-Frobenius theorem that basically says if you keep doing this for a really long time, you will basically reach a steady state distribution. So basically, if you keep doing this for a really, 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 really long time, after a really long time, we can basically just kind of like get the probability of where you're gonna be at. Um, and this is really, really fun. Just something that I wanted to show really quickly, and we can just see it right here. So once again, staying single, 40% chance, getting a girlfriend, 60% chance, breaking up, that's a 20% chance, and then staying in a relationship, that's an 80% chance. And then if you run the numbers, well, you start by being single. This is the blue line, so no girlfriend. You start by being single, and then whatever happens in the middle. And then over like a lot of time steps, you basically reach this steady state. And this means that if I had to guess, right? If I had to guess 40 years in the future, are you gonna be in a relationship or not? Then I could tell. Well, you most likely will be in a relationship. Now, what happens if we move around these probabilities, right? Let's just say that like getting a girlfriend is so hard. Like this is extremely hard. Um, so getting a girlfriend is like 30%, and then let's just do 20 and 80. Super hard. Boom. If I had to guess, oh, that's a 50-50 actually. That would be literally tossing a coin. That's so funny. Okay, that would be literally tossing a coin. Now let's make this even harder, right? Let's say that you only have like a 10% chance. Yeah, you're absolutely cooked. That's it. Well, now if I had to guess, of course you would probably be single with a 60% chance of being single. Now, what if we made it even worse, right? Did you have like a 0.1% chance? Well, you're most likely being single. Yeah, it's like a 95% chance that you're like single after a lot of years. So that's a really, really cool way of expressing Markov chains. And it doesn't end there. Like this way of expressing Markov chains is actually the original Google algorithm. So if you've ever heard of this thing, this called page ranker, and they basically did this. But okay, I'm just gonna tell this story really quickly, right? But like they basically what they did is like they managed to get every single web page one, web page two, web page three, web page four, and they basically looked at where they were connected, right? where we're connected to each other.
And then they basically created um, their transition matrix, right? With all the probabilities of how likely it is for you to like move to this next web page. Um, they basically created all this thing, and then they reached this steady state. And in this final steady state, it basically like it returns a value what it's telling you which one right before if you looked at this distribution you could kind of say like okay it's most likely that I just will be single. In this thing you also like you can interpret this final matrix as being like oh what is the most important web page out of all the ones that I've seen before, right? Why? Because it is the most likely that I will be in after like a lot of time. So I mean I don't want to do the math because I don't think it's that necessary, but like this is called page ranker, right? And it's literally just like a Markov chain. It's so cool. And it uses this thing called the Perron-Frobenius theorem, which has to do with eigenstates and eigenvalues, which I don't really want to explain right now. So I'm just gonna like it doesn't really matter. My point is that this exists and this is really cool. Um, okay, so we're there already. We're into Markov chains, um, and now we know like okay, a Markov chain to gradually convert one distribution to another. Okay, now we're just gonna understand how the hell we're doing this. But at least we know what a Markov chain is right now. Now, very quickly before we keep going, I just want to emphasize the point of like what we just created, right? You're just able to use this new mathematical tool to like model all sort of like all kinds of things. This is so fun. So, for example, like I just got ChatGPT to create a new example, and it basically created this thing where we have basically before we had only two states, now we have five, um, and each one represents a different person, right? You have Tim, the gamer, Sarah, the cat whisperer, whatever, Bob, Debbie, and Danny. So like it's five different people, and then the transition matrix is basically like um, there's like this big room, and each one wants the room. So how likely are they to like trade the room with someone else, right? So like I don't know, Tim, he's too busy gaming, so he doesn't really care. Sarah has six cats, so she really wants it. Bob, yeah, he's just like using it for storage. Debbie loves yoga, so she really wants it. And then Danny, he doesn't really care as well. So if you run the probabilities for this, right? Who ends up in the big bedroom? Well, over time, if we know the probabilities of how likely someone is to give up the bedroom, over time we know that the person most likely to be there is going to be Debbie. Now this is kind of like a bit of a cringe example, but my point is that now you have the ability to create these um, new models for like really really cool stuff, right? So if you can think of a model that kind of like is represented like this, you can just run it and see what happens. You can just I don't know like calculate the percentages for your friends and be like okay you're this likely to be to like die alone or something. um so yeah, even though this is relatively basic, it's still very powerful, and as I said before, like page ranker is literally this. So it is extremely powerful, and yeah, that's just like a super quick side note. Okay, so really quickly, next up in stochastic processes. In a little bit, we're gonna go deeper into stochastic processes, and we're gonna see what is Brownian motion, what is this thing called quadratic variation, and then how do we get to Ito's calculus. Once again, these are all concepts that are related to what we already saw. This is just kind of like going deeper. So what we just saw are called discrete stochastic processes, and now we will look at continuous stochastic processes. So this is coming up. And then later, like way later in the second part of this video, we're gonna see SDEs, which are basically like stochastic differential equations, and these are based on Ito's calculus. So we're gonna see where they come from, how are they related to like normal differential equations, and why are they just like stochastic, I guess, right? This is very related. And at the end, we're just gonna see Fokker-Planck. There's a lot of things here, uh, but we will eventually cover these topics. And this is actually related to flow models, if you already know what that is. If you don't, that's okay. We'll see it when it's done. Anyways, so now we will actually take a look at the paper itself. So we're gonna take a look at the deep unsupervised learning using non-equilibrium thermodynamics. Finally, now we already know what a Markov chain is. We already know what where the name comes from, kind of. Um, so we'll finally just take a look at the actual paper. As I said before, it doesn't really matter to like explain each one of the equations itself. Um,
as much as it matters just to understand what is going on. So okay, let me just make myself smaller again. That's good. Okay, deep unsupervised learning using non-equilibrium thermodynamics. Now, if we go to the paper itself once again, as I said before, it kind of goes on why they do this, the inspiration from non-equilibrium statistical physics, um, and then how they learn to reverse diffusion process and restore structure in data, right? So there's a lot of stuff here, and they go into like learning this framework, diffusion process. Um, but to be honest, we kind of just care about this sentence right here. We build a generative markup chain which converts a simple known distribution, example a Gaussian, into a target data distribution. So this is what we care. Well, this entire thing. So let's just take this paragraph. We just take this paragraph and we understand this is literally like all the paper is doing. So our method uses markup chain to gradually. Okay, sick. Let's just kind of like unpack what this thing is saying, right? Use a markup chain to gradually convert one distribution to another. An idea used in non-equilibrium classical statistical mechanics. Statistical physics, whatever. So we already know what a markup chain is. We just saw this, right? We already know that a markup chain is just this thing that basically depends only on the previous step. So we know what that is already. Now, what does it mean to like convert a simple known distribution into a target data distribution? I think that's the first part that we need to truly understand. So first of all, what is a data distribution? Like what is our data distribution? Um, so this is really important, right? And this is like honestly like a really fundamental question that we just kind of get. We just have to get very, very clear. Okay, so when we talk about these things, we're basically talking in terms of images, right? That's what we wanna look at. So in terms of images, what does it mean to have like an original data distribution? Then again, this is like honest to God, just like a really good question. So what is an image? That's the first thing that we gotta ask ourselves. So an image is just a bunch of pixels, right? So you just have like this grid of pixels, and then each one of them they have like different values, and that's what makes an image. So we can just make this kind of like a little face, right? It's like a little smiley face or something. Um, Now normal images they have something that's called RGB values, right? So they have red, green, and blue. These RGB, and then they combine these values to make up an actual image. But for now, let's think about the black and white image. This is the one we have here. Now, this image is represented by values between like white and black. So we can say that these values are basically just between 0 and 1, right? So we would just say that x, this would be the name for each one of our images, will be between 0 and 1. So each one of these pixels would just be 0 and 1, or values between that. Now, and a complete image is kind of like really hard to understand. So like we will make this even simpler. We'll make this way simpler. We're just gonna look at an image that has 2 pixels, just 2 pixels, and you'll see how this translates to bigger images. This is just easier to visualize. So it's gonna be pixel 1, and this is gonna be pixel 2. Um, Once again, if this is 0, this is just gonna be white. If this is 1, this is gonna be black. And then if it's anything in the middle, it's just gonna be gray. That's kind of the idea, right? So this is only between 0 and 1. Now, as I said before, x1 can take values. So this is our x1. Can take values between 0 and this is 1. So this is white, and then you can move this is gray, and then you move, and this is black. Now the other image, it can also take values between 0 and 1. We'll call this x2. This is 1. So this is basically the space in which both of our images live in. So what would it mean, for example, if you said that this is where we are at? Well, that would mean that x2, which is this pixel, is at 0.5, and it would mean that this pixel is at 0.5 as well. That would basically mean that if you are right here, that would mean that we have 2 gray pixels side by side. So this would be 2 gray pixels from this point. Just make this another color. Now, what would happen if we were right here, for example, right? Let's move this. This would mean that both of our pixels are both black. And then anything in between. So if you were here, for example, that would mean that this one on the right is black, and then the other one is gray. So this would be another point, and so on. Now, what is a so this is our space. This is where our pixels live. And if you move around this space, if you move around this space, you basically move around the values for these pixels. So okay, that's fair enough. Now, what is a probability distribution, right? What is a distribution? Well, a probability distribution is just what is the probability of something at a certain point. So for example, let's just say that we have just one pixel, single pixel. Once again, this goes between 0 and 1. Now, what if we said that this pixel it just has to be black? So we just say that the probability of this pixel being black, it's here basically. Like it's just black, right? There's no other option basically. So it would be kind of like this. Now, what if we say that okay, this is kind of like blackish? So the probability of this pixel being black is kind of like it's like a blackish, right? It's close to being black. It's not necessarily black. So this would be our probability. Now, what if we say that this is kind of grayish? We would say this is our probability. So the probability of finding this pixel, so if this pixel was kind of grayish, right, we would say that, okay, it's kind of like around here. Okay, so what would happen then if we have two pixels now? Well, now our probability goes like this. So we have one pixel here, second pixel here, and then we just plot on this new axis. What is the value for the probability? So if we said, for example, that, okay, our pixels are generally just white. So the probability of finding a pixel that is white is very, very high compared to finding a pixel that is black. So basically this would be the probability. This would be x1, which is the first pixel. This is the second pixel. So the probability is really, really high when they're white. Where are they white? Right here. So whitish is kind of like all this section. Then this is kind of grayish. And then we would say that this is kind of blackish. So if we say that our probability is basically white, this would mean that for these values, the probability will be really high. And then for these values, it would be pretty low. And then for these values, it would be like close to 0. So our probability function would kind of look like this. This is 3D, mind you. So this is, yeah, maybe not that pretty. But hopefully you can, maybe we delete these things, would make it better. We don't want to delete that one. Perfect. This is a probability distribution. So when people say, oh, the original data distribution, this is what we're looking at. Now, of course, we're not looking at just 2 pixels. We're looking at like a bunch of pixels, right? Like 512 by 512, or like 1024 to 1024. So just like a lot of like millions of pixels. That's why most images come in the range of megapixels, because that's like a million pixels at least. So if you think about it, what would be a probability distribution for like an image that is 1 megabyte big? Well, this would be 1 million pixels, which is basically impossible to graph. So that's what we're using this data distribution with just 2 pixels, because I think that's like the easiest example we can think of. Now, we have our data. So for the data that I showed here, we just said that, okay, most of them are kind of white. Like most of them are just white. Not all of them, maybe. There's some of them that are gray. But basically we have not a single one that is black. So this would be our data. So of course, if the distribution for this data, right, it would be like, okay, white is very likely. So probability for white is very high. Now, if we extend this same idea to multiple dimensions, aka multiple pixels, we can think of each one of these as a dimension. So this was 1 dimension, and then this is 2 dimensions. So we can just think about these pixels as dimensions. If we take a look at this one, for example, this is like a 5 by 5, I think, 2, 5. So this would be 25 pixels. So this would be, I mean, it's impossible to graph, but let's just imagine, yeah, like 25 dimensions. Something horrible. And then for each one of these dimensions, we have a value. um, for the probability. Now, this value would be very high where we have data already. So where we have like little faces, for example, where we have like a, if we make another image with like a house, that you can imagine this is kind of like the image on top. Um, the, those sections where these pixels have that exact values, as we said before, this is just the white ones because the white ones were the ones in our data. Now these ones is way more complicated. There's like a lot of pixels, and some of them are black, some of them are white. So like some might be different if you change the image. Um, but it's essentially the same thing. So it's essentially just for these values of each one of these pixels, we just have a dimension, and then for certain images that we have in our data, we basically get the probability. Now, once again, if you look at like a real example of an actual image, um, that would be just something extremely high. Like let's just take a look at. Okay, so this is Avogado. This is the image we're taking a look at. Now this is a black and white image, so you can already see that like it kind of matches our previous ideas. Now we have a lot of pixels in here, a lot of pixels. So you can imagine if we had a bunch of images of people, um, then our data distribution, which is like really really hard to visualize, would kind of be like we've had like a bunch of pixels where the pixels kind of like make a face. That would be a really high value for the probability. So okay, I think that makes sense so far. Then again, for like really complicated images, it's kind of hard to see. But I think if you just look at this 2 pixel example, this just makes it way better. Um, so whenever people are saying in this paper, where they say they convert our known distribution, which is a Gaussian, into a target data distribution, this is basically what they mean. And this is basically what the distribution of images means. Just to be really really pedantic on what it is, on what this is saying, let's just do a different one. For I really have to fix that. Um, let's just do a different one basically for like now black pixels. So once again, we just have these things x1, x2, the probability, and then let's just say that we have like most of them being black pixels. This one is gray, but most of them are black. Something like this. Now, what would be a data distribution for this? Well, most of them black, so blacks are going to be really high, and then some of them are gray, so it's going to be low, and then the other ones are just very 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 low. So it kind of looks like this. And so these are a data distribution now. So once again, whenever this paper says, or any paper really, whenever they say our target data distribution, this is exactly what they're talking about. Now, not for 2 pixels, of course, but like for a lot of pixels. Basically, when you get to this point. Once again, this is kind of like really really hard to visualize, and I like to think of data distributions and diffusion models kind of just like as guides, right? If you have like this multi-dimensional space where like the combination of pixels is just enormous. It's huge. You have so many combinations, so many pixels. All of them can take like different values. So like most of these combinations are just useless. Most of these combinations are just noise. Um, but these models and when you try to traverse this data distribution, it's kind of just like guiding them, right? About around all this noise on this sea of noise. So okay, we now know what the data distribution is. Nice. Now, what is a known data distribution? What does this mean? Well, you probably know what a Gaussian is. Um, maybe it would be worth it to just know where this comes from a little bit. Um, so you probably like you know what happens when you multiply multiple numbers together. This is just this number times this number, this number times this number, this number times this number. This is called an exponential. So instead of doing this thing, you can just go like this, and this is just once again an exponential. Um, now that would just be like doubling the previous number as before. Now if we did this for a really really long time, so let's just say this is 0, and then this is 1, and this is 2, and then this is 3. This is how it would look like. So y equals, this is how it would look like. And then once again, like if you were at 1, d would be 2 to the 1. And then if you were at like 2, that would be 4, and so on. So this is our um, this how our function looks like. Now, what would happen, for example, if you all of a sudden made this squared? So before we had values that went from like -1, 0, 1, etc. Now, once we square these things, basically we get rid of the negative values. So all these values, they now become, well, positive. They're also squared, but most importantly, they're positive. Um, so before, if we had this thing, now we have an even sharper line on the positives, and then we also have the sharp line on the negatives because they're mirrored. -2 squared is the same thing as 2 squared. So now they're mirrored. So now we get this function. Now what happens if you make this thing negative now? And we can just see it. So what happens if we make this positive? Well, we get this thing, as I said before. And then what happens if we make this thing negative? Well, all of a sudden we get like this squished up thing, which might already look like something. And what you're essentially doing is, as before, you're just making these values negative. So you're just making like every single value negative. Um, so we go from here to here. Now, believe it or not, this is the same thing as the Gaussian distribution. So I don't really remember the Gaussian distribution formula, like just out of my, just, just like a one shot. I basically just remember this thing, because as you might already know, E is just a number. So E is just a number. It's a very special number, and it's a very special thing in mathematics. It's not only a number, but it's also like a function, and it's a lot of stuff in mathematics. But like, if we did this thing, this is the same idea basically. If you just change the number, for example, like we could do, instead of 2, we could just do pi. Oops. So we could just do pi to the minus square, and we would get a data distribution. We could do 3, and we'd get a data distribution. Of course, we choose E because it has very nice properties. Um, but what I'm trying to say is that in principle, this is just a number, right? This is really not the way that you learn this in class, but this is just a way I remember things. Which I find it way easier because it makes sense, right? To go from like basic, um, to go from like basically just multiplying a number by itself and then just going like, okay, what happens if this x, I just make it squared, and then what happens if I make that square negative? And this is what we get basically. So a Gaussian distribution looks like this. Now, a Gaussian distribution has a lot of very nice properties. Um, for example, you can start defining different characteristics of this function. Once again, if you look at the formula for this, so if you look at Gaussian distribution, you will see that it's this thing. This kind of looks disgusting if you don't know, um, if you've never seen it before. But I think once we've made the previous example, like it kind of just makes sense. So this is basically what we said before, just with a constant at the beginning. So this we can just call it a constant, C, and this is also just kind of like a constant. I mean, this is a constant, D, for example, and this is just a value that moves the thing around. And once again, we can just go see it. We can just go see it. We can put a constant right here, call it C. And we can just move this thing around. Um, then we can get another constant over here, and then we can just call it D. What happens if we move around this constant? Well, that kind of like squish it. Okay, cool. And then what happens if we put something minus, so a, say, well, this just moves around distribution. So once you know the fundamental thing of like how this thing comes from, just by the formula itself, we're not really talking about any characteristic of the Gaussian function, but just by the formula itself, right? It comes from exponentials, and these things, even though they might look kind of like scary, like where does, like what is that, right? Well, it's really not that hard. Um, So yeah, that's just the way you remember this distribution, the formula list. Now there's a lot of characteristics about this distribution, about this equation itself. Most notably, that you can basically use this thing. It's called the standard deviation. Now, what is the standard deviation? It's basically just how far apart this thing is. So if the standard deviation is really really high, that just means that it's like really fat, and if it's not, then that means it's really slim. So that's what the standard deviation is saying. Um, if you want to know where the standard deviation comes from, it comes from something in probability theory called um, like moments. This is honestly really really cool. I really like this thing. Um, so okay, we're gonna explain this super quickly. I really enjoy this. So what is distance? Let's just put one. What is distance? What does it mean for something to be kind of like far apart? Well, we usually call distance um, how far away in units something is from the origin. So if we call this the origin, let's just say this is 0. How far away from 0 something is, we would say that is the distance. So this would be the distance, 5. Now, this is kind of arbitrary if you think about it. What if we just said that, we don't want it to be from 0, we just want it to be from 1? Well, that would be a different distance. That would be just 4. So yeah, this is basically just how far away something is from 0. So this is just x, in this case minus 0. Um, and then in this case, it would be x minus whatever point you want it to be around. Of course, we're making everything from the origin. So this is 0 from the origin, and this is a from the origin, and then the other one is 5 from the origin. So at the end, we get 4. Um, but this is just one way of measuring distance. So you would say, if you wanted to know how far away different points were from each other, you would have this line, and you would get like, okay, this is 0, and then we have a point here, a point here, a point here, and then a point here. And then you would say like, okay, what is the average? Like, what is the distance of all these points with respect to the origin? Well, for this, you would just add up all the numbers. Once again, this is just adding up. So you would just add up where all these numbers are. So this would be x1, this would be x2, this would be x3, this would be x4. And then you would just divide this by the amount of numbers that there are. So you just do like 1 plus like 3, that's 4, plus like 5, that's 9, plus like, I don't know, 10, that's like 19 over 4. So yeah, that's basically what you, this is the distance, kind of like the average in this case, but it's really the distance for all the points away from the origin. So this would be, I don't know, something over here. Now, then again, we just said that this is kind of arbitrary. So you could just make this different. What if we made that distance squared? So once again, this is what we're doing. So what if instead of just taking the distance from the origin, we just made the distance squared? What would happen then? Well, if we make the distance squared, then that would mean that this is the x1, x2, x3, and x4. And this distance would just be squared. Now this distance would now be squared. Now this distance that would be squared. So we're basically just squaring the distances. Now, what would this change? Let's say our origin is right here. Before, we were just taking the distances and then just looking at the values. So if we had points all the way over here, then the average, as we defined it before, would be right in the middle. But now, we just defined a new sort of distance. And this new distance is what we had before, but squared. So before we had this negative distance, that now it's not negative, it's actually positive. So this goes over here. So since these points are symmetric, then we would have like, the first one would be here. Then the second one, just it's here. And then the previous one, it used to be over here, but now it's squared. So it's not negative anymore. Now it goes over here. And then this last one, it also used to be all the way over here, but now it's squared. So it's squared and positive. So this should be the same. So now what we're basically doing is just determining how far away something is without, you don't really care anymore if it's going to the left or to the right of the origin. Now, what if we made those points closer to each other? If we have the origin here, now what if we made those points closer to each other? So this is 0, and these are the points. Well, all of a sudden, our distances, so let's just say this is the square distance of the first, and this is the square distance of the second, the square distance of the first, and this is the square distance of the second. Now, our distances are way smaller because this thing is way closer, right? The same thing would happen if you just made the other case. What if you just made everything really, really far away? What if you just make a point all the way over here and a point all the way? Let's just say that we just define a point here. Sorry, we just define a point here. This would be like x1, this would be x2. Now, once again, if you just get the squared values, this would be here, and then this would be here, but it's squared, so just say it's this. So this is just like a general kind of like distance from the center. It doesn't really matter if it's going to the left or if it's going to the right, as opposed to the other one. This is basically the concept behind the sigma or the standard deviation. So this thing right here, the sigma, the standard deviation, basically comes from this principle. You could make this even further. You could take this even further. You could now say, well, the actual formula is not against 0, but the actual formula is like this, and this is just what we had before, the average. And if you think about it, this is just moving with respect to what are we doing the distancing. Now you can take this one step further and be like, okay, what happens then if you have this? Well, we can just look at it. You have an origin, and then you have different points, and then you just go like, okay, what is this thing saying? And if you make it cubed, now that just makes this doesn't remove the sign anymore. So it just makes any point just cubed. So now for this one, for example, it would be the same thing. This should be like really big. Well, anyways, this should be like really, really big. Now, what happens in this case if you now have a lot of points here and then just one point here? Well, since these points are getting cubed, these values would just get extremely high, and these values would be not particularly high because it's just cubed. So the values for the right would be extremely, extremely high, and then the values for the left won't really be that high. So what this thing is basically telling you is just where do you have your highest concentration of values? Is it on the left, or is it on the right? I said that the opposite, but is it on the left or is it on the right? This is what this thing is telling you, and this is called the skewness. Skewness. I think that's how you pronounce it. Skewness. Just check it very quick. Once again, this is what you have to think about. Like fundamentally, like it's useless to remember those formulas. Fundamentally, you can just look at this and be like, okay, this is just distances. So if they tell you in school like, oh, you know, the mean of the distribution, if they tell you in school like, oh, this is standard deviation or this is skewness, that's exactly what it is. Like it's just distances from the origin or from some different point. Okay, so that's basically like a really quick intro into Gaussian distribution. What is the actual data target distribution? So this is our image distribution. Now we can actually start thinking about what this thing is saying, because we kind of know already what our data distribution is. So target data distribution, we already know what this is, and we also know what a known distribution is. So there's different ones, but really you almost always work with Gaussians. So okay, now let's go into the actual paper. Okay, now let's look at the actual magic behind the paper. As I said before, this basically all comes down to like this single paragraph right here. So let's just go through it, right? It basically says our method uses a Markov chain to gradually convert one distribution to another. An idea using non-equilibrium statistical physics. And then we build a generative Markov chain, which converts a simple known distribution, a Gaussian, into a target data distribution using a diffusion process. Okay, so this is like literally all the paper. Now, let's just basically summarize what we just read here. This is saying we have a data distribution, and then we convert this data into a Gaussian. And then we go all the way back. Now, to convert this data, we basically use a microchain. Then again, we're literally, and then to go from here to here, we use a generative microchain. Once again, this is basically what the papers say. Our method uses a markup chain, okay, to gradually convert one distribution to another. So one distribution into another. Now we build a generative markup chain that basically converts a non-distribution into, in this case, a Gaussian, right, into our target data distribution. So this is exactly what's happening. Now, I just want you to know right here that we already know what all of these things are. Like, you already know what every single one of these concepts represent. So let's just go through them real quick. Let's just start at the data distribution. We already explained and we already went into what a data distribution is. How does it look like for multiple images, for just a single pixel, for like 2 pixels? How would it look for like a bunch of pixels? So you already know this. We already know what a data distribution is. Okay. Now, oops. You also know what a markup chain is. So like, we already know what a markup chain is. So once again, let's just go real quick. Let's just go see what a markup chain is somewhere around here. Okay. So we define once again the markup chain as just the stochastic process where the next state depends exclusively on our current state. So if you remember, we basically made this example of like you toss a coin and then you win $10 or you lose $10. So basically, let's say that right now you're doing horribly and you own $100. Um, so right at this second, you toss a coin and you can either go to -90 or you can own more money to -110. But the point of a markup chain is like it doesn't really matter what happened before, right? You could have been winning all night and then you lost. You could have been losing all night and then you started winning. You could have been like, kind of close. Um, the point is that like for a markup chain, it doesn't matter. The entire history is just the next state will be exclusively defined by our current state. So where we are right now. Okay, so we already know what a markup chain is, and we already went through some examples and how you can look at markup chains and stuff. Now, so we know markup chain. This is also a markup chain. What makes it generative, we will see, but this is just a markup chain essentially. And now we also know what a Gaussian is. So we also know what a Gaussian is. Once again, let's just go back quick to what a Gaussian is. We basically define kind of like the intuition of exponentials, and then we said like, okay, yeah, we get to this equation. Now this equation has some certain parameters. It has a variance, and it has a mean. These parameters basically just define how the exponential function will behave, how the exponential distribution will behave. So for example, this is the mean around which this distribution is centered. And then we also have the variance, which will be basically defined before as this thing, which basically is just saying like how exactly this, right? How spread or how like contained spiky our distribution is. Um, so basically, instead of writing this entire equation, you usually just say that our Gaussian function or a normal, which are the same thing, is basically this funky n that has, well, two parameters, the mean and the variance. So this is kind of like a shorthand of writing the equation. So instead of writing the entire equation, you basically just go like, okay, this is um, my Gaussian function, my Gaussian distribution. So we usually do this. Now, once again, like don't get confused. This is literally just a representation of the actual equation. We just define it by the parameters because like it's the same thing. We're just moving around the parameters, which is basically what changes this equation, this distribution. Anyways, so okay, we already know what it's lagging. Okay, we already know what a data distribution is. We already know what a Gaussian is, and then we already know what a markup chain is. So we have all the components to actually like understand what this paper is doing. Now, how does it actually work? How does it actually achieve this? Well, let's just look at the simplest example. So like we will just look at the most basic example of just a single pixel. And you will see well, like this is way more powerful than you imagine. But let's just look at a simple example. Simplest example. Now, let's just say that our pixel, this is the pixel, this probability let's just say that for our pixel, the probability distribution looks something like this. What is it saying is basically like it's very, very close to like 1, somewhere around 1. So it's blackish. What does this mean? Is basically, as we defined before, that um, in our data set, we basically had like blackish colors. So maybe this was a bit grayish. It was grayer. You get the point. It's basically there's no probability here. This is extremely low because in our data set we basically had no white pixels. But most of them are black. So like this would be our probability distribution. Now, okay, what do we do? We have this. Now, how do we go here? Well, we basically define a markup chain that will get us from here to our Gaussian distribution. How do we do that? Well, let's say that this is time step 0. This is time step 0. Now we take one step forward in time. So we increase time step to time step 1. So this would be time step 1. Now, what we would do here is we will define a markup chain that is basically a normal distribution centered around the mean. And we will say for now that this is just um, a constant standard deviation. Now, this mean will actually be a sample from the original distribution. So once again, just do this super quickly. These are our original data distribution, and then we say that we'll sample here. Okay, now this, let's just put another color. This point will be the mean. So this will be the mean. And for now, let's just say that our standard deviation is just 1. So now what we do is we basically create a normal distribution that's centered around this point that we just sampled. So we just sample this point, and we create a normal distribution centered around this point. It's a little not very well centered. There we go. Scuff it. Okay, so this is our new distribution, and we just center around this point. Now what do? We just take another time step in time. So this would be p equals 2. And what do? We do the exact same thing. We have this distribution, and then we just sample. So let's say, what does it mean to sample? Is just to take a point out of the distribution. Of course, the points that are most likely are going to be these ones. And then, for example, getting a point from here, it's extremely unlikely because that's the definition of a distribution, right? Like this is the probability. So for example, let's say that we got very unlucky, and for this sample, we just get it somewhere around here, which is very unlucky, like a 1% or something. So we sample and we get this point. Now, once again, we define our markup chain as being centered around this point, and then you sum it. So what do we do? What do we do now? Well, for our next time step, we literally have this point, and then we draw another Gaussian. And then what do we do? Well, like you can probably imagine already like what is happening. So you will just go like this, and then you would just sample from here. Let's just say we get this point, and then our new distribution would be centered around this point. And then, I mean, I'm just gonna do it in the same drawing now, so it's easier. Let's just say that we sample from here now, and then we do this, and then let's just say we sample the next one from here, and then we do this, and then let's say that we sample the next one from here, and then we do this, and so on. Let's just sample. The point is that like if you keep doing this over a lot of time steps, we will basically reach a Gaussian. Now, this is not a coincidence. We actually define our markup chain in a very specific way so that it actually reaches the Gaussian, but in principle, it is the same idea conceptually. And now it's a bit different. So our markup chain doesn't really look like this because this wouldn't actually converge to a Gaussian, but it's basically doing the same thing. It's just a little bit different. We will see this in a second. Like in a second, we will see the equations. In a second, we will see the proofs. In a second, we will see like all the mathematics that are involved. Right now, I just want to give a conceptual example of like an idea of the intuition of how this is working. Um, Now, the actual markup chain is not this exactly, but the actual markup chain has a diffusion term. So once you understand this, basically, the actual markup chain has a diffusion term that basically goes like, okay, the mean 1 minus this diffusion term, comma, this diffusion term. This is just an identity matrix in case we're talking about multi-dimensions. In this case, which is one dimension, so we'll just leave it like that. So this is the actual This depends on the time step. This is the actual formula, and you will see why we created like this, and you will see the actual equations, and you will see all of this in a second. But like, my point is just that this is fundamentally what's happening, right? Now, why is this a markup chain? You might be asking, how is this a markup chain? Well, if you think about it, if we are here, or we are here rather, the next point, so like, where do we go from here? It's independent of what happened before. So like, we might be here because we sampled like 3 times already, and we got this point. Or we might be here literally on our second attempt, and then we get here. It doesn't matter, because from here, we basically draw our Gaussian, and then our next point depends only on this one. That's why this is a markup chain. So, okay, we have our data distribution. We define our markup chain, which is basically just sample, and then center a Gaussian there, and then sample, and then center a Gaussian there, and then sample and center a Gaussian. And then at the end, we said that basically this converges to a Gaussian. Then we said, of course, that like the actual, this wouldn't, because this would just like go around. But we said this markup chain that actually does converge into a Gaussian. Once again, I will explain in a second how do you actually prove, how do you know that this will converge? I will explain in a second. Right now, I'm trying to do the conceptual kind of like ideas. So okay, we're basically like, we end up at a Gaussian. So we end up at a Gaussian that is centered around 0. So we end up here, which is very good, because once again, if you look at this, simple non-distribution, well, this is just extremely simple. So this is the D time steps. This is an extremely simple non-distribution. So what we do right now is like, we are here. We already went from the distribution. We defined our markup chain, and then we get all the way to a Gaussian. Now, what does it mean to have a generative markup chain to get all the way back to the distribution? Well, believe it or not, it's basically the exact same thing as we just defined. Like, it's literally the exact same thing, but something extremely important. The machine learning model will now learn where to go. So what do I mean by this? We're here. We're here basically at this point. Now we go now in reverse. So t minus 1. So we were at 0, then at 1 and 2 and 3, and then we did some stuff here. So let's just say that like we ended up at t. I don't know, like, let's just say it's like 5 or something, and then this would be like going back. So what do? We are at this known distribution, Gaussian. What we do is basically the same thing as before. We basically sample. So let's just say we got this point, and now we define our Gaussian. But now this new mean will be given by a machine learning model, and now this new sigma will be given by a machine learning model as well. Now, what does this mean? This is such a cool and like such a beautiful idea. What this means is basically like, once you are, let's just say we're here. Now the machine learning model learns that we need to go to our data distribution. We need to go here. This is where we need to go. So if we are here, the machine learning model will tell you like, okay, you need to go right. So it will basically output. Let's say we're here. The machine learning model will tell you like, okay, just go to the right. So go here. So it will output a mean, and then it will also output a, a variance. And then we just construct our normal distribution based on this, right? So this is what we do. Now we moved to where the machine learning model told us, right? We took a step where it told us. So for example, let's just make this is t minus 2 now. Let's just say that right now we're in this distribution. Let's color it differently. We're in this distribution. Now this is a Gaussian. Horrible drawing, but this is a Gaussian. Now let's say we got extremely unlucky. And for this Gaussian, we basically get a point all the way here. We got extremely unlucky. So this all the way here. So in our new time step, we would be here, here. Now remember that our actual data is at 1. Our actual data, like our pixels, are 1. So we actually need to go, we want to go here. So now we passed it. Before we were kind of close. Now we passed it. So now, with other machine learning models, we're here. So another learning model goes like, okay, let me give you a new mean and a new variance, and you need to move now to the left because that's where our data is. So it goes like, okay, just move here. Let me just put this into like this to this color, and it just goes like, okay, now go now go here, and then let's just say that we're kind of close. So maybe just go like this. So this is what the it's like. Okay, just you can move around how wide you want this thing to be. So this is like this is so cool. You're basically learning the steps to go back. You're basically going like, okay, this is our data distribution. You go do, and then you arrive to a known Gaussian distribution, and then you go like, okay, how do I go from here to where I was before to like our data distribution? And then you just tell a machine learning model to learn where it should go, like in which direction should I take a step. Well, the machine learning model is going to tell you that. Um, and it will output about the mean of where you need to center this Gaussian, and it will also output how wide this thing has to be. So, for example, let's just say another time step. Um, let's just say we're basically there. So this is one. This is where we are supposed to be close to, and this is our new time step. So the machine learning model will tell you like, okay, you're basically there, buddy. Like this is one. This is where we are right now, and this goes like, okay, just you know what, just take a tiny step, and then you just make this like this, because we're basically already there. We're basically already there. So it just goes like, okay, just sample like there. And once again, this is just like this. Now, as you can see, like we basically transformed this simple known distribution and we went back with the machine learning model into our previous, like into our target data distribution. This is so sick, right? It's so cool. Um, I know this is for 1D, and I will explain a second how this works for like other dimensions and stuff. But like this is exactly what is happening. We will see also the equations in just a second. But like I just want the conceptual thing to be very clear of like this is what is happening. Like the machine learning model is learning this. When you hear about diffusion, there's now flow matching and stuff. But like when you hear about classical diffusion, the machine learning model is literally just a bunch of neurons that tell you a mean and a variance. Now some caveats right here. In most machine learning models, you don't actually learn the variance, so they usually just learn the mean. So this is just a constant, usually. It's just a constant. You usually only learn the mean, so you don't really learn this. But I mean, there are experiments of people learning both, and like you can move them around. But like my point is that the machine learning model is literally just a bunch of neurons that go like, okay, where are you right now? Oh, you're here. Okay, I know that you have to go like to this other point, which is where our data actually is. So it's kind of, I mean, I think it's very beautiful and like such an interesting idea. This is basically like going um, like you get into like a forest, and then like the door is here, and you're kind of lost. It's extremely dark, and then you like move around, and you're like randomly, and then you're like, damn. And there's like, okay, the machine learning model tell me where to go, right? So like, uh, let's just say this is our random forest, and then you have a door here, and then you went out the door, and then you went, ooh, right? And then like you're like, how do I go back? And then you're like, okay, machine learning model, and the machine learning model will like, okay, go here, take a big step here, and then you take a big step here, and then you're like, okay, take a medium step here, okay, take a medium step here. And like, okay, you're very close, you're very close, you're very close. Like, take a tiny step here, okay, and now take a tiny step here, and then you're closer. This is basically what this machine learning model is doing. It's just basically navigating to, um, like, yeah, through all this like chaos, and then finding a way back into our actual data. Now, um, this is of course not uh, like this is the simplest case. Of course, this is as we said before with our data distribution. Normally, we don't have just a single pixel. We actually have like millions of pixels, or maybe not millions, but we have a lot of pixels. We have a lot of dimensions. So normally, this actually works for not only the single pixel, but it usually works. For example, if we go back to our example to what we had before of 2 pixels, then most of them being around black. So this would be our 2D data distribution essentially. you could like it's basically the exact same thing. It's basically the exact same idea. So we just sample from here. You say we get this, and we can see this as a vector. So let's just say this is somewhere like around 0.8 and 0.7. Okay. So then let me move this a little bit. So then we take a time step. So time step. This is t equals 0. This is 0. This is 1 now. And then what we do is for this, we use this value as the mean. We use this value as the mean. So let's just draw it. 0.8 is, I don't know, somewhere around here. And then 0.7 is, yeah, somewhere around here. And then we just create our Gaussians. And then we sample from here. So let's say for the first one, we got extremely lucky and we went all the way here. And then for the second one, it's just like normal. So we got a point very close to it. So our new uh, vector would actually be for the first one, we got weirdly unlucky. And then for the second one, well, it's basically like super close to it. And then you do this iteratively a bunch of times, like a lot of times. So you keep doing this, you keep doing this, you keep doing this, you keep doing this, you keep doing this until at the end, you will basically reach our Gaussian. So this is the idea. And then, I mean, for two dimensions, it works the same way. Like, how do you go back? Well, exactly the same. You just, you're like, okay, diffusion, I'm right here. Where should I go? And the diffusion model tells you like, oh, the diffusion model tells you like, okay, you have to move here. So like, okay, we move here. Whoop. And then you're like, okay, now where should I go? It's like, okay, you need to move here. Like, okay, I move here. Where should I go? And then, like you keep sampling. Um, you keep sampling, like you choose to distribute, like you get a distribution out of the model. Well, you get a mean out of the model. Then you create a distribution around that, and then you sample, and then you use that as the next step. You keep doing that until you're basically there. Now, you just have to imagine this into like a bunch of dimensions. Like this is for an actual image, so this is a bunch of dimensions. But I just want to like let it be clear that this is basically like this is exactly what is happening. We're basically noising each pixel, um, and this is actually something like that you can mathematically prove. That this example that I did, that you basically went like, oh, they just do each pixel independently. You can mathematically prove, and we might do this later if we have time. But like, this is exactly what it's doing. So this first part is actually called the forward process, and then the second part is called the backwards process. Process, and like this is exactly what's happening. So I just want the intuition and like the idea behind this to be super super clear. Because yeah, it's just going from our data distribution using a markup chain, and then going to a Gaussian, and then using another markup chain that the machine learning model gives the parameters to, and then you go back. It's really really cool, and it's such a cool idea. Now I feel like we need to actually see it, like you might be like, okay, I kind of get that, but like how does it actually work in practice? So, like if we go to the actual paper, like before this might all have seemed like very daunting math, but let's just look at this. So let's just first look at this section right here. um Let me get this here. So this is the forward trajectory, and we will look at the equations. Okay. uh this thing, and then let's also grab this other equation, which is also very important. You will see why in a second. I will explain this. Oh, I didn't grab this. I didn't grab it. There we go. Okay. So if we look at this, which is the very daunting math, like out of this entire paper, this is the very daunting, very complicated. You're like, wow, that's kind of hard. Um, Now let's just take a look at what it is exactly. Once again, let's just read. So we label the data distribution as Q of x0. Then the data distribution is gradually converted into a well-behaved, analytically tractable distribution, pi, by repeat application of a Markov distribution curve. So okay, just don't get confused here. This is like not that deep. We're basically saying like, okay, we convert this into a analytically tractable distribution, pi. So basically, pi is just a Gaussian. Pi is just a Gaussian. And now, by the repeated application of a Markov diffusion kernel, for pi. Now, you might be like, that looks so like so hard, like so weird. Well, it's really not. Like this is just a placeholder. This is like a mathematical placeholder for what we just said before. For this right here. Now, why is this the case? Well, it actually happens that we can define pi as a Gaussian. So basically, this middle point would be a Gaussian, like our where we converge to. This would be a Gaussian. But we can also make this a binomial distribution or something different. Now, you don't have to worry about this because as far as I know, binomial is not actually used. So just Gaussian. But the point is that since pi can be either a Gaussian or it can be either a binomial distribution, you basically make this mathematical object to hold. Like it can be anyone, right? So it can be a diffusion kernel for pi, where pi can be a Gaussian or it can be something different. Now, for our case, pi is a Gaussian. So this t is just basically just a placeholder for our Markov chain that we defined before. Amazing. So, that's kind of a lot easier. Um, and then we have a beta diffusion rate. Then again, this is what we defined before. I will explain what this is in a second, how it looks like intuitively. But once again, what this is doing is just basically like sample, get a point, draw a distribution there, sample, draw a distribution there, sample, draw a distribution there. So, okay, now we will actually ignore this equation for a bit. And we'll just look at the one that's under it. That's under it. What is this? Oh, we also already know this. This is just a Markov chain. Like this is the definition of a Markov chain. We've had this definition before. Like we just put it on the top. Now this is a little bit different because this is saying like uh, this is a little bit different, but like it's literally the same thing. It's just like if we have the one before, what is the one right now? Which is basically the same as saying like, okay, if we have the current one, what is the next one? It's literally the same thing. It's just a difference in notation. So this is just a Markov chain, which we know, amazing. And now what is this? Well, we literally just defined it before. This is our Markov process, like our Markov kernel, which is the Markov chain that we created up here. So this is just basically a definition of like, okay, this is a Markov chain, and this is the one that we're using. Once again, this T that looks kind of complicated, this is basically just um, like a placeholder for what you could actually use, because you can use a different this could be a Gaussian or it can be something different. So since that could be different things, we use a placeholder. Anyways, okay, now that's easy enough, I think. And then we go into like, okay, what is this forward trajectory? So you go like, okay, the forward trajectory corresponds to this the starting at the data and performing t time steps of diffusion. Okay, what is this thing right here? Well, this is just the data. We defined it before. Data distribution. We defined it before. So this is just the data. And now what is this section right here? Well, we know that this is the Markov process, the Markov kernel. So basically, this is just applying the thing over and over and over and over and over and over again. So basically, what this thing is telling you. Oh, by the way, like if in case you don't know, this is basically just a product. So if you have like x1, x2, x3, this is the same thing. It's like the product of like xi. So this is the same thing. So it's basically just applying. So this object right here, this mathematical object, basically just encodes the trajectory of going from the initial data and then applying this t times. So once again, let's just go back here. What this thing encodes is basically going from initial data and then applying the diffusion process t times. Boop, 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 3 times. T times, I mean, t. This is what this mathematical object holds. Um, Once again, you can just see it data, and then this is just a Markov process that you just apply. So this is just the forward trajectory or the object that holds what we defined before. Now this thing right here, it's actually kind of important, but this is a little bit trickier to explain. And this is basically the definition of a stationary distribution. What does that mean? It's just that basically
what I said before of like, how do you know that if you keep doing this, if you keep applying this kernel, that we will basically reach a stationary distribution, like this distribution? Well, how do you know? One of the ways that you know it's by this thing, which is basically like um, knowing that you get a stationary distribution. So what this thing is basically saying is like, if you have um, one state and then another one, that this is like your current, and this is your next one. This is basically you're saying like, if you apply, once again, what is this? This is just a diffusion kernel. If you apply it to the distribution, no matter where you um, no matter where you are. So this is what the integral is saying. So like you can start anywhere basically, or you can end anywhere. If you apply the diffusion, you basically will end up with the same distribution. So in other words, like this is just, I mean, you don't have to like understand this 100%, but this is just saying like, I don't know, if you're here and then you apply the diffusion kernel, um, you will basically like still be here. So this is what it's called like a stationary distribution. Now it is a bit tricky mathematically, but then again, like it's not super important in this case. It is important if you're actually creating this, um, but it's not super important if you're just learning it. And this is, I know that there's a lot of questions right now, especially regarding how do we know that we actually converge to this distribution? Can we prove that mathematically? And like, of course we can. This is one way, but we can also prove it by saying that it follows detailed balance, which is another thing that a Markov chain can do, or that it can follow. Let me just show you this. It's actually super pretty. Um, so there are certain. So okay, so this is a very pretty visualization of like what detailed balance is, and it's basically like you have to follow this equation up here. So basically, you can just prove it. You can put in the values, and you can just prove it. Once again, there's also the definition of aperiodic. So aperiodic Markov chain is basically this thing. This looks really hard, but like I swear it's not hard. It's very pretty actually. Like it's kind of geometric and I don't know. I thought this was very pretty. Anyways, my point is like you can mathematically prove that like this thing will converge. I don't think it's necessary to do that right now, but you can do it. Um, okay, so we already unrolled most of these complicated math. Now let's look at the last section. So not the last section, but like this thing right here, the reverse trajectory. So let's look at the reverse trajectory. Uh, there we go. So we looked at the forward trajectory. Now let's look at the reverse trajectory. Well, this is just essentially the same thing. Now we define. Remember what pi is? Pi is our Gaussian. So we define this thing as our Gaussian. So like when you're at time step t, you're basically time step t. This is once again. Let's go up. Time step t. It's a Gaussian. Amazing. So this is basically like where we land at the end of the forward process. We end up with a Gaussian um, at SMT. And then we basically go like, okay, this is the Gaussian. We defined it before. And now what is this? Well, this is our reverse Markov chain. The thing that we basically defined here. Remember that we said that like, okay, we go from t and then we go from t minus 1 and t minus, and so on. This is our reverse Markov chain. So this t right here, once again, like if you look at this, it's just a Markov chain. This by definition, we defined this before when we explained Markov chains. It's just a Markov chain, and then this is a product, so it's applying it once and look all over again. So what is this thing? Well, same as this encoded basically the forward trajectories. This thing encodes represents the backwards trajectories. So it's going from here, and then it encodes these things. Okay, so you apply, and then you move, you apply, you move, you apply, you move, you apply, you move. Um, Now once again, like this is just the actual mathematics, but not like okay, how does it actually look like? You might be like, okay, those are some pretty equations, but like, what are the real ones? I think like that. Those are actually the real ones. That's it. So if we go down here, here, okay, you can see that here they define forward diffusion kernel and reverse diffusion kernel. And as you can see, they have a Gaussian and they have a binomial. So we only care about the Gaussian. And let me put this here. And now where are we? Amazing. So this is our actual diffusion kernels. And if we look at them, once again, this is once again the definition for Markov chain.
the definition of a Markov chain, Markov chain, Markov chain. And then what is this? Well, this is just some funny notation, and I'll explain the notation in a second. But this is just some funny notation for what we basically defined before. So in the first one, we're basically saying that you have a normal distribution that's based on the previous step. So this one, and then we have like a scale, and then we say that like this thing has a certain variance. This is exactly what we defined before. So this is just a scale. So once you sample from here, and then you get the next one, you basically scale it down by a little bit. And then this is a constant, so we define it here as 1, but it's just a constant. Now this constant actually changes with time, but like you can imagine here that this is 1, and this might be 0.9, and this might be like 0.8 or something, but I mean, essentially it's just a constant. So this is basically our forward diffusion Markov chain. And then what is our backward diffusion Markov chain? Well, if you look at this is just saying normal distribution where the mean is this thing. Now they don't actually use machine learning here necessarily. No, it's not. Uh, oops. They don't necessarily use machine learning. These are just like functions, because this is not like the actual implementation. Like they don't actually like tell you like, oh, you should use this machine learning thing, or like you should use neural network. They basically just go like, oh, just use a function of like this thing will basically tell you where to go. This could be a machine learning model, and it's, well, that's what it is. But in this paper, it's more mathematical, and this is like the approach that they took. So they basically just say like, okay, but we can basically think of this as these things. Now, this at the beginning is just some notation of saying that like these are the parameters. So these are the parameters of our normal distribution, and this is basically with like what are we talking about right now? Like the actual like, so this is the next step, right? So like the next step depends on this, and then the previous step depends on this. Once again, why? Because uh, here we're going forward, and here we're going back. So this is just a special notation, but like I mean, it might be a little bit confusing, but you can get used to it, and it's not that like complicated. It's okay. We like that's it. Um, that's literally it. Like this is the entire mathematics of the paper, and this is the entire like idea behind it. Um, Once again, the thing that has to be like the clearest, even in the mathematics was not necessarily super clear. The thing that has to be the clearest, and why I explained it like this without adding all these other variables, is that it has to be clear that you're basically going from a data distribution, and then you're just like sampling, 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 moving, and then you get to this. And then once you're there, you basically do this same thing. It's like sample, but like where you move now, it's defined by the neural network. So like you're like, okay, move here, move here, move here. Once again, this is kind of like if you're like lost in a forest, and then you're like, okay, this is super dark. Where should I move? And the machine learning model is like, okay, big step here. Okay, tiny step here. Okay, big step here. Okay, tiny step here. It's basically exact same thing. Um, Once again, for actual machine learning models, they usually don't predict the variance. They usually leave this as a constant. And even if we go a little bit further, they don't usually predict the mean. They usually predict the mean of the noise. But I mean, essentially, they're just predicting like you can predict anything you want here. Like the idea is this one. Like this is the idea. The idea is to have a Markov chain. The idea is to go from this to this distribution and then back. So this is basically the most important, and I feel like the most complicated thing to wrap your head around. Once you understand this, not only is normal diffusion easier, but also like more complicated stuff like flow matching and all these other models or like techniques are way easier. Okay. Okay, so now just to close out this paper, what I just did is I proved that adding noise to this multi-dimensional Gaussian is basically the same thing as adding it to every single one of the pixels, or like as a combination of multiple unidimensional Gaussians. Now, I don't think I'm gonna add this video. I'm just gonna put it on YouTube as like an extra video, because I mean, I don't think it's worth it. So, but basically, I just proved that you can do this. So you can watch that if you're interested. Um, and yeah, basically it's just independence, so each pixel gets noise as like a unidimensional Gaussian. Anyways, you can go watch that. And finally, I just wanted to basically wrap up this paper and basically go from what we said at the beginning. So at the beginning, we started saying that like
the idea of diffusion, all the way from the beginning, is like you go back in time. So you basically have this thing that basically, converts into something chaotic. So we had this example of coffee with like a flour that's made out of cream, and then it slowly with time it merges, and then you had like this magical box that takes you all the way back from the beginning. Now we just created that magical box. Like that's exactly what we just did. So basically, we just created this data distribution, the coffee, and then with the flour, and then it went to noise. So like it went to this combination with like now they're all mushed up, and then we had this magical box as our neural network that basically takes it and goes do and recreates the flour with the cream. Now, if you think like that's an esoteric example, if we go back to the paper and then we just look at what they actually did, you will realize that it's not not that esoteric. So it's actually not that far off from what is actually like, genuinely happening. So you can see, and this is the most important thing, right? We say that we start at zero and we have this. Then again, you can see this is a flour on coffee, and then it slowly merges. So like slowly the cream goes around and it merges with the coffee, and now we have like this mushy thing. Well, the network just learned how to turn that mushy coffee back into the actual um, flour. So we're literally going back in time, and we're learning how to compare. This is exactly the thing that we said at the beginning, and now you know how. Now you know how if you have like a flour in a coffee, you're basically applying diffusion on it, which is, you can think about every single one of these pixels, which is what we just proved, and then it's just moving around, right, in a Gaussian, and then just sampling. So at the end, you basically have like all these things that are like not related to each other anymore. And then we learn with a diffusion, with a machine learning model, we learn the process of like going back. So like you're here, and then you go boop 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 boop, boop, and then you go back. So it's exactly going back in time. It's basically the same thing as we did before. So now you know how it works, and now you can go into the paper and be like, okay, I understand the idea. Now, before we keep going, I just want to say that like we still don't know how to train these models. There's a lot of stuff that we still don't know, and if you go into the paper, there's a lot of stuff still that we haven't really covered. But I think, in my opinion, for this paper, this is the most relevant parts, and the actual training and the actual machine learning comes from a following paper. So we will take a look at that next.
Okay, now we'll take a look at the unit. The unit is one of the most fundamental and basic, common ideas in machine learning. It's almost legendary just how commonly it is used. And it's used absolutely everywhere. So I think it's very important for us to get a deep understanding of how it works and where does it come from. So I have divided this video into three parts. The first part, let me move myself out a little bit. The first part is just like a very short story, like a very short story time, just a quick timeline. Basically, just saying how did we get here. So I will explain just some machine learning history, which I think is not only interesting but actually very useful to understand how it works and how we got to these ideas, basically. Now, if you don't want to see that, if you don't want to see this machine learning history, you can just jump right into model architecture. You can see the model architecture and the laws. So, how do you actually train this model, and what is the model itself? So we'll take a look at this in the second part that you can just jump right into. And the third section is just the code. So I have created a couple of Google Colabs, and I've trained some units for different tasks. And you will be able to see, and we will go through the code, and you'll see what this is useful for, and how they work, how do you actually train them, and then you can move them around, right? Like all of this code is available to you. It's on a Google Colab, so you can move it around. Also, these notes, as I said before, these notes are available because this is my own platform, so I'm just gonna share this with you. Okay, amazing, good. So now, what is a unit? What is a unit? So a unit is a convolutional neural network for image segmentation, as it says right here. Um, the original unit was meant to do segmentation of medical images. What does that mean? Is like, okay, you have a microscope image, like this one, and then it's like, okay, out of here, what is background and what is a cell? So this is a cell, this is a cell, let's say this is a cell. And the idea is for the unit to be like, okay, I will give out a mask where black is just the background and then white is a cell. So as I said before, this is a cell, this is a cell, like this is what it outputs. This was the original kind of like goal of the unit. Okay, how did I actually achieve that? That's what we're gonna see. And how do you train it? That's what we're gonna see. Okay, amazing. So now we're gonna go into part one. Tiny story time, just super quick timeline. And this is just a short story of how we got to UNet. So first, we're gonna see something that's called UNet, which is the first convolutional neural network, and it was created by this guy that I mean a lot of you might probably know. His name is Jan LeCun. That's why he called it UNet. And he was the first, basically the first person to develop the the, the convolutional neural networks. Now the crazy thing is that this is this was developed in 1988. He was working at Bell Labs, which is like AT&T, which was created by the guy who invented telephones, like Graham Bell. So they had like a lot of money, and he was doing like a research, like research into these things. And basically, he created something that was trying to extract the digits out of handwritten images. So, I mean, I think this is pretty self-explanatory, but you basically get like, oh, this is a four, right? So you get a four, this is a one, this is a zero. And the idea was well to get this automatically. So that was what he did, and he implemented basically the idea of convolution and how to make a model learn these things. Um, so this, I mean, this is like the first convolutional neural networks. It begs the question of like, okay, what is convolution? I'm gonna explain that right now, and I just want to say that there's this beautiful video and like this very very good animation from this guy called Triple Gwen Brown, and he has like a really cool video which explains basically what is a convolution. So if you really don't know what a convolution is, I think it's definitely worth it to just go watch this first. Now we're gonna go through it again just because it's very important for us to have like a first principles basically understanding of what we're talking about. So we're gonna go through it again, but then again, if you wanna like learn a convolution with these beautiful animations, you can just go to this video right here. So okay, let's just put this on top. What is a convolution? Okay, a convolution is you basically have an image and then you have a kernel. And what you do is you slide that kernel around and then you multiply the values of your kernel by the values on the image. And then you add them up and then that's the value for your new pixel. So basically, here you can see a kernel. It has certain values. And then you multiply it against the values of the image. And then you add them up and those values create the new value for the other image. So as you see right here, it's basically just sliding it. Now we're gonna go through it again in case that wasn't particularly clear. But the video is amazing. So if you don't know what I'm talking about, I think it's definitely worth it. Just go take a look. Okay, so let's just go through the idea of convolution again. So you have an image. What is an image? An image is just a collection of pixels, like a grid of pixels. So this is a grid of pixels. Now we have something that is called a kernel. What is a kernel? Is it's just a collection of values, kind of like a little tiny matrix, or I mean, it can be size or whatever you want. And then it has values. And then what you do is you slide this kernel, you slide it, and then you multiply each one of the values. So for example, this would be the value from the image. You multiply it against this, you multiply it against this, and you multiply it against this. And then you do that for every single value in your kernel. And then at the end, you get the value for the new pixel. So multiply, add them up, and then you get the value. Now you might be asking a really important question is like, okay, why does that matter? And I got a very good example for you here. So before machine learning and before all these crazy models, people used to do computer vision with something more kind of like basic or fundamental, which was doing kernel convolution. So before all these crazy machine learning models, if you wanted, for example, like if you wanted to know where the edges are, and I mean this still works right now, but this is a really old technique. You would do something like Sobel, which is what you're looking at right here. So you basically have, okay, you have your arena image, and you have a kernel that looks exactly like this. And then once again, you multiply, um, you slide this kernel around the image, you slide it, you multiply the values of the image against the kernel, and then you would get an output. Now, if you're wondering why do we get this output, for this very specific kernel, it's basically saying like, okay, everything that's on this left side is going to be negative, and everything that's on the right side is going to be positive. So if we take a look at like super quickly at what the values would look like, um, let's say that we're going from dark to light. So we basically what we're saying is like, okay, we have dark on this side of the image, and then we have light on this side of the image. So when you multiply them together, the dark part will be negative. So what does it mean to be dark in an image? It's just that it's a zero. So zero is dark, and then bright is 255. So we're saying here is like, okay, zero. So this is zero multiplied by all the negative numbers is a zero. So we got a zero here.
and then the other side is a very positive value. So we have a positive value here, and multiplied by these numbers, this would be also a positive value. So at the end, when you add them all up, this would give out also a positive value. Now, for example, what happens when we have the opposite? What happens when we're going from light to dark in the image? So once again, this part would be negative. So what does it mean? This would be negative. So it would be very negative because it's like, okay, 255 times all these negative things. And then this side would be 0. So this would be 0 as well because like it's dark. So at the end, we will have a negative number. Now, since we cannot really have like negative values, this would basically also be a 0. So everything that's going from light to dark would be a 0. Everything that's going from dark to bright would be a positive number. So in this case, a white. Now we can take a look at the rest of the example. So what would happen, for example, if you had, oops, that's my bad. Okay, what would happen if you had the same thing on both sides? So what happens if you have bright and bright? What happens if you have black and black on both sides of the image? Well, since we're getting negatives here and then positives here, this would just cancel out. So at the end, you just get a 0. So this would be both a 0. Okay, so basically, what this does is just it takes everything that's going from dark to bright, and that's what it outputs. That's how it gets a white value at the end. So you can do this for a lot of different kernels, and you get different outputs. So in this case, it's called subtle X. Now, if you turn this kernel around, now it's not the now it's not the vertical edges. Now it's the horizontal edges. So I made also a very quick Jupyter notebook or like a Google Colab where you can just play around with the kernels and see what happens. So as I said before, this is the subtle X kernel, and now if you just move it around, um, you get the horizontal lines, and you get also like different things if you move around the kernel. So you can play around with that. I think it's very useful. It's okay. This is how you get. This is how a kernel learns. So in this case, the kernel is just you multiply the image times the kernel, and then or you convolute the image times the kernel, and what happens is you get these vertical edges. The idea of a convolutional neural network is to make the machine learning model learn this kernel. So the machine learning model will learn these values. So you can imagine at the beginning it will be like totally random, and then the machine learning model will be like, okay, I'll just learn the features that I need from the image. So in this case, like one kernel might be like the vertical edges, one kernel might be the horizontal edges, one kernel. So the idea is the machine learning model learns the kernel, and that's what Jan LeCun did in 1988. Okay, so that's really cool. I mean, first you know I worked UNet, and then comes the second one, which is called AlexNet, because this guy I won't pronounce his last name, but his name is Alex. I think he's Ukrainian. He has a very complicated last name. And he created something that's called the AlexNet, which is basically just like a scaled up version of LeNet. I mean, there's a couple distinctions there, um, but fundamentally it's not that different. It's just like a bigger version of LeNet. But this was extremely important at the time. It was extremely important at the time because it won. So it was trained on like this data set, which contained, if I'm not mistaken, like 1.5 million images, and it won. So basically, like you had to segmentate every image. So like, okay, in this image, where's a dog? And then it's like, okay, the dog's here. So it segmented this data set extremely well, or like by those standards, by the standards at the time, extremely well. And this basically revolutionized the field because people at the time were like, okay, we're doing like all these like computer vision things with like these funny like pieced up together algorithms or whatever. And then he just came in and he was like, okay, you know what? You can just do a machine learning model, then it's that it works extremely well. And yeah, and it basically beats every single other one of your algorithms. So what AlexNet did basically is just change it was like a paradigm shift in the way that like people were like, okay, we need to invest in machine learning now. So that's what AlexNet did, which is also very, very cool. Now, AlexNet is very deeply intertwined in the history of machine learning and of modern things. Because I mean, you might know him. His name is Ilya, and he's the co-founder of OpenAI. And they were both working. They both worked together on this paper, and they were both watched. I forgot the name, but like they both were watching their PhDs by George Clinton, which he's also sorry, not Geoffrey Clinton, and he's also extremely legendary because he's the guy who made Boltzmann machines. I think he worked in some of the backpropagation things. He's extremely legendary, one of the oldest people to like know that machine learning was going to be a thing. So he was his advisor. That's the word. He was his advisor. And so this is 2011.
Um, so almost 15 years ago, by the time I'm recording this video. Okay, now this guy also brought it. Pure cool that like there was no PyTorch or anything. He just spread it down. I think PyTorch is like 2017 or something. So, yeah, he just made it entirely on like C++, which is I don't know. It's kind of very impressive. You have to like code all your stuff from scratch basically at the time. And now we come to the unit. The unit is so the unit was released in 2015 by these guys right here. So this like Thomas, Philip, and Olaf. They're all like Germans, which is right here. And now the unit is one of the most, as I said before, one of the most basic things, or like one of the most fundamental building blocks of modern machine learning. And it came up, they came up with this idea in 2015, so almost 10 years ago, which I mean, it's relatively new for science standards, but like for machine learning, it's very old. So when we watch the model architecture and we go into how does it actually work, you might be like, okay, this is, I don't know, pretty fundamental. And the thing is like, it is very fundamental because it's relatively old machine learning standards. Um, but it's extremely significant. Extremely significant also just in the timeline and how it is related to, to all these other characters. So okay, that was a super quick, tiny story time. So once we're past this, we learned a little bit of what a convolution is and how does the kernel um, like work, does its magic. And we also said that a convolutional neural network is basically the machine learning model learning this kernel. So okay, now we go to part two. Part two is the model architecture. So if you go to the paper, they say a lot of stuff. The architecture consists of like a path. They go into the thing. This is the diagram that you see on the my explanation, my board, and then this is like some overlap, training. Now the thing is, I think everything that's useful from this paper, or like the most useful thing, is just to know these diagrams. So like know the model architecture, what is happening. Everything else, in my opinion, is not as important. So just getting to know and like understanding what this is doing very well, it's all that matters. So that's what we're gonna do. Okay, so model architecture. How does this work? We're gonna go through every single one of these little tiny diagrams, and I'll explain what they do. And as you see, most of them just repeat. So it's once you get a part of it, you will get the entire picture. So okay, at the beginning you have this thing that is an input image style. What does that mean? This is literally just an image. So let me just move this a little bit so that it's easier to explain. Um, Maybe I'll delete this. I'll delete this for now, and now I'll just move it down. Perfect. Okay. So input image style. What does this mean? This is like a literal image. So you have your image, and what does it say right here? So it says 572 572 times 572. So this is just the size of the image. This is just an image that is 572 by 572. And then this thing is just saying that there's one channel, which basically means it's just black and white. If you had three channels, that would be red, green, and blue. So that would be three channels. In this case, it's just one because it's black and white. So this is just a black and white image. So you get a black and white image. And then we go to the first section of this, which is the little arrow. What does this arrow mean? If we go down a little bit, this just says a convolution, 3 by 3, and a REL. What does it mean? Well, this is exactly what we looked at before. So before I said, okay, what is a convolution? You have a kernel, and then you slide that kernel through the image, and that's what creates these feature maps. That's what they're called. And then the machine learning model has to learn these kernels. Well, what you're saying right here is like, okay, we're gonna do a kernel that's a convolution. That's gonna be a 3 by 3, so just 9. That's exactly this one. It's gonna be a 3 by 3, and then we're gonna apply a ReLU activation function. And then we're gonna do this for n number of kernels. So once again, this is just a kernel that is 3 by 3. And then we will do this, in this case, 64 times. So we're going to do this 64 times. What does this mean? Once again, if we think about it, we said that a machine learning model will learn these kernels. So in this case, you have 9 weights. You have 9 things that have to be learned. And then we have 64 of those. So if we look at our model, and we will do this in the future when we get to the code, if we look at the model, we're supposed to have 9 times 64 parameters for this layer. That's so like 64, 192. That's 576 parameters. So when we look at their model and then we look at this first part, we should see that the model is trying to learn these 576 parameters, which is just these 3 by 3 kernels that are multiplied, or like that we have 64 of them. Okay, So what you do is right here, you just do convolution 3 by 3, 64 times. And then you do an activation function, which in this case is a ReLU. How does the ReLU look like? It's just a function that goes like this. So this is just an activation function. And then you do this. This is being done pixel-wise. So for each one of the pixels you're activating. So you're doing a convolution, then you're doing an activation function. What does this mean? Is like, okay, like after the convolution, let's say you get, well, as we said right here, in this example, we get a positive. So our positive would be somewhere around here, I don't know. And this would be the value for our activation function. But let's say that if we get a negative, it would be somewhere around here. So this would be 0. So it would be 0 for the negatives, and then for everything positive, it would be somewhere around here. Or like, it's basically just y equals x, so the same value. Okay, so once again, this is just the machine learning model trying to learn these feature maps. So it's trying to, like, you have an image, it learns the 64 kernels, and then you basically get these 64 outputs. So what you get is 64 feature maps, which is basically you get 64 of these, but the machine learning model learns these kernels so that they will all look different. So what is this in a diagram? Well, it's just this section, 64 of them. And then you do it again. So then you do exactly the same thing. So then you go like, okay, we're gonna do a 3 by 3 convolution times 64 times. And then, well, you get the feature maps again. So you just do this again. Now, if you look closely, you can see here that we're going down in. So you have 572 and then 570 and then 568. Why is that? Well, this is just how convolution works. So in order to explain this, we can just go into a convolution visualizer. Let's make the image a little bit bigger, and then let's make the kernel size a 3 by 3, exactly as an example. As you can see, what it does is like it slides the kernel around, slides. And the idea is that you then multiply each one of these values against our kernel, and then you add them up, and that would output this pixel for our output image. So this is what it's doing. Now, as you can already see, this value right here has no pixels around it. So basically, the image is starting at this pixel. So everything that's around this one. So this is more obvious if you move it around. As you can see, like everything that's on this row has nothing around it to compare it to, and everything that's on this one has also nothing around it to compare it. So we basically lose this section of the image when we do a convolution. We can solve this very simply by adding a padding. What is a padding? It's just adding some pixels around so that now we can, like this has something around it. Once again, this has something around it, so now we can actually get some meaningful information out of these pixels. And this would give like an input the same size as the output. But in this case, we're not using any padding, so that's what you get. That's what you lose these 2 pixels from the row and from the column. And then you lose the 2 pixels and then you lose them again. Okay, so that's what it's doing. As I said before, it's just a kernel. In this case, it's a 3 by 3 followed by an activation function, and then doing this n times, so as many times as you want. In this case, 64. Okay, so we got this section right here. So hopefully that was clear. And then we go into the second symbol, which is the second arrow. What is this arrow doing? This arrow is a max pull 2 by 2. What is a max pull 2 by 2? It's quite simple. As I said before, you had a kernel and then you multiplied each one of the kernels. What a max pull 2 by 2 is doing is you have a 2 by 2 kernel, or like it's not really a kernel. It's just you have a 2 by 2 grid, and then you slide this grid against the image, exactly as we did before, and then you just output the maximum value in that grid. So if we take a look at our convolution visualizer, let's just remove the padding and make this 2 by 2. So you basically go like, okay, 2 by 2 every single one of them, 2 by 2, 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 and then just give me the maximum value out of these 4, and that would be the next one. So that's what you're doing. It's literally just getting like, okay, this 2 by 2 little tiny matrix, you slide around, and then you get out the maximum value, and that's a max pull. So okay, like that's all that's doing. So what this effectively is doing is reducing the size in half. Because like before you had this bigger image and then you just extract the maximum values with a 2 by 2 kernel. So at the end you get an image that is half the size. So what you're doing right here is just, once again, getting the maximum values out of a 2 by 2 kernel. And then you just do the exact same thing again. So as I said before, you just do a convolution that's a 3 by 3 followed by a ReLU, a convolution that's 2 by 2 followed by a ReLU. And we can see right here how our our sizes of the images, or like of the feature maps, are also getting reduced in the same way as they did before. Okay, so this is exactly the same thing as in the beginning. So this is what's happening again. And then we also get another max pool, which effectively makes the halves the previous image, or like the previous feature map. And then we do this exact same thing again with the convolutions. As we can see, it's also going down 2 by 2. Um, and then we do another max pool, and then we do another convolution 3 by 3. And then you do another max pool. We'll ignore these arrows for a second. We'll take a look at them in a moment. And then you just do this exact same thing again. And as you can see, like it's it's always decreasing, because of what we said before, there's no padding. Okay, so now we get into something that's different now. Now, what is this up arrow doing? This up arrow doing is something that is an up convolution, a 2 by 2 up convolution. What is an up convolution? Well, let's just go back to our definition of what is a convolution. So a convolution is just, you have this image, and then you have this kernel that slides around the image, and then you multiply all these values of the image together, and then you get this, you add them up, and then you get this final pixel value back. What an up convolution, in this case a 2 by 2, is doing, is basically doing the opposite. So you go from a single pixel, so it's basically doing the opposite, from here to here. You have a single pixel. They just do it from this side. So you have a single pixel, and then you have a kernel. In this case, it's a 2 by 2. So it's a 2 by 2. And what it does is that the machine learning model is now learning this kernel. So it learns this kernel so that you multiply this pixel by each one of the values in this kernel. You multiply, you multiply, you multiply. And then these would be the values for a bigger image. So now with these values, you construct a bigger image. So there we go right there. So essentially, what you were doing before is going from like this bigger image, doing convolution, and then extracting the value for a single pixel. Now what you're doing is basically the opposite. You have a single pixel, and you have a kernel that's trying to know how the single pixel basically maps to this bigger thing. So it's kind of like the opposite, and that's why it's called an up convolution. It has some other names, but in this case, they call it a convolution. And it's a 2 by 2 just because this thing is a 2 by 2. So once again, what is this thing doing? Is just single pixel. The machine learning model learns a kernel, and then it multiplies the pixel towards each one of the values in that kernel, and then that's how you build um, a bigger feature map or a bigger image or whatever. So this arrow. Now, okay, so far so good, I think. Now, what is happening here? Now it seems to be two parts adding or being added, being concatenated here. And that's basically exactly what's happening. So at this section, we go from this to this. So we basically go from 1024, which was down here, to 512. But now this is 1024. Why? Because we're basically doing something that's called residual connections. What residual connections are is just, okay, just let's take the step what we had before. Let's take the step in the past, and then our step right now, and then just literally concatenate them together. Like, so you had the one that's before, exactly this one. So our output from this step, and then from our output from our new step, and then you just concatenate them together. That's all that's happening. This is called residual connections. And then again, it's literally just concatenating together the output from the past with the output from the present. So that's what we get. So out of here we had a 1024, and then we did our up convolution. So we had a 512, and then just added with the other 512, and then you get a 224 again. And then, well, we have just, oops, we have the exact same thing as we did before. So this is, once again, this is simply just convolution 3 by 3. And then we do the exact same thing. So we do an up convolution, which is what we described. And then once again, we get an output, this output, and then you concatenate it together with the previous step. Now there's something important here, and like you can see that there's like these dashed lines, and what do they mean? Well, here this has a dimension, or like a size of 104, while this size it's 136. So basically, this one is bigger than the other one. So what do you do is you just crop it. So this is basically like having this is the equivalent of having like two images, and just the other one is slightly smaller. So what do you do is, well, you just crop the other one to fit so that they can both be concatenated. So now we concatenated.
So that's what I'm doing. That's what you're doing, and this is called a center crop. Why? Because this is 136 and this is 104. So you want them to be the exact same dimension so that you can concatenate them together. So that's what these little tiny like dots are, are meant to describe. Okay, so you just add them together once again, convolution, 3 by 3, ReLU, what we described before, and then up convolution, what we described before as well. Um, and now you get to this point, so you do the exact same thing, you do the exact same thing, and then you do the exact same thing. And then once again, you can look at here, and then you can keep seeing that this goes down by 2 because of what we explained at the beginning. Okay, and now at the end, you just get this arrow. What does this arrow mean? Let's go back. This is just a convolution. That's a 1 by 1. What is a 1 by 1? Let's just go to our um, visualizer, a kernel size 1. Well, 1 by 1 is just, you have one output, one input, and a single weight, and then you multiply it against your inner image, and then you basically get an output image. So this is basically literally just a single weight multiplied by the input, and then that's how you get an output. So that's all that's happening. So it's a 1 by 1 convolution. It's like single weight. And what do we get at the end? We get this 388 by 388 with 2 channels. What does this mean? This just means that this would be the segmentation, right? So like in this case, this would be this segmentation. And what we're doing here, what the 2 means is that this has 2 classes. So you would basically get one, for example, like they just say, what are 2 classes? They just say cats and dogs. So we basically get like, okay, this is the segmentation mask for the cat, this is segmentation mask for the dog. So in this case, there would be nothing, like it would be all black on the cat, and it would be something on the dog. Maybe if you find an image where there's a dog and a cat, maybe you would see the cat being labeled on one and then the dog being labeled on the other. So that's the idea. That's the idea. In this case, we have 2 labels, 2 classes, and then you could of course make this even bigger, or you could make this even smaller with a binary mask. So for example, in this case, we have a single class. Like we just want to know what is background and what is a white cell. So it's a single class. It's called a binary class. Now in this case, for example, we would have a lot of classes. So okay, what is a sailboat? What is a sailing vessel? What is a watercraft? And you would have a channel for each one of these, and this is the output. So okay, we just went through the entire UNet architecture. What is it called a UNet? Well, it's just because this kind of looks like a U. So nice. That's all this thing is. So I think it was pretty clear. Once again, this will make a lot more sense once you actually implement it. And once you implement it in the code, you can see the dimensions change, and you can see, as I said before, each one of the parameters. So like here, we said that we would get 576 parameters, and you can see in the neural network if that's actually the case, which it will be. So okay, we just looked at the UNet architecture. Hopefully that was clear. And this is all it is. Now we will take a look at the loss. Okay, now we'll learn how to actually train these models. Specifically, we'll take a look at the loss function. Now, I think it's worth it to derive the loss function mathematically at least once. Especially this idea of like minimizing the negative log likelihood. It literally comes up like absolutely everywhere. So deriving this at least once gives you a very good intuition of how loss functions work in general. So yeah, we can derive the mathematics just once, and then afterwards you can forget about it if you want and just use PyTorch. But doing this at least once is extremely useful. So that's what we're gonna do today. Now let's just set up our scenario. So let's say we have an image, and in our image we have a dog. So we have a dog right here. And then let's say that in our image we also have a tree somewhere in the back. Okay, this is an image. Now we will do the simplest possible segmentation. What is that? It's just binary segmentation. Binary just means like 0 and 1. So we'll do binary segmentation where 0, well, 0 is just not a dog. So this is not a dog. And then 1, this is a dog. So 0 not a dog, 1 a dog. Simplest possible case. Now let's take a look at how our ground truth would look like. So our ground truth would basically look like 1, where we have a dog, and then 0 absolutely everywhere else. Because that's what we set up, right? Like this is our segmentation. This is either a dog or not a dog. That's it. So this is our ground truth looks like. Now we can take a look at the output of the model. So what is the output of our UNet? This is basically
what we get out here. So the output of the unit is basically a bunch of arbitrary values. So these values, they can be like negative, they can be like extremely positive, or anything in between. Now the problem with these values is that these values do not reflect a probability distribution. So like these are just arbitrary values. So what we do is we pass them through a sigmoid function. Sigmoid function. What is a sigmoid function? A sigmoid function is just something that looks like this. Something that looks like this. What is this doing? Well, if the value is like extremely negative, well, that would be a 0 after passing it to our sigma function. If the value is extremely positive, well, that would just be a 1. And anything in between will have like different values according to this function. So what this is essentially doing is turning our arbitrary values into something that we can interpret as a probability. Now this is called logits. And once we pass into a sigma function, then we have something that we can now compare against our ground truth. So let's say that after doing this, the model basically outputs something like this. And then just make this another color. And then everything else is just 0. What am I writing here in this horrible drawing is, okay, this is the model is very confident that this is a dog. These pixels are a dog. This, the model is not super confident, it's very uncertain. And here the model is very confident that these pixels are, once again, not a dog. So now we can take a look at an arbitrary pixel inside of our ground truth. So basically we just zoom in into an arbitrary pixel. Once again, as we said before, this can take basically the value of 0 or 1, because that's what we said at the beginning with the binary segmentation. So we will call any arbitrary, like an arbitrary pixel, we'll call it y. Once again, y can only be 0 and 1. And then we'll take a look at an arbitrary pixel inside of our prediction. So inside of our prediction, and we will call an arbitrary pixel y hat. What can y hat be? Well, if we take a look at, I don't know, let's say this pixel, y hat could be, let's say, 0.5. What does this mean? This just means that the model is 50% sure that there's a dog in there. So it's kind of uncertain. Now, if we take a look at, for example, this one, the model might be 80% sure. 80% sure that that's a dog. And then, I don't know, somewhere around here, it will be like, okay, the model is like 0.05. 0.05%, so like 5%. I mean, 0.05, that's the output of the model, so 5% that it's sure that it's a dog. So basically, like, okay, this is not a dog, essentially. So now that we have these two labels and then we set up our scenario, we can now take a look at, okay, what is the probability that the model will output the correct class, right? So like, what is the probability that this would be a dog? So we said before, well, the probability that this is a dog is just y hat, because we set up at the beginning, right? Like that's what we said. 80% probability this is a dog. Now, conversely, the equivalent probability is also like, okay, what is the probability that this is not a dog? Well, if you think about it, this is just 1 minus y hat. Well, why? Because here it has an 80% probability that this is a dog, or equivalently, this is a 20% probability that this is background or not a dog. Is this clear? So this is like a 5% probability that this is a dog, or equivalently, this is a 95% probability that this is not a dog. So not dog, and this is a dog. So that's exactly what we're saying here. Y hat and 1 minus y hat. Now in probability, we would call this, what is the probability of y hat, given the fact that we know that this is 1, that this is a dog. So then again, what is it saying is like, okay, if we know this is a dog, then the probability of the model outputting the right label, it will be just y hat. And then this would be equivalent of saying, what is the probability of the model prediction, given that we know that this is a background pixel. And that would be 1 minus y hat. Once again, because we set it up like it's equivalent probabilities. So now we can basically combine these two ideas, and we combine these two probabilities into a likelihood. So this is what we would call a likelihood. This is likelihood, and what is the likelihood is doing is basically like, okay, what is the probability of y hat given any of our labels, right? And we just combine these two ideas, and what we get is something that looks like this. Then again, what is this thing saying? It's like, okay, what is y? This, the pixel that we said before. So if y is equal to 1, so like there is a dog, then what is the probability of our model? Well, the probability of our model is just y hat. Now, if we know
that the value is not a dog. What is the probability for model? Well, 1 minus y hat. Why? Because if you put 1 in here, this will cancel out. And if you put a 0 in here, so 0 and 0, this would cancel out, and then you're left only with this section. So that's our basically like our equation for the likelihood. So like, if you know this is a dog, this is what the model is saying. If you know this is not a dog, this is a background pixel, this is what the model is saying. And this equivalent probabilities as we said before. So like 80% probability this is a dog, or 20% probability this is a background pixel. So okay, what we want now is to maximize the likelihood. So maximize the likelihood. What does it mean to maximize the likelihood? Well, let's just go through a simple example. As we said before, let's just say that the model is saying like, well, there's a 0.5 probability for this specific pixel. But we know that this pixel is in fact a dog. So this is a 1. So what we want now is to make this probability as high as possible. So once again, we want this probability to be maximized. So we want this to be as close as possible to 1 because we know that is the right level. So we want to maximize this thing. Now let's say that the model output something that is like, okay, like 30%. But we know that this is in fact a background pixel. So this should be 0. Now, as we said before, this would be 1 minus y hat. So 1 minus y hat, this would be 0.7. And once again, we want to maximize this, right? Because we want to maximize, if we maximize this value, that would mean that we're maximizing the model prediction for it to be a correct label, so for it to be a 0. So we want to maximize this idea, which is maximizing both the values where the pixel is actually a dog and the ones where the pixel is not a dog or like the background. So this is what we're doing the max likelihood. Once again, this is our likelihood. So this thing right here. So what we're trying to do is we're trying to maximize y hat, y minus y hat, y minus y hat. This is what we're trying to maximize. Now we set this up for a single pixel. Now how would it look like for like every single pixel? Now we just say that the probabilities are independent. So that like one pixel doesn't the probability of one pixel doesn't influence the probability for the next one. So we can now write this as the product. What is a product? Well, this is just x1, x2, x3, x4, right? So we can just write this as the product of the likelihood for a single pixel. So this would be like the product of this. So that's what we're doing. Now we want to maximize, once again, we want to maximize this thing. But now there's a problem, right? There's a problem here. And the problem is like, once we start getting these probabilities back, and then we multiply them together, this will turn out to be something extremely small. So like, let's just set an example. Let's just say that like we get 0.1 and then like 0.8 and then like 0.9 or something like that. Now, if you multiply this together, this will be like a tiny number already, right? Like this will be 0.08 times 0.9, and then let's say like oh, that's 0.5, so like half of that. Like it would just be like a tiny little number after you multiply by all these pixels. So that's something you just don't want, because that would be a number that's close to 0, and that's very hard to train for. So what we do here is we just say like, okay, now we want to maximize not the product of the likelihood, but we want to maximize the log likelihood, right? And what this will do is essentially just turn this into, instead of products, turn this into sums. Why? Because the log of AB is the same thing as the log of A, plus the log of B. So what we're doing now is just we're turning this product into sums. So this is the same thing as the sum of the log likelihood. Now this is way better, because instead of like before we were multiplying these together, now we're basically adding them up instead of doing the product of them. So this is a lot easier to train for, because we're now trying to maximize this number. So this number has to be as high as possible. And now we're just adding them up, which is a lot easier because this doesn't go to 0, right? Now, the reason why we can do this is, in mathematics, this is called monotonically increasing. What does that mean? Is like, in our example, 0.1 is smaller than 0.9. So 90% is obviously higher, right? So when we do this conversion, we need to make sure that 90% is still higher than 10%. Now, let's just see what it looks like. So our log function would look something like this. And this would be 1. This is, of course, 0. Now let's just look at, okay, 10%. So 10% is right here, and then 90% is right here, which is 90% is still bigger than 0.1. So like 0.1 is smaller than 0.9. So okay, that makes sense. So our function is monotonically increasing. Now we can think of a function that is not monotonically increasing. For example, let's just say like this function right here. Now, what does that mean? It means that before you had 0.1 and 0.9. But now, after applying this function, the value would be higher for 0.1 and will be higher for 10% and lower for 90%, which doesn't make sense because we know that a higher probability must be like, well, still be higher. So this is why we do something that is called a monotonically increasing function, which is the law. So that's not only like a cool thing, it's like a requirement for us to do this. So amazing. We now have this idea of maximizing the the log likelihood. Now we just do something here, and it's we do the equivalent. So now we say that like this is equivalent of minimizing the negative log likelihood. Then once again, no need to get lost. What is our likelihood? Well, our likelihood is exactly this right here. So this is just maximizing the log likelihood is equivalent to minimizing the negative log likelihood. Why? Let's just take a look again at our graphs. So this is y equals log of x. And now let's just see what is this would be, let's make this better. There we go. This would be y equals minus log of x. So this is equivalent. Why? Because if you're here at 0.1, if you want to maximize this value, right? So if you're here and then you want to maximize it, you go up. You're trying to get to 1, right? This is equivalent if you're here, and then you want to go to 1, it's equivalent to minimizing this function, going down this function. So what we're trying to say is that going up the log likelihood is the same thing as going down in the negative log. So that's why we can say that these things are equivalent. Now, why? There's a good question of like, why are we trying to minimize as opposed to maximize? And the reason for that is because our optimizing algorithm is a gradient descent. So gradient descent. So what is gradient descent? Gradient descent is just moving around the parameters so that we find a minimum, right? So it's a minimizing algorithm. So that's what we're always trying to minimize something. So that's why we're trying to frame the problem as a minimizing problem as opposed to a maximizing problem, even though they're equivalent. Now, if we did something that is called gradient ascent, ascent. Now this would be trying to get a maximum value, and now we could use this one up here because we frame our problem into like a maximizing problem. But we don't really do this in machine learning. I mean, they're equivalent, but we don't do this. We just use gradient descent. So that's the reason why. Let's just cross this. That's the reason why we're trying to minimize something essentially. So that's it. That's essentially, this is called cross entropy binary loss, and this is what we use to train the UNet for a binary case. Now we will take a look at what that means for more classes, but this is essentially what it is for a binary class, which is the simplest one. Okay, if you understood that, then everything else is a lot easier. So let's just do a super quick rundown of what we're saying. So we're basically saying like, okay, we're getting the probabilities of each one of the pixels, and now we're saying like, what is the likelihood if we know the right label? Because we do know the right label when we're training, right? We do know the right label. So what is the likelihood of our model predicting that right label? So in this case, if we know the right label is 1, then our model is outputting this probability. If we know the label is 0, so not something, then we know this is the probability. And then we're trying to maximize this thing. Why are we trying to maximize this thing? Because it's the same thing as like maximizing the model probability of both the case where we have a dog and the case where we have a background pixel. So this is, if you maximize this equation, is maximizing basically like both cases. And at the end, we basically say like, okay, we do, instead of simply maximizing this likelihood, we maximize the log likelihood because it turns products into sums. And we can do this because it's monotonically increasing. And then
we reframe the problem instead of maximizing, we reframe it into minimizing the negative log likelihood. So that's what we did. Now, it's something extremely similar for the case where we have more than, for the case where it's not binary. So we have more than one classes. So we have more than one classes. So for example, in our scenario, we have a dog and a tree. So we can think of something that it's, we have a dog and a tree. So what would our ground truth be? Well, it would just be, okay, this is a dog, then this is a tree, and then absolutely everything else is just background. So this is background, this is background, this is background, this is background. So this is our new ground truth. Now, what is our model outputting? So our model will output now three different channels. So 1, 2, and 3. Now, once again, these channels are arbitrary values. So we need to turn them into probabilities. So what we do is we basically get like a section, like a single pixel. So let's just say that we're analyzing this pixel here. So we just get this pixel. And let's say that this is outputting like a minus 0.5, and this outputting like a 5, and this outputting like a 2. So what we do is we take these values and then we pass it to softmax. What is softmax doing is basically the same idea behind sigmoid of turning these into probabilities, but now with for multiple classes, for multiple labels. So this would now be, then again, we can just visualize what this thing is doing. So if we take a look at the plot for softmax, it would be something like this. And this would be like, okay, 0.5 is around here, and then 2 is around here, and then 5 is around here. So if we take a look at these heights, and then we add them up. So we add the small one, and then we add the one in the middle, and then we add the one up. And then we just say like, okay, out of this total height, what percentage is each one of them? So for example, this is like, I don't know, let's say 50%. This would be like 30%, and this would be like 20%. So now this essentially just we're returning these arbitrary values into now probabilities, which is very similar in concept of what we were doing before. So now once we do this, we just lock out the biggest value. So we go, what is the biggest value? In this case, the biggest value is 5. So that would be our that would be this one. So we just say that, okay, let's just say that this is 0, this is 1, and this is 2. So 0 would be background, 1 would be dog, and then 2 would be tree. So now what we're saying is like, okay, the one that has 5 has the highest probability. So we, for this pixel, so now once again, we create our out mask, and then we say like, okay, for this pixel, we will make this have the value of 1. Why? Because this was the highest one. And that's what you do. So like, then again, you do this for like every single pixel. So you would get, for example, I mean, in this case, it's horribly wrong, right? Because right here, it should be a tree, but let's just say that around here, you should get a 1, you should get a 1 around here, you should get a 1 around here, and then, so just make this blue, and then you should get here like a 0, you should get here a 0, you should get here a 0, and then of course, you should get here a 2, you should get here a 2, you should get here a 2. And that's essentially what is happening. And now what do you maximize, or like what do you minimize, sorry? Well, you minimize the negative log likelihood, where our likelihood, so our probability is now, so this is log py. And now our probability is now our softmax. So what you're doing here is just doing the softmax of our logits. So we're doing the same thing, right? So like once you understand how binary works, and once you understood like, okay, why are we doing the log likelihood as opposed to just the normal probabilities? Why are we doing the negative and we're minimizing that? Well, once you understand this for like the simplest case, then you can just think about a more complex case with multiple classes, with multiple levels, and this would be the same thing as minimizing what you said. So like basically, you would just try to make these as close as possible to the right ones. So for example, in our case, this was completely wrong, right? So what we want is like, okay, we want this to, we want this one to have like a higher probability, so that in our output, it would be like this would be a 2, right? So we basically want to move this one there. So it's more like, okay. So that's basically like one of the most common losses. And this is like the mathematical derivation. And I said at the beginning, this is extremely useful and extremely important to do at least once, because afterwards you just get an idea of why are you minimizing the negative log likelihood. And well, this is exactly why. Okay, it's super exciting. We made it to the third section of the video, and now we get to see everything that we learned implemented into code. So I have provided two different implementations of the unit, each one with different segmentation objectives, and we will go through them and we will see exactly how they work, what are they doing, and we will get to visualize a lot of the things that we learned. Okay, super exciting. So we'll see the first one. Um, then I'll go through each one of the blocks. So we have the imports, then we have the implementation of the unit. Now, remember when we went through the architecture of the unit, right? We went through the entire architecture and we said, look, okay, we start with an image 572 by 572 and so on, and each one of the convolutions will change the size. Well, in order to make this like fair and like as clear as possible, I have recreated this exact unit and I called it a hard-coded unit. So I've recreated every single one of these steps. So every single one of the convolutions, every single one of the max pooling, every single one of the up convolutions I have recreated, and you can go through each one of them. And I have also added the sizes so that it's even more obvious what are we doing. So once again, here it's just the definitions for the layers, and now we can see the forward function. And once again, you start with this image, and then you do a convolution and a ReLU. What is this doing? A ReLU and a convolution. So convolution, ReLU, and then convolution, ReLU, and then P1 up here is just max pooling. So this is just doing the first steps that we define, and that for the rest. Then what is center crop? What is what we said before, right? Like these are bigger than these ones. So when we add them, we need to crop them. So this is what this function is doing. So okay, basically recreated the unit. Cool. So we recreated the unit. Now, what is the data set? So what are we trying to segment it in this case? So for this first scenario, I tried to just make some synthetic data that would be very easy to visualize. So what I did is I created, okay, random location, square, triangle, circle, and then just combine them. And you see how this looks like. So first of all, you just give it a size and it will give out random locations. What do we use this for? Well, we just define a square and then we say like, okay, in a random location, create a square um, with the color and with the size. And then we say like, okay, random location, create a triangle with a certain size. Once again, random location, create the outline of a circle, random location, create a circle. And now what we do is we basically combine them into a single image. So it's like, okay, random, 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 combine them, and then we're trying to make the model learn each one of these um, each one of these masks. So the model should learn by channel each one of the different geometric figures that we find. So once again, we just okay, random, random, random point, different figures, and then the model should learn them. So here we're just defining the data sets. Um, we're getting this get item basically just gets you new data every single time. Then yeah, data loaders, and then yeah, there's reverse transform is basically just we're transforming our images for the neural network. So that's what this thing's doing. Now we get to the fun part, which is the actual training. So we defined first of all the architecture. We defined the data set, which as I said before is just a bunch of geometric figures. And now how do you train this? Now here we have this function called calculate loss or calc loss. And this function has the binary cross entropy, which is exactly what we explained. Once again, as I said before, we don't have to implement this by hand. This is just done by PyTorch. So we just say, okay, do this with our logits, and it will do everything that we said before automatically. And now I added a second one, which is called the soft dice. This is just because it was getting a little bit hard for the model to learn. So I decided to add this extra loss. But fundamentally, like this is exactly as we said before. This is just something else to make the model learn. This is just a different type of loss, which just looks um, at both of the regions. So okay, we have the loss that we find. I just added this extra loss so that it would converge better, and then I just do weighted sum. So basically get like a little bit of this loss and a little bit of this loss, and this is what we're trying to optimize. Okay, so now we get to the actual training of the model. So once again, we just get data loaders, we just get the device, we just set a number of epochs to train for. And yeah, we're getting some metrics, we set the model to train, and then we do, well, the actual training, right? So we're basically getting, from our data loaders, we're getting the image, so it's just the image that we defined before, and we're getting each one of the masks. So that's what our model is trying to learn. So this is just the training code, and then we're also outputting some metrics to make sure that it converges as we expect it to. So I trained it for, I think, around 50 epochs. Um, and here we use the optimizer, we use Alam, then we use a scheduler, and then we just train. So train to train, and then you get to see every single one of the losses. And then, okay, the actual exciting part. So how does this work, right? So this is just the code for visualization. And now you can see here, okay, we set this as an input, and then this is the predicted mask. So that's pretty good. And then we get to see the channel, and each one of the channels will output. Okay, so this is the triangle, this is the circle, and this is the square. And it will do this for every single one of the images. So like this is working really, really well. But there's something interesting here. As you can see, the input is bigger than the predicted mask, right? So like we're missing half the circle here. Why is that the case? Well, as we said before, we kept losing 2 pixels every time we did a convolution because we're adding no padding. So at the end, our mask will be 388 by 388 as opposed to being the same size as the image. So just in the spirit of leaving everything as the paper, I did the same thing. So our mask is different size, like it's smaller than our input. Then again, we can just use padding and it will be the exact same size. But I decided not to use it just to be just to like see visually that this is what happens if you add no padding. So okay, so this is our first model, and then you can come in here and move things around and just train it. This is not that expensive to train. Um, okay, amazing. So I made this first model, and then I realized like, okay, this might not be that useful, right? Like this is just synthetic data, kind of like random example. It's like, okay, let's do something that's a little bit more real life. So I went ahead and I found the data set for this original idea. Like you get a microscope image and you try to output a mask where the background and the cell are divided. So once again, we just get the imports. Then we do data imports, and this is basically grabbing all the data. So we get the image, and then we get the mask for the ground truth. So you get all the data. Uh, so yeah, you get all the data. You do some data transformations, and this is just some printing to see what we get. So you can see here, there's a couple examples. So this is the input image, and this is the mask. Then again, I'm doing some transformations for the same reason as I said before, that I'm trying to leave everything as is. So for example, like in this case, there's the image and the mask are the same size, but because we don't want any padding, I had to make the mask slightly smaller so that it matches what the model is expecting to output. So this is why we're doing some data transformations. Now, once again, we define the unit. Center crop is just a function that does this part that we define here. And then we define the unit exactly as before, 572 by 1, so this right here. And then 64, so 64, 64, exactly the same thing. And then once again, exactly the same forward. And now, okay, so this is the unit architecture. Then we see the dataset. So this is just, well, yeah, the dataset. As I described before, this is just microscope image and then the mask. And then we do training. So this is actually using a different type of loss. So it's extremely similar, but I found that it wasn't converging that well. So I modified it a little bit. So this one has, yeah, it's called the focal loss. So it has a couple epsilons in there because this was exploding and it wasn't working that well. So I added some extra things. But I mean, this is fundamentally not that different from what we just learned. So this is the focal loss, and then I added this soft die loss. I mean, soft die coefficient just to check the evaluation of the model. This is just a function to see the samples. And then, okay, we go ahead and actually train it. So device, model, optimizer, 30 epochs, and then we go through the training. So once again, we just get an image, we just get the masks, and the idea is for the model to learn to segmentate this thing. As I said before, I was getting some not a number, so that's why I added this metric printing. And here I basically print every couple epochs. I just see what's happening inside. So this is the input, this is the ground truth, and you can see like the mask is pretty, it's not that great. And then as it keeps on training, well, the masks are getting way better. So I mean, this is already a spoiler for how it would look like. So once it finished training, we can go inside and see, first of all, um, the parameters. So our model finished training, and I mean, you can see this before training, but our model finished training, and you remember what I said before of like, this is essentially just a 3 by 3 kernel, and we make 64 of these 3 by 3 kernels. So you have 9 parameters times 64. That's 576. Well, if we check our parameter count, we will see that exactly like that's exactly the case. Like we have 3 by 3 times 64, 576. This is what we have here. So it's just confirmation of like, okay, we are right in our intuition of like the model is learning these 3 by 3 kernels, and then we have 64 of those. So this is just confirmation, and you can see these for like all the other numbers, all the other layers. And now, okay, now the actual predictions. So once again, you get the test image. This is what it's supposed to look like, and this is what we get from the model. So this is honestly like really good, right? I mean, here it's wrong, and here it's also a bit wrong. I could let it train a little bit more. The problem here, I think it's more of we don't have enough data to actually get like really good predictions. But I just wanted to show you what the model can do, and if you let it train for longer, it'll probably be a lot better. But I mean, this is already pretty good. Okay, so we saw the parameters, we saw the predictions, and then we visualized the kernel. So like once again, when we said what is a kernel, right? Like we had an image, and then you apply the kernel, and then you learn something. Well, as I said before, this is exactly what a machine learning model is doing. So here we can say, for 64 kernels at the beginning, they're 3 by 3. How do they look like? Well, they look exactly like this. So these are our 64 kernels. And now, how do they look like after you apply the kernels? Well, the image looks like this. So this would be an image from a microscope, and then the model is learning these kernels, and after applying the kernels, the feature maps looks like this. So for example, we can do something really fun here, and we can look for something that's kind of similar to our Sobel. So something that is like negative and positive. So this would be, for example, let's see. Maybe for example 12. Like 12 is a little bit like a Sobel. So what are we expecting? We expect some vertical edges. So if we go down, what did I say it was 12? Well, if we go 12, you can see here that this is, I mean, a little bit, this is similar to what we were expecting, right? So this is, we are getting the edges, um, which I think is extremely just interesting and fun to see that our intuitions of what convolution is doing and what a kernel is are being confirmed by the model by like training these things. So okay, that's it. We went through the entire thing. We did a quick timeline. We saw the model architecture. We saw the definition for the loss, and then at the end, you got to see some actual code implementing exactly the unit that we learned. There's a little bit of a change with the losses, but I mean, the first one is using the exact same one, and the second one is using just a little bit a different version of it. But everything that we learned is applicable, and every single one of our intuitions was confirmed, including what number of parameters we need to have, and also how will the kernels look like. So I hope that was useful, and I hope that was understandable. And yeah, thank you for watching. Okay, we finally made it to possibly the most important paper so far, and that is denoising diffusion probabilistic models. Now, before we begin, let's just take a quick look at where we stand right now. So we're trying to learn diffusion math, of course. We're trying to prove that it's not that hard, and we're doing that by looking at each one of the papers and each one of the concepts that we need to learn. So we've taken a look at deep unsupervised learning using non-equilibrium thermodynamics. We know what a UNet is so far, and we're now at denoising diffusion probabilistic models. What have we learned? We've learned what is diffusion, essentially, what is statistical mechanics, what is stochastic processes, what is a Markov chain, probability distributions, what is a Gaussian distribution. We've learned the UNet, we've learned to derive the loss of the UNet, we train it, and now finally, we reach the most important part, which is like the actual diffusion model. So we made it there already. So we're gonna take a look at that, and then we're just gonna take a look at these two very very quick papers in the future. So okay, we're there. Now we're gonna divide this video into three parts. The first part is gonna be just a quick background. So just explain a little bit what we're trying to do. Then the second part is gonna be noise injection. So we're gonna talk about how do you actually noise these images and how you write this equation for the noise injection, which is very important. And finally, we're gonna take a loss function. So we're gonna derive the mathematics behind the loss function, which is this thing that looks horrible, like it looks disgusting, but you'll see that it's not that hard. Um, there's a lot of tricks there, and we're gonna take a look at that. And then we're finally take a look at the code, which of course we've trained a DDPM model, and you can play around with it, and it works. And we're gonna see like everything they say in the paper because we trained our own model, and we're gonna see everything we learned. We're gonna see it in the code. And just as an extra super quick thing, we're gonna show how this is equivalent to score matching. If you don't know what score matching is, that's absolutely fine. You can just skip that. It's just like a couple minutes. And if you do know, it's actually very interesting. We're actually going to learn score matching in the future. So, okay, now let's begin with part one. So let's just go super quickly through the actual paper. So the noise and diffusion probabilistic models. Let's just read a little bit. So considerations for non-equilibrium thermodynamics. We already took a look at that paper. Training on a weighted variational bound design. Okay, that is where we're gonna look at the crazy loss function. We're gonna see what that is. Now they talk a little bit about other models, for example, like GANs, autoregressive flows, VAEs, etc. They talk a little bit about like how they are able to produce images, and then they say like, okay, this is the proposed diffusion model. Diffusion probabilistic model, diffusion model for probability, is a parameterized Markov chain using variational inference to provide samples matching the data. Then we have a reverse diffusion process, which is also a Markov chain that gradually adds noise to the data in the opposite direction. Okay, so we already know what a Markov chain is. We already know what it means um, to noise something or to go back, because we're ready to look at that. But we're gonna see it again with the equations in just a second. So there's something very funny that I like to point out here, and it's this line right here. And they say like there's no demonstrations that they're capable of generating high quality samples, which is kind of funny, you know, like they didn't know. They didn't know at the time that like this was gonna be such a huge thing and so successful. So this is quite important, and we'll see why in a future video. Okay, so finally we got to the background. So let's just read, and then we'll see each one of these equations in detail. So okay, diffusion models are latent variable models of the form where are the latents of the dimensionality with the same dimensionality of the data. The joint distribution is called the reverse process and Markov chain. Okay, so don't get confused by like all the math. Let's just divide like what is this thing talking about, right? So like, okay, this is just saying x0 is our initial image, which is sampled from my data set. So like you have a data set and then you sample an image that is x0. So that's exactly this thing right here. And then we have x1, x2, x3, x4 until xt, which are going to be the noisy images. So they're going to be like slowly more and more noisy. And now what we call p of theta is the reverse process. So basically like, okay, you have an image, which is x0, which is taken from a data set. And then you noise it all the way until we reach t. And then once we reach t, how do we go back? That's called the reverse process. And it's defined as a Markov chain with a Laurent Gaussian transitions. And the idea, what is this thing saying? The idea is that once we reach xt, this is gonna look like a Gaussian centered around 0 with a unit variance. So this is what this thing is saying. Once again, we start from an image, sample from a dataset, and then 1, 2, 3, 4, 5 until t, and then once we reach t, this is gonna be just a Gaussian. Okay, amazing. So like, what is this saying? This is what we described. So this is the trajectory. This is the reverse trajectory. So this is saying like, okay, we started noise. What is noise? We defined it before. So we started this Gaussian, and then we take steps to go back. What are these steps? Well, this is just a normal distribution where the mean and the variance are calculated by our machine learning model. Okay, so we're gonna take a look at this in just 1 second. And now we have a forward process. So this is a backwards process. Once again, what is backwards? Going from t to 0. So noisy all the way to not noisy or like clean. I think this notation is not great, but I would have put it the other way around. But yeah, anyways, that's what it's saying. Now, forward process is fixed to a markup chain that gradually adds noise to the data according to a variance schedule. So once again, what is this thing? This is just the trajectory. So this is saying like, okay, we start with the clean image, right? So given our clean image, we have this thing which goes from like 1, 2, 3, 4, 5 all the way until t, which is basically just noising. What does it mean to noise? Well, this is just saying we have a markup chain that takes a step where the mean is like um, the so they're saying like the previous step or like the next step depending on how you see it, right? Like if you're here, then where you're going next, it only depends on where your current state. Is scaled down by this variance schedule, and our variance is the variance schedule, of course. Now let's say how do you train it? We're gonna take a look at this in the future as well, and we're gonna take a look at this also in just a second, which is how do you actually noise things. So okay, let's just start by the background itself. So super quickly, let's just we already went through this in the other video, but we're gonna just super quickly see it again. So once again, as I said in the first video, you can think about this not necessarily in the big dimensional space that is an image. We can think about this in just 1 pixel. So we can take a look at just simple 1 pixel. So instead of here looking at the entire image, let's just say we take a look at, okay, it's quite big. We take a look at 1 pixel, right? So we just take a look at this 1 pixel right here. So okay, we take an image. In this case, we will just take 1 pixel, and let's say that this is our little graph. Now, where is the pixel? The clean pixel, right? It's gonna be here, let's say. So this is gonna be x0. Okay, cool. Now, this going from x0 to xt is the noising process, right? Which is this equation, which once again, if we take a look at what this thing looks like, so it's this one right here. Okay, so we have it here. Now, what is this thing saying? This thing is just saying like, okay, to go to the next step, you basically use where you are right now. So we are here, and then you scale it down by this factor. Now b at the beginning is going to be relatively small. Let's just define b over here. So b, or like this beta, that's not b, is beta. This beta is going to be like really small at the beginning, and it's going to grow a little bit larger. So this is beta with like time steps. So once again, if we think about it, right, like just think about it, beta is going to be really small. So 1 minus beta is going to be like somewhere close to 1, and then the square root is also like, let's just say somewhere close to 1. And then this thing, this is just going to be, of course, close to 0, because beta is really small. So what does this mean? This just means that like, okay, we take this value, so this is this value right here. This is where we are. This is our clean pixel. And then we just scale it down. So this is going to be, let's just say here. Why? Because we're scaling it down by 1 minus beta. Let's just say that's like, I don't know, 0.9 or something. So this is just scaling it down a little bit. And then we define our Gaussian. So our Gaussian is going to look like this. Why does it look like that? Well, because our variance is very small. So our variance is tiny, so our Gaussian is like that. Okay. So now what do? We just sample from there. So this is the next step, right? We define this, and then we sample from this point. So let's just say this is at t equals 1. And now let's just look at t equals 2. So we just sample from here. Let's just define this again. So we had this distribution. And then we just sample from this. Like, let's just say that we get this one right here. We get that value. So that is our current value. What do? We do the exact same thing again. Now our variance, before it was very close to 0. So let's say that before we were here, now we're here. So this is still pretty small, but not as small as before, right? So this is still pretty small, so but a little bit bigger. So now this value will be, I don't know, let's just say 0.8. So 80% of this, we're gonna go here, And then once again, what would this value be? Well, this value would be a little bit bigger than before. So our new, let's just do another color. Our new Gaussian is gonna, let's say, look like this. So, the variance is a little bit bigger. So like you have a little bit more variance. Once again, we are centering this value. This value right here is this. And then we're just scaling it. And then we're defining this a Gaussian with this variance. This is how big it is. Okay, so we have another distribution. And then once again, what do you do? Well, for T3, I mean, I think you got the idea. For T3, what do we do? Well, we have this new Gaussian right here. Now, once again, we just sample from it. Let's just say that we get somewhere around here. And then once again, okay, we sample from there. What is our beta? Okay, let's go see our beta. Okay, our beta is a little bit bigger now. So what does this mean? This means that this will be a little bit smaller. So let's say that this is just like, I don't know, 60%. So this is 60%. And now our beta is also going to be bigger. So this will be somewhere, let's just say somewhere around here. Or let's just make it a little bit fatter like that. And then once again, what is this doing? Like this is just iteratively doing this and this. Like you just sample from here again, and then you just get a clean pixel, and then you multiply against the beta, and then you do this iteratively until you basically reach a point where, so let's just say dot 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 t equals t. At t equals t, we get to a Gaussian centered on 0 with a unit variance. So, okay, so once again, like the math is not that hard, right? Like the math is understandable. This is our Markov chain. What are we doing? We're doing this for 1 pixel. So these are clean pixel. We just scale it down a little bit by the beta noise schedule. And then we also have the beta noise schedule, which defines the variance. And then we just sample, 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 sample until we basically get to this point right here. Now, once we're here, right? So once again, you can think about it like we're just taking a look at a single pixel, right? We're basically noising. We're going from this clean pixel, and then we iteratively take steps until we noise it. Now that we're at the noisy pixel, how do we go back, right? It's like we're here. How do we go back to that clean pixel that we had before? Well, that is the job of the machine learning model. So like this is our Gaussian step that we have to take back. And this is going to be parameterized by theta, which are the neural network weights, of course. So once again, now let's just take a look at how that would be. So we're at t. Now let's just say like, okay, what would be t equals t minus 1. So we were at this unit Gaussian. And let's just say that, okay, we sample from there. Let's just say that we get this value. Right? So we sample from the unit Gaussian. So we sample and we got that value right there. Okay. So we're starting right there. Now, how do we go back? Well, just take a look at our other equation, which is this one right here. So how do we go back? Let's see. What does this thing say? This thing is saying like, okay, the next step is going to be learned by the machine learning model. So the machine learning model will take, let's see, the machine learning model will take this a function of what? xt. What is xt? This value. And t. What is t? Well, a time step. So we're going to give the machine learning model both where we are right now, in this case is just complete noise, and the time step. And the machine learning model is going to tell us where to go. So we're going to, and also like, it's the same thing for the variance. Now you will see in the paper that the variance is actually kept constant, but I mean, you can learn it. It's essentially the same thing. So, okay, so you give both where we are right now and the time step to the machine learning model, and the machine learning model outputs where you're supposed to go. So now the machine learning model will tell you. So like, let's just put this into another color. Let's just say, oh, this is horrible. Let's use this one. So this would be the output, right? The machine learning model is now telling you, okay, given that you're here, and given that this is the time step, you have to go here. And then let's just say that it also predicts the the variance. So it's just gonna say like, okay, you're gonna go here with the variance like that. So your, let's just use the same color. Your distribution is now gonna look like this. Or yeah, let's just make it a little bit farther. This is gonna be your distribution. Okay, so like now what do? We take another step. Let's just say this is gonna be t equals t minus 2. Let's just do this again. Okay, so now we are at this distribution, and we just sample from this distribution. So let's just say that we sampled here. We get this point right here, right? Now, once again, what do? We pass this point to our machine learning model. We pass this data, this time step, and then the machine learning model is going to tell you like, okay, since you're here, now you need to go. Now you need to go here, right? So like it's telling us where to go essentially, and then it's saying like, okay, and now you're gonna go there with the variance. That's kind of like this. So before we had a higher variance, now it's a little bit like a smaller variance because we're getting close to the actual point. And the idea is that you do this iteratively, right? So like you keep doing this, you keep doing this until the machine model basically gets you back to where we started. So the machine learning model basically learns how to go back. And the idea is that you would basically end up at this like this. I mean, you're not gonna end up necessarily at the exact same point, but the idea is that you would uh, get the distribution of like somewhere around that point. So like, what are you doing exactly? Where we're just sampling a pixel from a data set, and then we're like, okay, this is our pixel. What are we doing? We are taking a Gaussian step and sampling according to this noise schedule, which defines our distribution. So you sample and then you do this for another time step, and then you do this for another time step, and then you do this iteratively until at the end you will reach this unit Gaussian. Now, once you're at the unit Gaussian, which is this part right here, once you're at the unit Gaussian, now you're like, okay, now t, which is the last time step, t minus 1, you pass t minus 1 to the machine learning model, you pass where you are, and the machine learning model is going to tell you where to go. So like, you should go here, you should go here, you should go here, and that iteratively until we basically go back to our clean data. Now you might think like, okay, this is just one pixel though, like this is not the complete picture. But the thing is, it is the complete picture. This is the exact same thing, but for multiple pixels. Like this is exactly what is happening, and we actually proved this. So if you took a look at one of the extra videos that are published, we proved that like each one of the Gaussian steps is independent because the variances are so like one pixel won't affect the other one in our mathematical definition. So we proved independence. So that means that basically each pixel is doing exactly this. So like you can just imagine this for multiple pixels, so like more and more dimensions, as we said at the beginning. So okay, now once again we have learned what these things are, right? We've learned what this thing is. We've learned what this thing is. This is just the repeated application of what we of this equation right here. So just the repeat application. So this is the trajectory. This is the repeated application of our backward trajectory, which we already showed, right? So I mean, I think we're good. Like this is pretty understandable. So okay, that is the first part. That is the quick background. Okay, now we'll take a look at the second part of this video, which is noise injection. Now, noise injection is defined like this, and we're gonna see how this is derived. But first, let's just take a look at the paper super quickly. So, okay, the paper goes, a notable property of the forward process is that it admits sampling t at an arbitrary time step t in closed form. What is this thing saying in plain English? It's like, okay, we have a forward process. What is our forward process? This is our forward process, which is basically saying like, okay, you have a clean image, and then you iteratively add noise to this image until it ends up at a unit Gaussian, right? So that's our forward process. What this thing is saying is that a property of the forward process is that it admits sampling at any time step you want. So an arbitrary time step with a closed form using the following notation. So this is basically saying like, we have this equation that allows you to go from clean image all the way into like 50 time steps or like 10 time steps, just one shot, right? Like you don't have to go through the intermediate time steps. You can just boom, go there. So once again, let's just be super, super clear. Let me make myself smaller. How does it look like? Well,
we have a clean image. So this is our clean image.
And then we define a for process as just slowly adding noise to this, right?
So this would be time step equals 1, and this would be just a slightly noisier version of our original image.
So it's
Slightly more noise. So then time step 2, we add more noise into this image. So this would be noisier. Now time step 3, then once again, I mean, this is just more noise, right?
so normally you have this clean image, and then you go times step 1, times step 2, times step 3, and that's how you arrive to this noisy version of the image. What this thing is saying is that if we use this notation, we can basically go from the clean image all the way into whatever arbitrary time step we want, and it will give out the noisy version of that image at that time step without having to go through all the other time steps. So once again, how does that look like mathematically? This is just saying like the probability, you know, of the image at time step whatever you want. In this case, let's just say 3, given. So this is given that we have the original clean image is equal to this equation right here. So once again, this is just saying like, okay, if you follow this equation, it will give you the noisy version of that image for like any times that you want, without having to go through like all the intermediate steps. Okay, so we're gonna derive this mathematically and see where this comes from. So first of all, this is our forward process right here, right? Once again, what is our forward process? Well, we defined this before just for 1 pixel, which is a lot easier to see. So we just said like, okay, if this is our current time step, where are we gonna, our current value, sorry, where are we gonna go next? Well, so once again, if we our current value, where are we going next? Well, where we're going next depends on where you are right now, with a scale version of that, and a certain, oops, let's just use another color, a certain variance. So once again, how does that look like? Well, this is where we are right now. This is our current point. Now we scale this point by this value, so 1 minus the square root of 1 minus beta. Let's just say, just for an example, this is 90%. So we take 90% of this. Let's just say that it goes right here. And that's going to be our mean for our Gaussian. And now we also have the value for the variance, which in this case is going to be beta t. So beta at that time step t is going to be the value for our variance. So let's just say that it looks something like that. And this is where we're going to sample for the next time step. So this is the equivalent for just 1 pixel of what we're saying before. So this is equivalent, right? This is just on a whole image, and this is just on a single pixel. Now, starting from this, we can reach this final equation of just like noising a whole image by just giving the time step, right? So let's just see how does this looks like when we sample, right? What does it mean to sample from there? Well, it turns out that if you want to sample, so if you want to sample, if you want to, this means this little tiny wiggly thing means sampling. So if you want to sample from a normal with a certain mean and a certain variance, then what you do is you take the mean and then you add the standard deviation. So in this case, it's going to be the square root of the variance, so the standard deviation times epsilon, where epsilon is going to be sampled from a normal, from a unit Gaussian. Once again, let's just super quickly take a look at what this means. This is just saying like, okay, if you have a certain Gaussian, let's just say that ours looks like this. So this is your distribution. So how do we get a point from here, right? Once again, we are most likely to get points where there's a higher probability. So we're very likely to get a point around here, and less likely to get a point around here, for example, right? This is very low probability. This probability times your value. So how do we sample from this? Well, this is the sampling trick. So basically what you do is like, okay, first you sample noise. What does it mean to sample noise? Is you sample from a unit Gaussian. So you have a Gaussian that's centered around 0 and has a variance of 1. And then you just sample from there. So you just get a point from here, right? So like you just say you get a point from here. So you get a point from there. And this is just like a random value. And then what you do is like, okay, you take that random value and then you scale it by your standard deviation. So in this case, our standard deviation, let's say it's relatively small. So we'll scale that value down a little bit. And then you just add to the mean. So once again, let's just take a look at what this is. It's just like, okay, this is the mean. And then let's say we got this point right here. and we're gonna scale it down. So if we just add it without scaling, that would be somewhere around here. But we scale it down, so it would be somewhere around here. So our sample will be this one. Now, if we try to sample again, what would we be doing? Let's say like this is the mean. So we just sample from a Gaussian distribution that's centered around the mean. That's centered around 0, sorry, with unit variance. And now let's say that we sample, I don't know, this point right here. So we get this one, we scale it down by our standard deviation, and let's just say that it's a point right here. So this would be a second point. Now, once again, we keep doing this, and now let's say that we get very unlucky and we get like this value right here. So once again, that would be the mean plus this value scaled down. So let's just say that this is somewhere around here. So you would be sampling from here. So this is the way you sample mathematically, right? So this is the sampling trick. So once again, if we take a look at our equation for this Gaussian, it looks like this, right? It's a little bit messed up, but it looks like this. So let's just write it down again. So our Gaussian, where we're trying to sample from, is 1 minus beta t of t minus 1, comma, this is, let's take a look again, this is just beta t, right? So beta t, the identity matrix. Okay, so the first thing they say is like, let's just call alpha t equals 1 minus beta t. So they're just saying, let's just do this. Once again, this is right here. What it is doing is just different notation, right? So this would be like, okay, you have your same normal, and then this would be now alpha t x t minus 1, and then this would now be 1 minus alpha t. So we just changed the variables, so nothing crazy so far. And now we can check how the sampling would look like for this equation. So once again, what is our mean? Our mean is this thing, and then we add. So whatever is our so this is the variance, and we want the standard deviation, so that's going to be the square root of this thing times epsilon. Once again, where epsilon is sampled from. Okay, so this is just sampling from the normal that we defined, right? Okay, so far we haven't done anything crazy. Now let's just take a look at different time steps. So let's just say like, okay, let's just start at time step 1. How would this look like for time step 1? Well, x1 would look like if we just follow the equation, right? So this would be alpha 1 x0 plus 1 minus alpha 1 epsilon, right? Okay, so first of all, we literally just took a look at the equation and just filled in the values, right? So now let's take a look at time step 2. So how would that look like? Well, that's going to be alpha 2 x0 plus 1 minus alpha 2 epsilon. But now we are, oh, sorry, this is not x0, my bad. This is x1. Okay, but now we already know the value for x1, right? So like we already know the value for this because we had it before. So we can rewrite this basically just substituting x1 for the thing that we already know. And if we rewrite it, it will look something like this. So first, everything will be multiplied by this value, right? So the first one will be alpha 1, alpha 2, x0 plus, once again, you have to multiply it by this one. So it will look something like this. Epsilon plus what we had before, epsilon. So okay, we just rewrote the equation with what we had before. Now let's just take a look at the next time step. So this is a bit more clear. Once again, what is this? We just plug in our values in the equation. So it would be something like this, plus 1 minus alpha 3 epsilon. Once again, we know the value for x2, right? So we know this value for x2, which is the one that's just above. Once again, everything will be multiplied by this. So it would be 2, 1, x0, and then plus 3, 2, 1, plus 3, 1 minus epsilon, plus what we had originally, which is this thing right here. So plus, it's not writing, there we go. 1 minus epsilon. Okay, so now hopefully you can see the pattern here. So this thing has a very interesting pattern. If you keep going, you'll see even you see it even clearer. But there's a pattern where like when we increase the time step, we basically get a result that looks like this. And this is just in terms of the original image, right? they use the original image, and then a bunch of values for of epsilon. So we can extract basically the pattern already, and we can see that okay, x of any t that you give it, right? Like any t will basically be. So what is this? This is just a product of the times that where we are. So like you're saying like alpha 3, alpha 2, alpha 1. Well, we can rewrite this as alpha t, for example, or like alpha s t. Once again, what is this thing saying? This is just saying like, okay, what is the, if we write something like this, I don't know. This is just saying, well, if t equals 3, this would be 3, 2, 1, right? So this is just basically a way to represent this thing. So we can rewrite this as a product, and then we just call this product alpha t bar. So once again, don't get like confused. This alpha t bar is just a representation of the product of all these alpha t's. So we can just say that okay, this is just alpha t bar x0. So you can just give this basically. If you give it once again, if you give it 3, this would be equivalent of this entire thing. And actually, like before we keep going, this is what they do. So this is exactly what they do. Yeah, s equals 1, of course, because we have a 0 is the original image. And then we just see that okay, this is plus. We basically generalize this section right here, and then this we can just show that as c epsilon, where c is just a constant, right? Like this c of course has a pattern, and if you want to know, this c has a pattern of something like so 1 minus this thing is always present, so you say like something like s epsilon, and then how do we basically represent these things? If you look at these portions, they are always the maximum, so like whatever we are, and they're getting rid of the other ones, right? So like this is the maximum, and we're missing 2 and 3, 2 and 1, we're missing 1, and in this case we're missing them all. So you can just rewrite this as this would be not t over s. Once again, what is s? S will be, for example, if we say t equals 3, s will be um, like 1, 2, and 3. Okay. So, but then again, that's not that important. Like, um, just let's just keep going. So let's just say that this is just a constant times e, where e is our sample from a normal unit Gaussian, right? So this is our sample. Now, in mathematics, when you start adding Gaussians, it turns out that also is also a Gaussian. So this is called like the linearity of adding multiple Gaussians. And it turns out that if you keep adding once again unit Gaussians with a certain constant, that would end up looking like a normal distribution, where this would be just the addition of c squared. So that's how this is gonna look like. And then if you square this c, right? So like we define this c again, but if you square it, it turns out that this will look like this part right here. So once again, I don't want to do the algebra right now, but you can trust me that this will be like, okay, this would be 0, so this would be mean, plus, once again, this would be the variance, right? So we can now just call this 1 minus t and the square root. Once again, why? Because this this is a normal distribution, so this is the variance, and when we sample, we want the standard deviation, so we just take the square root of that. So this is the answer. And now what happens if you, so like we generalize this section, and then we said that this section is equal to whatever we defined down here. So we just finally add them up. Just saying like xt is alpha t x0 plus, so 0 of course doesn't make any difference. So once again, what is this thing saying? So okay, we basically found a way to show that if you give this thing the original image, and then if we sample from a unit Gaussian, so what is a unit Gaussian? This will be defined a little bit up here. So if we sample from a unit Gaussian, so we sample some noise, and then we multiply by these factors, we are able to instantly just like get any single time step that we want, right? So we don't have to go through any single of the other iterations, we just boom, 50. Okay, it gives you the image at 50, or like 100, it gives you the image at 100. Okay, so this is the mathematical derivation, and this is how we get to this equation. And once again, this is the change of notation. So we saw where this comes from, right? So like this is not just something that they give you. We saw where this comes from mathematically. Now, if you don't trust what I did here, this addition of different Gaussians is actually a convolution, and I made like this beautiful notebook for you to like make sure that this is actually the case. But otherwise, you can trust me. And then we get to this equation, which is just saying like, okay, we calculate this value, we calculate this value, we sample, we have the original image, and then you product, add, and that's how you get the final noisy image. So before we keep going, let's just see how this looks like in the code, right? So like, I coded this already. This is the full implementation of the DDPM, but so first let's just take a look at the noise. So what is this thing doing? Importing, now we're getting the data. We are getting the data for celebrities. I think, yeah, like this Elon Musk right there. So okay, the data from celebrities, and then finally we're defining our noise schedule. So in this case, we just say that t, before we just say like 1, 2, 3 until t. Well, now t is 1,000, and then we say that beta starts at this tiny number, and then it ends at this tiny number. So we do this, and then we define once again. We said before that alpha t will be 1 minus beta, and alpha bar t will be the product of those, right? So we can calculate. So we defined our whole time step. We define where beta starts. We define where beta ends. Now we define y minus beta, and then we multiply them together to get this value. And basically, if you keep doing that, we get to this point, right? So like everything else is just doing what we said before, and now we get the original image, and then we get some noise, as I said before. So like original image, and then you get some noise that's from a unit Gaussian, and then we multiply what we already calculated plus the product of the noise times the other scale factor, and then that's how you instantly, like boom, one shot get your noisy image. So what is the square root of alpha bar? Is what we defined before. So square root of alpha bar, and then what is this square root 1 minus alpha bar? Well, it's what we defined before as well, right? So like you can see that this equation right here, it's actually implementing the code, and it works. So once you define this equation, you can now just give it an image, and then you see what happens. And as you get, like, you can just move this thing around. So like you can put like 100, like a 50, or like 300 or whatever, and then you can see the noise. So like you don't have to go to like 1, 2, 3, 4, 5 until 100. You can just boom, instantly get this thing out. So how does that look like? Well, it looks like this. So like we can get 50 instantly, or we can get 800 instantly, or yeah, 200, whatever you want, we can get it instantly. Now we can do something very interesting, and it's looking at how is noise added, right? So here, this is a little bit complicated to see, so I'm just gonna try to explain it one by one. So the first line that we're looking at, this is 1 minus beta t. Now what is beta t? Beta t is starting at this tiny little number that is close to 0, and then it goes all the way to like 0.2, we define 0.02, I believe, yeah. And so like 1 minus that is going to be this plot right here. So that's just going to be like 1 minus almost close to 0, so that's almost 1. And then at the end, it's just going to be like 1 minus 0.02, so it's going to be like very close to 1. So this is our beta, and then we define, okay, what is our alpha, right? So this is just the product of each one of the 1 minus beta. What does that mean? It's like, okay, you start at 1, and then let's say like this is like 0.999, right? It's like your value is 0.999, and then let's say like the next one is like 0.8 or something. So like now it's 0.999 times 0.8, which is, I don't know, something like 0.7 something, right? And then you can do that like 0.7 times, I don't know, like 0.7, and then point, so like that's how it works. And this is the second plot right here. So this is how that looks like. And now we just, so we defined alpha bar, and then we can see how alpha bar looks like, and that's the first graph. And then we can also see how 1 minus alpha bar looks like, and that's the second graph. And what this thing represent, this one is basically how much of the image do we have at this time step, and this one is how much of the noise do we have at this time step. So once again, it just a simpler version is like how noisy is this, and is this noisy. So at time step 0 or 100 is going to add noise almost linearly. And then we can see something very interesting, that like at around time step 500, the noise is not gonna change that much. We're already like almost purely noise, and we can see that. So like we can see that here. So once again, times 50, 100, 200, this is almost linear, right? Like it's almost linear increasing. But we can see that at time step 400, we're almost fully noise. And at time step 700, 800, and 900, they almost look exactly the same, right? Once again, why? Because if we take a look at our graph, these time steps are almost fully noise already. It's okay. This is what we defined, and this is what the paper defines. But we can go one step further, and we can make up our own noise. So instead of just defining all these betas and stuff, if we just say like, okay, we will call our alpha bar, alpha t bar, we're just gonna call this equation. Let's just not focus on the equation itself, but let's just take a look at how the equation looks like. So once again, this blue bar is our equation that we defined. So it looks something like this. And then this other plot is 1 minus that, the square root of 1 minus that, right? So what is this thing saying? Once again, it's like, okay, this is the image, the original image, and then it's going to go down, and the noise is going to go up. So once again, how noisy is like, okay, at time step 0, it's going to be um, like, it's going to increase almost linearly, and then I mean, it's almost linear, like almost completely linear, right? At this time step is not going to be that linear, but it's almost linear. Once again, we can go and see what that looks like, right? So like times at 100, 200, 400, 600, we can see that even at 800, we still have a little bit of the image, which in the other one we didn't, right? So like these all looked exactly the same. But we see that here there's a little bit of the image still at times 800, which is what we expect, right? So this is not purely noise already. And now we can even like further, we can define our own noise schedule. So like I just made up my own noise schedule, which I defined it as this exponential decay. And now, so basically I just defined this plot. And then once again, we can take a look at the 1 minus that, the square root of that, and it will look like this. What does this represent? It's just like, okay, this is the percentage basically of the image that's going to be present, and this is how much noise is going to be present. So we're basically adding noise with this plot. So if we see this, is like, okay, at 100, we really have a lot of noise. And like 200 is a lot of noise, right? This is a lot of noise. But I mean, at 800, this is super noisy, but it's still not complete noise. So if we take a look at how that looks like, well, at times 800, 100, we already have a lot of noise. 150, it's super noisy. 200 is like super noisy. 400 is, but we can see that even at 500, 600, 900, this is still a little bit of image right here because of the way we describe um, our noise schedule. It's okay. You can come around and you can play around with the different functions. You can make up your own functions, like everything. As long as this thing is going down, like you can make up your own functions. You can make a logarithm. You can put anything in there that you want, and this will basically change the noise schedule, which is the way we add noise to the image. So okay, hopefully that was understandable. We went through the math, we went through the code, and this is the way that you inject noise. So now we will go through the loss function. Okay, so we finally arrived at the loss derivation. So how do you actually train these models? Now, there's a thing here that the loss derivation actually involves a lot of very convoluted algebra. And I don't think that's particularly useful to understand what's going on. So like, in order for me to like make this as clear as possible, I'm not gonna go very deep into the algebra derivation itself. I'm just gonna take a look at the general intuitions. So I try to make this as easy as possible. So I even added some steps here so that you can just like follow this and hopefully make the entire picture a little bit easier. And also, I just want to say that like you just have to go through this derivation once, and then you can basically forget about it. This is very useful because it does give you a mathematical framework of where the loss emerges from, right? So like this is not something that you just come up with necessarily. This is something that actually emerges from the things that we're trying to optimize. So I think that that's why it is very useful to go through the math at least once. But then again, we're not gonna go into the details of the algebra. We're just gonna take a look at the intuitions. So okay, with that said, let's just go into the paper super quickly. Now this says like, okay, we can rewrite the loss as the following function. Where does this thing come from? This thing comes from the original paper. So deep learning using non-equilibrium thermodynamics. And I actually have an independent video for this. This is like derived from the elbow. Once again, we're just gonna pretend that we're given this equation. So like, don't worry about it and don't worry about what each of the specifics are. Well, we're gonna take a look at the intuition, okay? So we're just given this basically, and we're also given this. This is also non-trivial to derive, so we're just gonna pretend that we get it. I'm gonna make a video on it to like do the algebra itself, but here it's not that useful, I swear. So yeah, we'll see what like this still looks crazy, right? But we'll see essentially where this emerges from. Okay, so these are loss. This is what we have to work with. Now, what are we trying to do here? We're trying to optimize a model parameters, so the parameters of a model, so that the loss is minimized, right? So we're doing a minimizing optimization algorithm. Now we're trying to move around the weights so that this is the minimum possible, right? So the weights in this case are the theta. So we're parameterizing our function according to the weights. Now, if something doesn't depend on the weights, then that means that we cannot optimize it, right? So it's So we end up with something that is quite simple already. So from this crazy equation, we got to this slightly easier one. So we start from the elbow, then we only get the middle loss, right? Because there's a couple, we only get the middle loss. And then it turns out that this middle loss has the form of a KL divergence. What is a KL divergence? A KL divergence is essentially the distance between two distributions. So you have one distribution, you have another distribution, how far apart are they? There's this beautiful three blue, one brown video that you can go watch, and he explains this very well. And it's also non-symmetric, which means that. Well, let's just take a look at it, right? So what is the KL divergence? Let's say you have two distributions. The KL divergence is telling you how far apart are they from each other. This is what the KL divergence is telling you. So like how far apart are these distributions from each other? Now there's a disclaimer here that there's an asterisk that is not the actual distance, because if you took the KL divergence like this, you would get a distance. But if you swap them, you would get a different distance, which makes them non-symmetric. So this is not really the distance. Otherwise, it would be the same no matter how you put them. But you can think about them as a distance. Once again, there's this beautiful blue one brown video you can watch and explains this very well. Okay, so we're doing the KL divergence from for two different functions. What are these functions? Where this is what our model is trying to learn, so the backwards pass. So we're trying to make the model learn where to go, right? And what is this? Well, this is the actual Gaussian step that we're supposed to do. So this is where we are actually supposed to go, right? It's like we're trying to make our model learn where it's supposed to go by taking these Gaussian steps, and we find this, and then this is the actual Gaussian step that you have to take, essentially. Now, what this thing is doing is like, okay, we're just trying to make this as close as possible. So like minimize the distance, right? So we're trying to make these two basically like as close as possible. So this is what we're trying to optimize for. We're just trying to get them as close as possible. Why? Because if we try to get them as close as possible, this is essentially saying that our prediction would be very, very close to the actual distribution. So this is what we're trying to do. Okay, once again, the math, if you want to derive this, then you would have to like substitute for this equation, and then put them all into the KL divergence, which is like this integral, and then you solve for them. Now, once again, we're not going to do that. So just intuition. This is what we're trying to do. Now, it turns out that the KL divergence between two Gaussians, once again, we know that these two are Gaussians because we defined it. Like this is what we're trying to do, right? Our whole process relies on these Gaussian trajectories. So we know that both of these are Gaussians, and it turns out that the KL divergence between two Gaussians is closed form. What does it mean to be closed form? It just means that we have like an equation that will tell you how far apart are they. Now, I mean, just to make this a little bit clear, if we had like, I don't know, some random distributions like this, and then you wanted to know how far apart, like the distance, right? This would be very hard to do because I mean we don't really know, like it's a very hard function to define. Defining the distance is also a very hard thing to do. I mean you can probably do like some Fourier analysis or something, but like it's essentially hard. But if we have two Gaussians, well, Gaussians are very well behaved. We know a lot about Gaussians. They are very like essentially mathematically um, stable or like elegant. So we can derive a general closed form equation of how far apart two Gaussians are from each other. Now, if you wanted to do this, you could plug in the KL divergence of two Gaussians. Let me just move this here. You could plot the KL divergence between two Gaussians. That would look okay. So you could put these equations, the equation for the both the Gaussians, that you could put them into KL divergence, and you would get the general equation. Now, once again, we're not gonna do this here, but it turns out that the distance between two Gaussians turns out to be something with the form like this. Um, so this is 1 minus 2 squared plus a constant. So this is a constant, so this is a bunch of numbers. If you wanted to know what that is, you would like try to solve this equation, but once again, we're just trying to make it simple, so just trust me that this is the answer. Now, um, this is already like a lot simpler than what we started with, right? We started with this crazy equation. We get rid of the two values at the end, and we explain why. Then we're left only with this equation right here. And then it turns out this equation is just trying to minimize the distance between two functions. In this case, two Gaussians. And it turns out that the Gaussians have a closed form solution that we can essentially solve for. And this closed form solution has a form that looks like this. So we can now essentially train our model with this goal in mind. So if we plug in our what our Gaussians are, this would essentially be like, okay, we can now define our loss, right, as the expected value. So why the expected value? Well, because it's right here. If you don't know what expected value is, this is essentially just the average. It's actually just the values weighted by the probabilities, but essentially just an average. And we can plug in what we said we had. So this would be something like this. Okay. So this is our objective. And this, you could actually see this right here. So this is our objective. Oh, of course, there's like an extra concept. Now, once again, I know I didn't go into the algebra. I swear it's very convoluted and it's not necessary to understand what this thing is doing. But once we got into this section, we can start extracting something very useful, and that is that we can train a model now to predict the next the 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 next mean. So we finally arrived to an equation that allows us to train our model to predict the next mean. So once again, what does this mean? Is like what we had before. So you were at a certain time step, right? So let's just say we were here, and then the model is trying to predict like, okay, the next mean is going to be here, right? So this would be the mean for our distribution. And now we can train the model with this objective in mind. Okay, so we arrived at something that we can train our model on. Now, it turns out that we can do a reparameterization. And I swear this is the last thing. And once you learn this, you will understand what most people think of diffusion models, which is like removing noise. Well, this is how you get to removing noise. So once again, the derivation for these equations are non-trivial, so we're not going to take a look at that because I don't think it's that useful. But let's just say that we can prove that our first mean can be represented as this, which is the same thing as this. So this is just algebraically equivalent. And then, if we can prove this mathematically, so we have a form for this one right here. And then we can also prove that, like, okay, equation 10, so this is equation 10, reveals that our model must predict this thing, which is this thing, given x of t. Since x of t is available, why is x of t available? Because we defined it here, right? So we can, this is our one shot. This is like, give it a time step and you will get the noise image at a time step, one shot. So since we have our one shot available as an input to the model, we may choose the reparameterization of this. So once again, what is this thing saying? This is just saying like, okay, we define our mean and our other mean, and we reparameterize them to now, instead of predicting the mean, we can predict something different. So let's just take a look super quickly of what that looks like. So you will basically end up with these two equations, which once again, let's just do like this equation minus this equation, which are, just to make it like even simpler, this is this one, this is this one. And then once you do the subtraction, well, we can do this very simply, right? So like you can take this out, and then it turns out that this x of t will cancel, right? Because like x of t minus x of t, this will cancel, and then we're left with, once again, we can pull this out. We can pull this out, and we are left with e minus e. Sorry, this is a yeah, sorry, minus e plus. So this is what we're left with, right? So this is our this is how we reparameterize. Now, if we take a look at this, it turns out that this is not dependent on the mean anymore. This is just dependent on the noise. What does that mean for us? Well, it just means that since we have our loss, we can now plug this result. So we can now plug this result into our function, and this will basically turn the tables on our loss function. And now instead of trying to optimize for the mean, we're trying to optimize, or like we're trying to learn the noise. So we're not trying to learn the mean anymore. Now we're just trying to learn the noise. So this thing, before we're trying to make the model learn this objective, and now we found a way to reparameterize our objective in a way that we now can predict noise. So how does this look like finally? Well, finally, at the end, it looks like this. So let's just take a screenshot. And this is the most important part. If you didn't get the rest, That's okay. I did find a little bit troubling how to find a little bit troubling how to explain this, but this is our loss. This is our loss now. Once again, everything that you need to know from this is that this is just a constant. So we can call this, okay, it's just a constant. This is just a number. But the important section, the absolutely most important part, is that in order to train this model, we can give it the noise, and the model will try to predict that noise, right? Now, what does this mean here? This is just saying that we give it the initial clean image, and this just means that we're sampling from the unit Gaussian, right? So we have a clean image, we have a sample from the unit Gaussian, and then this is our sample from the unit Gaussian. So this is what we sampled, and then our model. What is this thing? Once again, like don't freak out. What is this thing? This thing is just a noise image, right? So this is what we defined before. So this is just like, okay, give me a time t, and this is just our noisy image. So this is just our noisy image. So give the model the noisy image, give the model a time step, and the model will output the noise. So what is this thing doing? This is just saying like, okay, this is the noisy image at this time step. Tell me how much noise we added, right? This is what the thing is trying to learn. And this is why it's so powerful, because now we can reframe our training objective with just the clean image, sample from a unit Gaussian. So let's just be very pedantic. What is this thing? This is just a sample from our unit Gaussian. What is our unit Gaussian? It's this thing. So we're just sampling from here. So we're just getting literally a sample. So we're sampling from this distribution. We have the clean image, we have a sample from the unit Gaussian, and then we can just define our objective like this, and then we have a one-shot equation to get the noisy image. So this is the actual derivation of the loss. Once again, I know this is like very mathematically heavy, and we didn't really go into it. It's a little bit wacky, but I hope that gave some intuition of why are we doing this. And now once we see the code, I think this will be a lot simpler to understand. Okay, so it's time to actually take a look at the code. Now I've made this very simple training recipe just to know um, what we have and what we expecting the code to do. So what do we have? We have these three things right here. So we have our clean image sample. Once again, this is just us grabbing an image from our next sampling. Then we have a random time step. What do we have a random time step? Well, we remember that we defined our general noising as like, okay, just give it the initial image and then any time step, and we'll be able to one shot the noisy image. So this way we don't have to like go through every single one of them. So you can just get a random time step and then see the noise at that point. So what we do is we grab a random time step between 1 and the total time steps. It's okay. We have our clean image, we have a random time step, and then we also get the noise. So we sample from this unit Gaussian, and then we sample from here. So they would just give us like some random number that's some noise. Now with those ingredients, we can now recreate first of all our noisy image. So what is the noisy image? Well, remember that we defined how this would be when we talked about the noise injection, right? So this is just following our equation. We follow our equation, and we already looked at this is actually outputting a noisy image, right? So this would get us a noisy image that at certain times that we sample randomly with a certain random Gaussian noise that we sample randomly, and then we pass the noisy image to our model, and we also pass this random time step to our model. So we pass those two things, and then our model will predict the noise at that time step and for that image. So you're like, okay, this is a noised image. This is a time step. Now predict the noise that went into that image. And then once the model predicts that noise, we just do the loss against the actual noise that we added and our noise prediction. So we just compare those two. And once again, we showed why we get to this point when we define the loss, and it's this very complicated, very convoluted math. But at the end, this is the loss, so we optimize for this. Okay, how does this look in the code? First of all, let's go super quickly through what this code is doing. So once again, it's imports. This is the data, just celebrities. Yeah, okay, celebrities, Elon Musk is somewhere in there. And then this is the data set. We already looked at how we add noise, right? We already said that we can add noise for a certain time step, and we can just do it in a single step, essentially, just one shot. Then we define a model architecture, which is a unit, as we already also took a look at, and you can see the parameters of the unit. We made an entire video about this. And then this is just a sanity check, so I just made ChatGPT take a look at my code and like print every single thing that we were doing, so print every single shape. This is extremely useful and this helps a lot. And finally, we go to training. So okay, this is where everything converges essentially. We've learned the idea behind diffusion with the first paper. We learned what a unit is. We now learned how to derive the loss. We learned how to derive the instant one-shot noise injection. We derived absolutely everything, and now we can actually train these models. So what do? Well, you define the loss as the squared error. Once again, why? Because this is the equation that we find at the end, right? Now we just say, okay, for a certain number of epochs, let's just, once again, let's just see our ingredients. So this is image sample, random time step, and Gaussian noise. So we get the sample. So this is the image samples. Then we get a random time step. Once again, random time step. Then we calculate these things, which are the ones that go into our equation. So we already had this before, remember, when we defined the noise. So we already calculated this. So we already had this. We defined them when we added the noise. So we have this, and then we also generate random sample, which is random normal. Once again, what is this? It's just this random sample. Of course, this is going to be applied to our images, so we want it to be like our images, the same shape. And then we calculate the actual noisy image using our equation that we derived, which is this equation. So once again, alpha bar times the image. So alpha bar times the image, square root times the noise. Square root 1 minus alpha bar times the noise. So square root 1 minus alpha bar times the noise. So we calculate our noisy image. And then we give it to the model. So the model gets the noisy image and the time step. And with our unit, it will predict the noise that went into this noisy image according to this time step, right? So it's gonna predict the noise, and then we train by doing the square error essentially between the predicted noise and the actual noise. So this is where everything converges. Everything we've seen so far converges into this optimization, and we just let it train. So just to show you what this would look like, of course, device, the model is our unit. Um, the channels are three, the output channels are three as well. Then again, we saw what this was in a previous video. Our optimizer, and I just say this, we're gonna run this for 20 epochs. So then we train for 20 epochs. And then let's see what this looks like finally, right? So like everything converges to this point. So let's see how this looks like. Once again, we just redefine everything. And we can now see, okay, we can do the process backwards. So we sample from noise. So we can just get this absolute random noise, and then we go back. So we're at 900, we're at 800, we're at 700. Now, if you're wondering why is this all noise already? Well, this is because we defined our noise schedule as, remember, we defined our noise schedule to like be basically pure noise from 600 upwards, right? So this is essentially pure noise. So this is the default of our noise schedule. So you go down, you go down, you go down, and then you can start seeing faces, finally, right? Now, these are not very pretty faces, but these are phases, right? Like you can tell these are phases. Now the reason why this doesn't work as well is because we're training on some like a little. So I made the images smaller, and we also train for 20 epochs, which is not nearly enough, right? I think they train for a couple thousand. So in order to not make this as expensive, I just train this for 20 epochs. But you can see that these are already phases, right? These are already phases. So we let it cook a little bit more, this would be like a lot better. But you can see that this is doing very well. And now we can test. So in the actual paper, they go into some interesting applications of this. So they go into like, okay, you can do, for example, why it's interesting. You can do progressive generation, right? Or you can do interpolation. So we actually implemented this. So let's just see how this looks like. So here, for example, we just, instead of giving it from absolute pure noise all the way back, we take an image and we noise it a little bit. And then we tell it like, okay, this is this time step where you are right now. Now go to our clean image. And this is what it does. So we just give it the time step and it goes it goes back and it gets the image, the face back, right? So it gets the clean face back. which is really, really cool. Even though we train it for like only 20 epochs, it's already able to basically get rid of all this noise and show the actual image, which is sick. And now just once again to test what they did, so they did like interpolation, and it's like, okay, you can interpolate in latent space. So we did that as well with our tiny model. And once again, what is this thing doing? It's just going from like, okay, this is the image of this face. Now go from this face to this other face, and the faces in between. So we go from here, and this is essentially like this guy with the woman's face. Now, once again, this is not as perfect as theirs because we train it for very little, but see, they're just interpolating between two faces in latent space, and we're doing the same thing, and you can see that it works. Now, we train this for a lot more time, we will get way better results, but this is just to show how these models work, and to make it also very cheap. So yeah, this is the end. This is an actual final diffusion model trained end to end with the entire mathematics explained, with every single part of the paper explained as well, and recreated. So this is essentially the end of part one. I hope everything was clear, and I hope everything was understandable. Now, if you go and tweak the code, that is the absolute best way to like learn everything we've discussed so far. So yeah, it's been a long road. Thank you for watching. Okay, we finally arrived at improved denoising diffusion probabilistic models. As the title says, this is essentially just an improvement over the previous paper that we looked at, which was the DDPM. So better DDPM. And I actually invite you to take a look at the paper yourself and try to understand what these improvements are. Because you should be already like quite able to understand not only the math, but also the intuitions and why are these improvements. So once you've done that, you can come back to this video, and I will first explain what the main improvements are. We will then take a look at the definitions into the actual paper. So where they define the paper, and then finally we'll take a look at the code. So like how do you actually implement this into real code? Okay, so there are three main improvements in this paper. The first one is that we have a new noise schedule. Once again, what is our new noise? What does it mean to have a noise schedule? Is the way that you inject noise. So we took a look at this actually when we saw the original DDPM. So we just said like, okay, for the original DDPM, we're gonna inject our noise in a linear way. So it's like a linear way, and then we said like it kind of looks like this, right? So like at 50, you have certain noisy image, and then 100 is like this other noisy image, and then so on. And then you can take a look at this linear schedule at 800 is like quite super noisy. And then we said like, okay, we can define other equations, right? So we defined other equations. So we said like cosine. What a coincidence. This is the one that they actually use. So once again, this is quite different. So you can, at 800, you can see a face, for example. And then for linear, there's no nothing in there. So once again, this is just a different way to inject noise. And this is the one that they actually use. So okay, they have a different noise schedule. Okay, second one is they learn the variance. What does this mean? Well, if you remember, we said like, okay, you have an original clean image that you sample from your dataset, and then you can noise this image all the way into T, and at T, this would be essentially just like noise. And then you can sample from this noise, and then you can go back, and then you can essentially go back to our clean image. Probabilistically, of course, not deterministically, but you can just go back. Now, this going back, this backward process was defined like this. And then we said like, okay, you make the model learn the mean, and you make the model learn the variance. But it turns out that for the original DDPM, they didn't actually learn this. This is just constant. And then this is the noise, by the way, so we reparameterize. And they just say like, okay, we found out that if you learn this thing, this behaves quite better. We will see this in the paper in just a second. So just have in mind that they learn the variance as well. Now this new learned variance has also a new loss. So the third and major improvement is that they have a new loss.
So what does this new loss mean? It's like, okay, we have our previous loss, so the simple one, and then we have this weight factor, and then we have this new loss. Where does this new loss come from? Well, if you remember from our original DPM loss derivation, this was quite a bit sketchy, but we just said like, okay, if we have like constant, if you have constant variances, this the KL divergence essentially comes into this simple form. But now these are not constant, so these are actually learned. So this is not that easy to define. This a little bit more um, involved, and this is actually where the new loss come from. Now, this is our simple loss, so we essentially have this exact same loss we did before with this new extra loss. Okay, so these are the three major improvements. Oh, and the extra one, which basically comes out of these ones, is that now you can, instead of doing like the whole 1,000 steps, you can sample faster. Okay, now let's take a look at the paper. So super quickly, we just say that, okay, DDPMs are class of generative models. They can achieve competitive log likelihoods. And then we find that if you do what they define, you can sample from fewer passes. Okay, super quickly, the introduction. So Dickstein, we took a look at this paper. So this is deep learning using equilibrium thermodynamics. We took a look at this paper as well. This is DPMs. We showed the equivalence between diffusion, like the DPMs and score-based models. And then, okay, in this paper, we show that DPMs can achieve log likelihood compared to other. Okay, so really good improvements. They learn the reverse process variances using a simple parameterization and a hybrid learning objective. What does this mean? Well, this is what we just talked about. So learn variances, new loss. After incorporating these new variances, we sample in fewer steps. Okay, amazing. So that's what we said. Okay, now the definition. So this is we've been through this math a lot of times by now, but I actually think from the original papers, this might be the best like background math explanation so far. So okay, once again, super quickly, we sample our clean image from our dataset. We define a forward process that makes this clean image noisier and noisier until we get to a sufficiently large t, which essentially makes it an isotropic Gaussian. And then we can like sample from this isotropic Gaussian, and then we learn this reverse distribution. So this reverse distribution, where our model learns this like mean and this variance, and we can go back probabilistically to our original image. Now, we also define this loss, which is what we took a look at the other video. So how do you get to this loss? And they say like, oh, this turns out to be the KL divergence between two Gaussians, which is also what we got, right? So like the KL divergence between two Gaussians. Okay, so KL divergence between two Gaussians and can be evaluated closed form. We know what this is. Okay, so it does not depend on the parameters. Let's keep going. Okay, they also say like, okay, we can get the noise latents directly with the original image. Once again, what is this? This is what we defined on the other video, which is like we have our one-shot equation that boom, you give it a clean image and then it gets you a noisy image at any time that you want. So this is what this thing is saying. Okay, now how do you train? Well, it turns out that we can reparameterize this loss. And instead of learning the mean, you can learn the noise. And then it turns out to be this loss right here, which is exactly what we arrived at, right? So we said like, okay, you can reparameterize this equation into now learning the loss. So this is what these things are saying. Um, okay, perfect. So now this is going to the actual improvement. So what are they learning? Okay, they say like, okay, original DDPMs are unable to achieve competitive log likelihoods, but it turns out that if you make this a little bit better, the impacts are drastic. So, okay, the original DDPM paper basically sets the variance to be constant. So the variance is not learned. And then they say like, why is this not learned? Well, it turns out that the model mean determines the distribution much more than the variance. So it's not that important if this is learned. But they discovered that they can improve the log likelihood by using a better choice of variance. To achieve this, they learn the variance. Once again, if you improve the log likelihood even by a little bit, it has a drastic impact. So that's very important, even if the change is minimal. Okay, so they learn it once again. This is exactly how they are defining this new learned variance. And then they arrive at like, okay, we have a new loss and this new, so this is the simple one, which we're very new. And then we have this weighted one. So once again, weighted, and this has to do with the variance, which once again comes from the full equation out of this. Okay, now they say like, okay, we improve the noise schedule, and then so they go into the problems of the linear noise schedule, and then they say like, okay, we find this equation out to be our new noise.
injection, and then they go into like why is this good, and then very importantly, they say like okay, we use cosine squared in particular because it's a common mathematical function. This choice was arbitrary. That is very very important in my opinion because this just goes to show that you can like just try different things, right? So like they just go like other functions with similar shapes might work as well, which is what we talked about in the original DDPM video, right? We just said like okay, we have a like we have our linear schedule, and then let's just say that we have a different linear schedule, which in this case was cosine, which is what they're using. But we can just define our own noise schedule, right? So we can just define our own functions. Now, of course, they should make sense. So this would be horrible in this case because it's very noisy at the beginning. But in practice, you can just define your own functions, right? Like that's, I feel like this is very, very important for us to get an intuition of like, this is not something that's necessarily coming out of the math, but it's just that you can just, you can imagine your own function. You can just plug it in and see what happens. They have really good, they have a goal. This is not something random. They do have a goal. But once again, bounded by this goal, you can define your own functions. And they say like, okay, we get the best likelihoods by optimizing this new term, and they just go into results, right? So like, how is this better than the original one? They go into the results. So the results. So they say like, oh, this is better. And then they go like, oh, something interesting. That if you do what the improvements that we defined, you can actually sample with fewer time steps. So instead of making like 1,000 or 4,000, whatever, this can be like 25, 50, 100. And the outputs, like the results would be is still quite nice. And then finally they just go into like, okay, if you like make the model larger and then you train for like more time, like this will make the model better. Okay. But that is essentially the most important sections, honestly. Okay, so we are through this is the original DDPM code. Now let's just see how these main improvements are actually implemented in the code. So first of all, cosine schedule, right? Different way to add noise. As I said before, we already defined this in the other like the original DDPM. But just to once again make this a lot clearer, this is our new cosine schedule, and this is how it looks like, right? So like if you go from like 50, 100 to 100, 300, and so on, this is how this is noising the images. And it kind of looks like this, which is the same graph that they have at the in the paper. So okay, amazing. So okay, new cosine schedule, perfect. Now learn the variance. What does this mean, right? Well, if you take a look at the model architecture, and we go into our UNet, so in this case, this is the same UNet as before, and we add the variance. So before we only had out channels, but now we have out channels plus one. Why is this plus one in here? Because now we have like a whole channel that would be the the variance. So if our channels are like 3 RGB, that would be our noise prediction, and then this new channel would be the variance. So this is predicting the noise, this predicting the variance. You just add this here, and our model is not only predicting the noise, it's also predicting the variance. So once again, learn the variance. This is what we're doing here. And finally, our new loss. So simple loss plus a weight factor times our new variance loss. So if we take a look at the training now, take a look at training. This is essentially the same training as before. Once again, sample an image, sample at the time step, then sample the noise, and then we have our one-shot equation that gets our original image all the way to the noisy image for any time step that we want. So we have our one-shot here, and then okay, the model now gets an output. Now this output, as I said before, has now the noise, the predicted noise, and the predicted variance. So what are we doing? We're just splitting the output into the first three channels, which as I said before, we'll take a look at the UNet, right? These three channels are the noise, this extra channel is the variance. And then we get the standard loss. Once again, what is the standard loss? Just split the noise and the noise, which we had before in the normal DPM. And then we actually add these new terms, which essentially use this equation for the KL divergence. And now we define it as to be our new like variance loss. And then we have our weight, and then we just multiply our weight times the loss, and then we add the simple loss, which is what we said before. And then we train. We just train this. Now they actually train this in the paper for like I believe 100 or 200,000 steps. Now that's a lot of compute, and that will be quite expensive. So I only trained this for like 80 steps, 80 epochs, because the loss wasn't changing that much. So I just stopped it here. And the results are not that good as the paper, but we can get an idea of like, okay, this is actually working. So we take a look at our like, we just take an image and then we noise it up to like certain time steps, and then we go back. We can see that the model is actually like learning the how to like go back to the original image. Once again, this is not that good because the model is not um, hasn't been trained for that long. But if you train this for longer, the results would be quite better. So yeah, and once again in our predictions, so like this is our predictions, you're actually taking both the noise predicted and the variance. So we're using both of them for our sample. Okay, amazing. So that was an improvements over over the DPMs. Now we'll take a look at diffusion model speed GANs, which is just like a very fun story. Okay, now diffusion model speed GANs on emergencies. We're not gonna take a look at the paper itself. We're just gonna take a look at the story, which is quite more interesting. So okay, it's 2014, and you're Ian Goodfellow, and you just made this thing called GANs, which are generative adversarial neural networks. And they produce the prettiest images. So they're quite finicky to train. They're hard to train, but they produce the best images, right? It's like you get essentially at this time you get all the money, right? Like everyone's pouring on you. You get like startups trying to get generative AI. You get like research labs trying to find out a way to make all this generative AI work. So this gets like a bunch of money, a bunch of investment. Everyone's trying to get generative AI, and this is the case for like the longest time. So a couple years passed, and then in 2020, here comes Jonathan Ho. So like Ho et al. And if you remember, he's the researcher from UC Berkeley who essentially came up with the DDPMs, which are like diffusion models, right? So he comes up with diffusion models or like DDPMs, and they're not quite yet there yet, right? So they can see that there's a competition between generative AI from like GANs and now DDPMs, but they iterate, and this is why like I've been reiterating every time we see this in the paper that like there's no demonstration they're capable of generating high quality samples, right? So like they insist every single paper, right? Like improvements come out and new methods of making this better come out, but like they're still not able to produce high quality samples until these guys at OpenAI come in. And these guys at OpenAI, they really believe in diffusion models, right? They say like, okay, this is the way. Where this is quite chaotic. We go from chaos to noise. This is kind of like a painter brushing, like strokes, like putting brush strokes. I don't know if this is what they were saying, but I like to believe that this is what they were saying. So they essentially come up. They really believe into like this DDPM technology, and then in 2021 they dropped this paper called "Diffusion Models Beat GANs on Image Synthesis," and then all of a sudden, all the money that was invested into these previous architectures, GANs and all the other ones, is now invested into diffusion models. So this is very important because it sets the time, right? Where like essentially from this paper onwards, this is the point where like they proved that diffusion models worked and they worked really well. So this was historic, right? This is the point where like finally all this no demonstration that they're capable of generating high quality samples. This is not the case anymore. And once again, now all these researchers are like pulling all these resources away from like GANs and all these other methods into diffusion. So it essentially shaped the way that like even like startups and VC and research like they all essentially moved. Of course, it wasn't instant, but this was a process, and this process was essentially led by this paper. So okay, just a quick story, and this is essentially the end of the part one. I hope everything is clear, and I hope this helped clear a little bit of the math behind diffusion